Today we are going to see how Spark works. Now the instructor asks each of them to count the total amount of marble in each pouch they have and to note it down in a piece of paper. I have two JSON files. One is a multi-line JSON file and another is a single line JSON file. Now if I scroll down, we can see 32 paths for partition because that is what we have said. Let me expand my JSON. Now in our data set, we have seen because of a bigger size of partition, this is why it took more than 3 minutes in order to get killed. But the executors are gradually scaled down. How we can optimize a big and a small table join and a big versus big table join. Today we are going to discuss about data lake. We will understand the optimization in data lake, and we will also understand what is the importance of Z orders. About two of the important topics. The first one is deletion vectors, and the second one is liquid clustering on data tables. Hello, and welcome back to a brand new course, PySpark 0 to Hero. Now, before you think what is different in this course, let me give you 3 reasons why you should look into this course. First, Spark is in huge demand for data engineers. Not only for data engineers, even data analysts and data scientists are also using Spark. Second, we are in threat. Generative AI is on rise. It can write any type of code that you need. So we must need to have a difference from writing code to understand how and why the things are important and how the things work in the background. Third, I will be sharing many tips with you and tricks that we use in general production scenario when we work with Spark. So to begin with, hi, I am Shubham and I will be your instructor throughout this course. Believe me, by the end of this course, you will be a hero in PySpark. To start the course, let's see what is Spark. Spark is nothing but an open source unified computing engine for parallel data processing. Distributed computing is on rise, and Spark is one of them. It supports major programming languages such as Java, Scala, Python, R, and Spark is built up on Scala. And the important reason why we should use Spark for data processing is Spark is 100 times faster than MapReduce of traditional Hadoop. Spark processes data using RAM, which is in memory and which is very fast. What are the Spark important components? Now, I'll not dig much more into Spark components because you have seen a lot of documents, a lot of videos about it. I'll just tell you what is important. These are the Spark components on high level structure. Spark consists of 3 components: low level API, structured API, libraries, and ecosystem. The low level API is the bottom structure of Spark component, and the structured API is built upon low level APIs. Low level APIs are generally consist of RDD, which is resilient distributed data, and distributed variables. Structured APIs such as Spark SQL DataFrame datasets are built on top of RDD and are optimized for use. The top level consists of libraries and ecosystem, such as structured streaming, which is built up upon structured APIs, advanced analytics, graph query languages, and other such huge libraries that Spark support. This is all as an introduction for Spark. I'll not bore you with too much of introduction for Spark. You can go and learn a lot about Spark in internet. If this is all we need to know for now. Today we are going to see how Spark works. Now this is very important because we need to understand how Spark works under the hood. There are few important terms with Spark. What are driver and executors? What is job, stages, and tasks? Today we are going to see an example and understand what are driver and executors, what is job, stage, and task, and how Spark works with this. Let us consider a very generic example. We have one instructor who have few group of peoples. So A, B, and 2 different individuals, and we have 4 groups, all marked in green. And instructor has a work. So what he needs to do is, this is a bag of marble, where marbles are segregated into pouches. Now, the job in hand for the instructor is to count the total number of marbles. So what instructor does, he assigns each pouch to different person. So consider this marble pouch goes to A, this goes to B, this goes to E, and this goes to D. Now the instructor asks each of them to count the total amount of marble in each pouch they have and to note it down in a piece of paper. So what each individual does is, A reports he has 10 marbles, B reports he has 5 marbles, E report he has 25 marbles, and D report he has 15 marbles. Now the instructor got the local count for each of the pouches, but he needs the total count. So he asks G, go and collect all the counts and give him the total count. So what G does is, G goes and collect all the counts. So he collects 10, 5, 15, and 25. And he sums up all of them, which is equals to 55. Now G reports this to instructor. The total count is 55. Now the instructor has the total count. Now if you have understood it properly, we did the count in 2 processes. The first one is the local count, and the second one is the global count. And in between these two, we had a shuffle stage where G went and collected all the values from each of the groups. So the data was shuffled between the groups. So this is where the shuffle happened. Now to do shuffle, each one of them has written the data in a piece of paper, right? And that paper was shared to G. So the data was persisted into something. And this is how Spark works. So for Spark, instructor is driver. And each group is executor. And whatever the count was done by each individual is task. And since the counting was divided into 2 pieces, local and global, these are 2 stages. And we saw how these stages were divided when we had shuffle. So whenever in a job there is a shuffle happening, the job will be divided into stages. Shuffle is the boundary which divides a job into stages. You always need to remember this. So with this example, we understand how we arrived at the calculation. Now we go ahead and see what is the individual responsibility of each component. The first one is driver. Driver is basically the heart of Spark application. It maintains all relevant information that is required for executors. It analyzes, distributes, and schedules the work. Next is executor. There are majorly two tasks only for executor. The first one is execute the code, and the second one is respond to driver with execution status. These are the major tasks that driver and executor do. Let's summarize what we have learned till now. A user assigns a job to driver. Driver in turn analyzes, distributes, and breaks down the job into stage and task and assign it to executors. Executors are basically JVM process. This runs in the cluster machines and it consists of cores. Now in this example we have 6 cores and 3 executors. All the 6 cores can run in parallel and perform 6 tasks at a time. And we also need to remember one core can only do one task at a time. So 6 cores running in parallel would do 6 tasks at a time. And this parallel nature is something that provides Spark the capability of parallel processing. Before we can jump into coding and do our hands-on with Spark, we need to understand few more important topics, such as partition, transformation, action, why Spark prefers lazy evaluation, and Spark session. Today we are going to deep dive into these topics. To start with, let's understand what is partition. So to allow executors to work in parallel, Spark breaks down the data, which we call the input data, into chunks, which is known as partition. If you remember our last example, we had a bag of marbles, and the marble were segregated into pouches. In this example, you can consider these pouches as partition. So according to this example, our data was partitioned into 4 partitions. Now this 4 partition of data can be executed by 4 tasks in parallel. This allows Spark parallel processing capability. Now let's understand what are transformation. Transformation are nothing but basically the instructions or code that we supply in order to modify or transform our data. The examples are select, where, group by, and the transformation helps Spark to build up the logical plan. There are basically 2 types of transformations, narrow and wide. So consider this example. We have an employee data set where we have to do certain transformations. Like first, we have to select only those employees who have salary greater than 10,000. Then we have to select only the name, department ID and salary from the data set. And the third transformation that we do is we do a group by on the employee data based on the department ID. Now, if you see, this whole workflow is a type of logical plan that is designed to start from the data set, which is employee, and end at the final data set, which gives us the group by data, which is required as the final output. So this is how the transformations are done, where we have where as a transformation, select as a transformation, and group by as a transformation. Now, what is a narrow and a wide transformation? Consider you have data partitions. Now, these data partitions contribute to only one data partition. Similarly, the other one also contributes to at most one, and the third one also contributes to at most one. This type of transformation is known as narrow transformation. But in case where one partition can contribute to more than one partitions like this partition is contributing to 3 partitions, similarly, the other one is also contributing to 3 partitions, this type of transformation is known as wide transformations. Now, as you can see in the example, the data from one partition is moved to multiple partitions. This is what we also known as shuffle. Wide transformations lead to shuffle. What are actions? We already understood transformation right now. In order to execute that logical plan, what transformation creates, we need actions. Actions basically trigger the execution plan. There are basically 3 types of actions. First, to view the data in console. Second, to collect the data in native languages. Third, if we write the data in output data sources. So we just discussed transformation and action. But what is the use of transformation and action? Basically, Spark prefers lazy evaluation. It means Spark will wait till the last moment to execute its computational graph. Now, what is this computational graph? This is the transformational logical plan that was created. And when an action is called, that transformation graph gets executed. So Spark will wait until an action is called. And why this is necessary? This is necessary for Spark optimize and plan the resources properly. This also leads to executional benefits. Let's understand with an example. Consider you have a sandwich shop and a customer comes up to you and asks for a sandwich, and he asks for a white bread sandwich at first. You start preparing the sandwich and the customer changes his mind and asks for a brown bread now. What will happen? First, you will waste your time on that white bread sandwich. Second, your white bread is wasted, which is your resource. But what is the better way? Consider you wait for that customer to complete his order to pay for it. This payment is an action. Once the payment is done, the order is locked. Now you know what the customer wants. What is the order? Now you know the customer needs a brown bread and whatever ingredients into that sandwich. You can easily plan for it, and now you can make the sandwich in more optimized way. This is what is called lazy evaluation, and Spark also prefers lazy evaluation. And the last topic for today is what is Spark session. So if you remember that example, that instructor, the instructor was the driver, and that driver process is Spark session. Spark session is basically the entry point for the Spark execution. Spark session is responsible to execute code in cluster. And for one Spark application, there can be only one Spark session. Don't worry, if you're still confused about Spark session, we still have hands-on sessions. We'll see Spark session elaborately in our hands-on session. Today we are going to discuss about DataFrames, which are the most important structured API and are built on the low-level APIs such as RDD. DataFrames are the most common structured API, which looks like a table. If you can see on my screen, it looks like simply a table, which constitutes of rows and columns. There is a schema associated with a data frame. That implies each column will have its own metadata. The data in data frames are stored in partitions, and the data frame are immutable. Immutable simply means that once a data frame is created, you can't change anything about the data frame. However, you can create a new data frame out of that data frame. Now to understand with an example, consider we had employee data which we read into a data frame. Now we had to filter the data where the salary is greater than 10,000. So we can create one more data frame out of this first data frame. Now we had to select only name, department ID and salary from the second data frame. So we can create a third data frame. So these are immutable. You cannot change anything about the first data frame. However, you can create multiple data frames out of the previous data frame. There's another way which is cascading, where you can cascade more than one transformation commands from one data frame and you can create a new data frame. Consider we have an employee data frame where we have data stored in 4 data partitions. Now we have a transformation that we need to apply on this data frame. Once the transformation is applied and the action is called, the data partitions are shared across the cluster. Now each core can work on each partition of data with different tasks, and all the tasks can execute in parallel. So 4 tasks in this case can execute in parallel on this data frame. And this is the main reason why Spark prefers keeping data in partitions. Now let's understand how Spark works on planning for the structured APIs. To work on the execution plan for a structured API, Spark basically goes through 2 planning sessions. One is the logical and second is the physical. On my screen is the logical planning workflow. Once the code is supplied by the user, Spark creates an unresolved logical plan. This unresolved logical plan is validated against the catalog in order to validate the column names and the table names. Once this validation is done, Spark creates a resolved logical plan. This resolved logical plan is taken into the Catalyst Optimizer, which basically does the whole optimization for the logical planning. Once Catalyst Optimizer completes its optimization, it generates an optimized logical plan, which is the logical DAG. Next in planning is the physical planning. Once the optimized logical plan is ready, Spark generates multiple physical plans based on the cluster and the physical configuration. These physical plans are run against a cost model, which basically generates cost for each of the physical plan. Once the cost is validated, Spark selects the best physical plan. And that physical plan is sent to cluster for execution. And once the executor receives the physical plan, they run that physical plan against the data partitions. And that is how the whole execution for Spark works. The last thing pending is DAG. DAG is directed acyclic graph. As you can see on my screen, this is how a simple DAG looks like. We have arrow marks pointing to the next step. And Spark uses DAG to resolve its executional plan. I am very excited. We are going to start our hands-on. To make sure you understand every concept along with the code, some videos can be lengthy. So make sure you watch them till the end. By the end of every video, I'll share one bonus or interview tip that will definitely help you. Now, you must have basic knowledge of Python and SQL to complete this journey. If you are new to Python, I'll add one link in the description to get you started with Python. Before we start, we need an environment in our local to practice. To follow me along, you can check out third video of my YouTube series, Data Lakehouse, Data Warehousing with PySpark. This third video provides the specific installation instruction of PySpark on Docker, and this is the same environment I'm going to use for this tutorial. This is my Jupyter Lab environment. I'll write code in Jupyter notebooks. Now I prefer notebook for now so that we can run each command individually and understand what is happening in background. For today's example, we will generate an employee data set and we will filter out employees having salary greater than 50,000. Then we will write the data set as in form of CSV into our output location. Now before we can write our program, we first need a Spark session. We know Spark session is a driver process that is the entry point for our Spark application. To get the entry point, we need a Spark session object. And to create an object, we need a Spark session class. The Spark session class can be imported from PySpark.sql module. Now, you can name your Spark session object anything. You can name Shubham, you can name Apple, you can name anything. So let's create our Spark session object. To create, we will use this builder method from the Spark session class. Spark session dot builder. Now we need to name our Spark application. To name, you can use app name and you can put any name. Let's put Spark introduction. Since we are working in local, we will use the master, which is the location where this code will be executed. For now, we will keep the master as local. In brackets, we will put it as star. Star will allow us to open the number of worker threads equal to your logical code. For my machine, the logical code number is 8. So it will open 8 worker threads to work in parallel. And at the last, we need to call get or create method. Now, this is a generic code for Spark session object. This will remain same for majority of your code. However, we can add few configs to this, which we will see in the later part of our course. For now, this generic Spark session will work for us. Let's execute this cell. Now, the cell execution is complete. Let's go ahead and check what this Spark session object is. We get some information when we execute this cell. We have the version of the Spark, the master, and the application name that we used. Along with this, we see one more thing, Spark UI. For every Spark session object we create, Spark provides us with an application UI. To open the application UI, you need to go to localhost 4040. Let's open the UI. This is the Spark UI. We will learn about Spark UI in more detail as we move along through the course. For now, we will just check SQL/DataFrame tab from this UI. This tab lists the query that are executed for structured API. Since we are dealing with structured API, any execution code that we run would be listed as query in this tab. We can come back and see our query executions in this tab. Now, since we have created our Spark session object, let's create our employee data and schema. This is our employee data and this is our schema. Employee data is a list of lists. Each list is an employee record. Now, we also have the employee schema, where we have columns like employee ID, department, name, age, gender, salary, hire date. For now, we are using string as a data type for all the columns. Now we have the data and the schema. Let's create our first data frame. We will use emp as our name of the data frame. We will use the Spark session object as Spark dot. We will use one method called create data frame. In this method, we will have two parameters. The first one is data, which is equals to the employee data that we have just created in the above cell. Next is schema. Again, we have the employee schema. Let's run this cell. Okay, the execution is complete. Now, if we go back to our Spark UI and refresh, nothing happens. Let's go back to our Spark session and let's validate what are the number of partitions for this data frame. If you remember from our previous discussion, Spark reads data in form of partitions. So whatever data frame we create would be built up in number of partitions. Let's check the number of partitions for this employee data frame. For this, we need emp.rdd.getNum partitions. If we run this, we see it has 8 partitions. If we go back and refresh our screen, nothing yet. Now let's see what is the data in this employee data frame. For this, we put emp.show. Now, show is an action here. If you remember, actions are responsible for creating jobs. Let's run this action. Okay, we can see our data now. Let's go back and refresh our data frame screen. Great. This is our first query, which has been created as soon as we call our actions. For this, 3 jobs has been created. Let's write our first transformation. We know we need to filter out employees with salary greater than 50,000. For this, we have an employee data frame, but we know data frames are immutable. It implies we cannot change anything about emp data frame, but we can create a new data frame out of that data frame. Let's create emp underscore final as a new data frame from emp data frame, where salary is greater than 50,000. Now, if you can correlate, this where condition is similar to SQL, what we use. Let's run this cell. If we go back in our Spark UI and refresh, nothing happens because Spark prefers lazy evaluation. Until we call an action, no transformation will be executed. Let's validate our employee final data frame partitions. It is still 8. If we go back and refresh, nothing happens because we have not called any action yet. Now, let's write our data in form of CSV. Again, writing the data to output is an action. Let's write our emp final data frame. To do that, we will use emp underscore final dot write dot format. Our format would be CSV, and we will write the data into our output location. Let's execute this cell. Okay, this cell execution is complete. Let's go back and refresh. Great, we have one more job created because write is again an action. This completes our demonstration for today, but this helps us to understand a few things about Spark. First, Spark prefers lazy evaluation. It implies we can write n number of transformations, but those transformations will not be executed until we call an action. Second, we can use Spark UI, which is the application UI, to understand what is happening in the background for our jobs. Spark also provides an interactive shell that we can use to start working with Spark. Let's open that interactive shell. Since my installation is a custom installation, I will the Spark command from /spark/bin/PySpark. Now this is an interactive shell that Spark provides. You can start writing the code here and it will start working. You can see the master is local here and we already have a Spark session created as Spark. So if we write Spark, this is a Spark session which is already available to us. So we don't need to create a new Spark session to start working. We can go ahead and write our data frame transformations here directly. Now the bonus tip of the day. Since Spark session is already provided in this interactive set, is there some way I can use a different name for a Spark session? The answer is yes. Consider I want to use Shubham as a Spark session name. To do this, what I'll do is I will use Shubham equals to spark dot get active session. Once I hit enter and I type Shubham, see now Shubham is a Spark session object. I can use this object to create my data frame. And both Shubham and Spark are pointing to the same address location. This is again an important interview question. In our previous video, we wrote the code for our first data frame. Today we will understand a few concepts about data frame columns, data frame rows, data frame schema, and we will see few structured transformations such as select, expr, and cast. Now, if you are new to the series, I would recommend you to go back and watch our previous video from the playlist. I am in my Jupyter Lab environment. In our previous video, we saw how to create a Spark session object and we created an employee data frame with the data. Today we will use the same data and we will proceed with our basic structure transformation. Let's generate our Spark session and employee data frame first. Here is the data of our employee data frame. If we go back in our Spark UI, since we called the show action on our employee data frame, we have one query created. Let's validate the schema for the employee data frame we just created. To view the schema, you can type emp.print schema. As you can see, we have defined all the columns as string, so we have all the column names and data type as string. Now, there is one more way in which we can view the schema. For that, you need to write emp.schema. Now, if you see, there is something different that is printed out. Spark basically stores the schema in form of struct type and struct fields. To define a schema, we need to have a list of struct type along with each column as a struct field with the column name and the data type and the nullable field. Let's consider an example. Consider we have a schema string of name with data type string and age of data type integer. Now, to write this in Spark's native data type, we need to import struct field, struct type, string type, and integer type from PySpark's SQL.types module. Let's import those. Now, to convert this schema string into Spark's native schema, we need struct type as a list. We need to define each column as a struct field along with its data type and the nullable. So, struct field would be for the first column, the name, and the data type is string, and nullable is true. When we say nullable is true, it implies it can hold null values. For the second field, which is age, we will again define struct field with the column name as age and data type as integer type and nullable as true. Now, in case the value is a non-nullable field, then you need to define here as false. Now, this is how Spark defines the data type. However, you can also use schema string to define your data frame's schema. Spark uses a method to implicitly convert the schema string into the Spark's native data type method. We will see that in the bonus tip for today. A data frame basically consists of two parts. First one is column and second one is row. Column is similar to that what we have in a spreadsheet or a pandas data frame. We can select, manipulate, or remove columns from data frame, and these operations are known as expressions. Now, to put expressions on columns, you need to have real value for the column, and for that you need rows. And to have rows, you need data frame. And that is why you cannot manipulate individual columns out of data frame. To manipulate a column, you need a data frame. Now, there are many ways in which we can define or refer a column. Let's see few of them. Now, to call a column explicitly, we can use COL or EXPR from PySpark.sql.functions module. Let's see an example. Now you see this is a column. Again, we can change it to EXPR. If we run, we get the same column. This is because any manipulation done on a column is considered as an expression. Now to call a column from a data frame, we can use emp.salary. See, we can call the employee data frame salary. There is one more way in which we can call the salary column from the employee data frame. That is using the brackets. If we run this, see, we get the same column salary from the employee data frame. Now, since we have understood how to call the columns from a data frame, let's go ahead and write our data frames. To make things easier, let's correlate our data frame queries with a SQL query. Consider we need to select few columns from the employee data frame, which are employee ID, name, age, and salary. Consider our output data frame would be emp_filtered. Now, to select columns, we can write emp.select. Now we know how to implicitly call the columns. We can use COL in bracket, we can put employee ID. We can also call EXPR and we can also put name, or we can use emp.age, emp.salary. Now if we run this, nothing happens because select is a transformation. We can go back and refresh. See, nothing happens. Now to view the data from the data frame, we can call the show action. So let's call the show action filtered.show. This is an action and this will trigger a job. Let's run this. See, we have selected only the required columns, employee ID, name, age, and salary. Let's go ahead and refresh. See, we have one more source string method, which is an action. Now consider from the created data frame, we need to rename employee ID to EMP_ID, and we also need to cast the age from string to integer. Let's write our second data frame now. Our EMP_casted. Since we can write columns as expression, we can write EXPR and we can directly put the expression. Again, we can call the emp.name column. Now again, cast is an expression that we can use. So we can write EXPR and we can put it as an expression. And we can call the salary column. We can write emp.salary. Let's run this. Nothing happens as select is a transformation. Let's view the data. Awesome. We have just renamed our column and we have also casted our age to integer. Just to verify whether the scheme is properly casted, we can write emp_casted.print scheme. See, age is integer now. So it is very evident that we can use EXPR to write column expressions. And to explicitly call column, we can use DataFrame.columnName. Now, Spark provides one more better way. The combination of select and EXPR in one method called selectEXPR. Let's use that method. From the same employee filtered data frame, we have to rename and cast the data. Let's create one more data frame called emp_casted1, which will be our new data frame, and we will use the same filtered data frame. And now we will use selectEXPR in place of select. Now we don't need to explicitly write EXPR for our expressions. We can directly write our expressions. Consider employee ID as EMP ID. We can write name as a column. We can write cast age as integer as age, and we can also write select salary. Now if we run this, nothing happens. Let's view the data. See, this is again the same data, but this time in a more neat way. We don't need to call EXPR explicitly because select EXPR does the job. Now, you can also write column names directly inside select. You don't need to call explicit column names emp.salary. You can directly write salary inside select. Now, since our casted column is there, let's write a filter statement to filter out age greater than 30. So we can write emp underscore final is equals to emp underscore casted dot select. Now we have already seen column names are basically expressions. So you can call the column names directly inside the select statement. So we can directly write select emp id, name, age, salary. Now to put filter, we can write where our expression would be age greater than 30. Now if we run this, nothing happens. This is because again select and where are transformations. To call an action, let's view the data. Emp underscore final dot show. See, we have filtered data where all ages are greater than 30. Now we can again write this data in form of CSV, which will again be an action. So emp underscore final dot write dot format, which is CSV dot. Now if we go back and refresh, you can see all the source strings that we call to view the data, and finally the same method in which we are writing the data. Now bonus tip of the day. Now if you remember our schema string that we used in the previous example, name as string and age as integer, we can use schema string also as a scheme rather than writing the Spark native scheme. But how does Spark converts this implicitly? There is a method that Spark uses, which is PySpark dot SQL dot type. Now, if we pass this schema string into this method, we will get the native Spark data type. Let's call this. If we run now, see, Spark implicitly converts this into the Spark native data type. And this is how Spark automatically handles the schema strings. So you can write either the Spark implicit data type or you can write schema strings directly. Spark will be able to handle those schema automatically. This was the bonus tip for today. Today we are going to work with few more basic transformations such as adding columns, using literal or static values, renaming columns, removing columns, filtering or limiting data from a data frame. But before we jump into the hands-on, if you have not subscribed or if you have not seen our previous video, I would recommend you to go back and watch our playlist. You can click the I button at the top. I am in my Jupyter Lab environment. Now, we are going to use the same employee data frame that we created in our previous sessions. Let's quickly generate our Spark session and employee data frame. So our employee data frame is ready. This is the data for our employee data frame and this is the schema. All the columns for our employee data frame were string. As usual, in order to make our data frame queries easier, we will correlate it with the SQL query. Consider this SQL query. We are selecting employee ID, name, age, and we are casting the salary as double. Now, we have already seen casting in our previous video where we used the expr method to do that. But today we are going to use the PySpark data frame APIs that are provided by the PySpark SQL functions module. Let's import column and cast. Let's write our employee casted data frame. Now, let's select employee ID, name and age from employee data frame. Now, we know that we can use the call method in order to explicitly call a column. Let's call the salary column as call. Now, in order to cast, we can write dot cast and we can put double. Let's run this. Okay, in order to verify, we can write print schema. Awesome. Looks like our salary column is casted properly. Now, since our salary is already casted to double, now we can calculate our tax. In order to calculate our tax, we will use salary into 0.2, which is 20% of the salary. Let's create our tax data frame. For that, we'll write emp underscore taxed is equals to emp casted dot. Now, since tax is a new column, in order to add a column, we can write that column as an expression in select. But there is a neat way. We can use with column that is provided by Spark. With column will help us to add a new column or override an existing column. Now, since we are adding a new column called tax, we will write tax And we can now put the formula to calculate tax. Let's run this. In order to view the data frame, let's type .show. Nice. Now we have a new tax column which is calculated as 20% of the salary. Consider a case where you need to add static values in your data frame. So consider this. We are adding 1 as a new column called column 1, or we can add a constant string called 2 as a column 2. Now in SQL, we write 1 as column 1, 2 as column 2. This will add 2 new columns in the table itself, and the value for those columns would be 1 and string 2 respectively. In order to create that distributed static column, we would need literal. Let's import the lit method from PySpark SQL functions. Now we know that to add column, we can use the with column. Let's add 2 new columns to the employee tax data frame. We will create EMP new calls as a new data frame that we will create from the employee tax data frame. Now to add first column, we will write with column, and name of our column is column 1, and we will use lit, in bracket we will write 1. This will add one new column, column 1, with the value of 1. Now again we have to add one more column, so we will write again with column 2, and the static value inside the lit method, which is 2. Let's validate the data. Nice, we have 2 new columns as column 1 and column 2, and if you see, the value is static throughout the table. This is how we can add new columns in a table. Now, what if we need to add 10 columns at a time? Do we need to write with column every time in order to add a new column? No, there is a better way. We will see that as a bonus tip for today. Consider we need to rename columns. Now, in our SQL query, you can see employee ID is renamed as EMP ID. So, Spark provides with column rename, which will help us to rename columns. Let's quickly look into that. From our data frame, employee new calls will create a new column called EMP underscore 1 equals to. Now, to rename a column, we will use with column renamed. This will help us to rename any column. So we have to rename employee ID to EMP ID. If we run this, nothing happens. As we know, this all are transformations. In order to run something, we'll need action. Let's run the show method, which is an action. Nice. You see, the employee ID is renamed. We can use with column rename in order to rename columns. Again, you can do this in the select expr as well, or you can use the expr method that we have seen in our previous video. So there are multiple ways in which you can rename a column in Spark. Now, there's one important question that is always asked. Can we use a column name with spaces? You see, column and 2 has space in between. So can we use this name as a column name? Yes, in Spark we can do that. In order to do that, we can use the same column rename method that we have just seen. Let's create a EMP2 data frame from our EMP new calls data frame. We'll write with column renamed, and we'll rename the column as column 2 to column 2 with spaces. Let's view the data. Awesome. You see, the column name has space. This was just for demonstration. If you are sending this data to any downstream systems which are using column names, and if there is a space in the column name, the downstream system might throw some error. This is why in production systems, we never recommend put spaces in column names. What if we need to remove columns? Is there a way we can do that? Yes, we can do that. Let's drop the column 2 we have just added. To do that, we will write emp drop data frame from our emp new calls data frame. In order to drop the column, we'll write drop, and we'll just add the column name, which is column 2. Let's run this. Nothing happens because we are writing transformations. Let's call an action. Nice. You see, the column 2 is dropped. You can use drop to drop n number of columns. In order to drop more than one column, you can use the comma and put the column names. See, both the columns are now dropped. We have been filtering data from the very previous session of our hands-on. We know how to do that. Let's create our employee filtered data frame. We'll use employee dropped data frame, and we will filter using where, and we'll put the filter statement where tax is greater than 10,000. We'll run this, nothing happens since these are all transformation. Let's run the show method. Nice, you see the data is filtered based on tax greater than 10,000. We can also use limit in order to limit the data. Consider from the filtered data, we only need to see 5 records. We can do this using limit, and in bracket we'll put 5. If we run this, nothing happens. Let's view the data. See, there are only 5 records now. You can also limit the data while viewing. Consider you want to show only 2 records. You can put limit as 2 in the show. And if you run this, it will automatically limit the data. But it is not necessary that we always need to view data in the console. If you are writing files and you need only 5 records, you need to put dot limit and in bracket 5 in order to do that. Now, time for bonus tip. We were discussing, consider a case where we need to add 3 columns at a time in a data frame. In order to achieve that, we need to write with column 3 times. But is there a better way? Yes. Consider you need to add 3 columns, where the first column is a tax, where you need to calculate the 20% of the salary column. And the second column is a static value 1. We'll put lit of 1. And the third column is a static value of 2. We'll put lit of 2. Now, we can create a dictionary like this, where we'll add all the columns that we need to add. Now, since we have the employee data frame and we want to add these columns into the data frame, what we will do is we'll create EMP final data frame from EMP data frame, where we will add with columns. Now, within this column, we can pass this dictionary of columns. Let's run this. Nothing happens since we are dealing with transformations now. In order to run this, let's call the show action. Awesome. We have all 3 columns added. We have the tax calculated from the EMP data frame. We have the static value as 1, and we have the third column with a string value of 2. From our past 2 sessions, we are looking into the basic structure transformations that we can work with data frames. Today we will look into few of the transformation and functions that Spark provides to work with string and dates data type. We will also see how to handle null data in Spark. But before we start, if you have not seen our previous videos or you have not subscribed, I would like you to go back and watch our playlist. I am in my Jupyter Lab environment. Before we can start working with strings and dates, let's quickly generate our Spark session object and our employee data set we have been using from past 2 sessions. I'll quickly run through all the cells. So our employee data frame is now ready. We have all the columns and data populated. And if we check the schema for our employee data frame, we can see all the columns are string. As usual, to generate our data frame queries, we will correlate with the SQL queries. So consider a case where we need to add a new gender column, which will be M and F. Based on the case 1 statement, when gender is male, we'll put it as M, and when gender is female, we'll put it as F. In case the gender is something different or null, we'll keep it as null. Now, Spark provides us with the when function that we can import from PySpark SQL functions module that will help us to write this case 1 statement. Let's quickly import the when function. Let's create a new data frame, employee gender fixed, from our employee data frame, where we'll add the new column new gender, and we will put our case when statement in PySpark data frame API. Let's create our new column new gender. Now we will put the case when statement. To do that, let's write when, and we'll put the column name call and put the column name as gender. We'll put the equality condition as equals to, and if it is male, we will denote it as M. Now we have one more condition. When the gender is female, we need to make it F. Let's write that condition again. Dot when. Nice. Now we have one else condition. If it is not male or female, we need to put it as null. Let's write the otherwise condition. For that, we'll write otherwise null. It implies if the gender is male, it will denote it as M. If the gender is female, it will denote it as F. But if there is no gender, it will be none. In Python, we denote none as null. Let's run this. Okay, now we can see the data. Great. We have the new column, new gender, where we can see the male columns are denoted as M, the female columns are denoted as F. But we have null where the condition was not met. Now, if you don't like writing the when case statement like this, you can always use the expr method. We have used the expr method in our previous sessions. Let's import the expr function and we write a new data frame called emp gender fixed 1. We can write emp dot with column new gender. Now we can use the exer function as this. We can completely copy our case when statement from SQL and we can run this. Now let's view our _1 data frame. See, the new gender is also converted now properly. So there's a flexibility in Spark. In case somewhere you don't like to use the PySpark data frame API, you can always use the case when statement inside the expr function. Now, PySpark provides too many transformation functions for string. If I start writing all of those, even 100 episodes will not be enough. You can go ahead and check this link to find out all the functions that are provided by PySpark. You can go to string functions and you can check out the functions that are available for string. We will check one of the important function today, which is the regex replace, which will help us to replace strings. If you see the select query, I have written a replace condition where if in the name, if there is a letter J, we'll replace it with Z. For that to happen, we need to import regex replace. Let's do that. Now, since we are writing a new column called new name, we will use the with column method. For that to happen, we'll write the new column as new name and we'll put the regex replace and put the column name and we will replace J by Z. Let's run this. Now we can validate the data. Great. If you see, the John Doe has changed to JOHN Doe, right? So we were able to replace J to Z. Similarly, you can find a lot of string functions that are available to help you out with PySpark. Just go ahead and check the link I just shared a few minutes back. Now, dates are very important data type in our data set. We must know how to work with dates. So, if you see our data set, we have one column called hire date, but the data type for this date is string. We need to convert this into date first. Let's write that transformation. So, we are selecting all columns and we are overwriting the hire date by converting this to date. To do that, we will use toDate function from the PySpark SQL functions video. Let's import that. Now, we will write one more data frame called emp datefix. Now we know we can use with column to add columns or overwrite the existing one. Let's overwrite the hire date by converting that into date. Now we can write toDate and we can call the column hire date and we have to provide a format expression in which the data is present. If you see the data is present in form of YYYY, MM and DD. If you don't understand what is YYYY, MM, DD, then these are literals that denote date and timestamp. For now, I'll just write it. I'll share one link which will show you the date time patterns that PySpark supports. So for that, we'll write YYYY, which is denoting the year, then MM, which is denoting the month, and DD. Now, if we run this, nothing happens because these are all transformation. Let's write our action. Great. We can see the date is converted, but we are not sure. Let's print the schema quickly. Awesome. You see this? The hire date is a date. Earlier it was string. So we were able to overwrite the column itself using with column. Now, in certain cases, we might need to add the current timestamp or the current date in the data frames, which we call as sysdate or now. Now to do that, we need to import current date and current timestamp from PySpark SQL functions module. Let's do that. Now we'll write a new data frame from our employee fixed data frame. Now we'll add the first column as date now. We'll call the function current date. Now to add one more column, we'll write with column. Now we'll add timestamp now. and we'll call the function current timestamp. Great. If you see, we have new column called date now, which is denoting the current date, and timestamp now, which is denoting the current timestamp along with the date. Now, if you see, the data is wrapped automatically because PySpark is trying to show you the data as much as possible, but wrapping the data which is exceeding. Now, if you want to see the whole data set, you just need to put truncate as false. If we run this, see, now the whole data is visible. Before we wrap up with dates, sometimes we need to extract date, month, year, or hour, time zone from the date or timestamp part. We also might need to convert the date into strings in a different format. So is there a better way to do that? Yes, and that will be the bonus tip for today. Now, if you remember, for one of the gender record, we had value as null. PySpark supports manipulating null values. If we wish, we can drop the row itself. To do that, let's create a new data frame called emp1, for example, which will bring from emp dated, and to drop the records which are having null values, we can write na dot drop. Now, if we run this and we see the data, you see the 18th employee ID is now missing. It implies that PySpark have automatically dropped the null record. Now, dropping a null value is never a good option. In a production scenario, we basically transform the null values data into something else. So in our case, for new gender, we will transform the null values to O, which will denote to others. Let's write our null data frame as emp null df, which will be from the emp dated data frame, and we will override the new gender column using with column. Now, to do that, we need to import Coalesce from this PySpark SQL functions module. Let's import that. We can write the Coalesce function as Coalesce. We can put the column name, which will be the new gender. And we need to transform this with O. But we know from our previous session, we cannot write strings directly. We need literals. So we'll write lit of O. We also need to import the lit now. Let's run this. Nothing happens. Let's view the data. Great. If we scroll down, see wherever the value is null, we are denoting it as others, which is O. We have been adding so many columns. Let's fix our data frame quickly. To view the data frame, we'll write emp underscore null df, which is our last data frame. We'll write a quick show method. To fix our data frame, we need to drop the existing name and gender column and rename the new gender as gender and new name as name. Let's write our final data frame. Emp underscore final is equals to emp.null data frame dot drop will drop name and will drop gender, and we will rename with column renamed new name to name, and we again write with column renamed new gender to gender. Now if we run this, nothing happens. Let's view our final data frame. Great. If you see, we have renamed the column as name and gender. Let's write our final data frame in form of CSV. To do that, we'll write emp underscore final dot write dot format, and the format would be CSV, and we'll save it at location. This completes the demonstration for today. Time for bonus tip. As a bonus tip for today, we will see how to convert the date into strings and how we can extract date information from strings. And to do that, let's import one of the function called date format. Let's write emp fixed as a new data frame, which we will call from emp final data frame. And we'll add a column called with column, in which we'll add date as string. Okay, to convert this, we'll use the date format. Now we know the column higher date is a date, so we'll write higher date. Now consider we need to convert it in form of dd slash mm slash yyyy. If we run this, nothing happens. Let's see the final data frame. Great. If you see this, this is now string, and the date is converted from 2025-01012 to 01/01/2015, and this is also string now. Now, what if we need to extract a few part of this? Consider we need to extract the year out of date. How can we do that? We can use the date format itself, but this time we'll only put YY. Now, if we run this, you see we are able to extract date now. Let's extract the zone from this timestamp column. To do that, we'll use this column as a column, and the literal notation for zone is small z. Let's run this. You see the zone is UTC. Spark provides an elaborated documentation for datetime patterns. You can go through this document and understand which character we need to extract which values. Consider you need to extract hour, you need to use capital H. Today we will look into one of the most important topics. Those are sorting, union, and aggregation of data frames. If you have not seen our previous videos, I would recommend you to go back and watch our playlist. I am back in my Jupyter Lab environment. Now, we have been working with employee data for past few sessions. Today we will just split the data into two. So we'll create two data frames called EMP data 1 and EMP data 2. I've just split the employee data into two parts. The schema of the employee data will still remain same. We will use employee ID, department ID, and all other relevant columns, and all the data types for those columns will still be string. I have used spark.create data frame in order to create both the data frames. The name of the data frames are EMP data 1 and EMP data 2. Let us quickly run through by generating Spark session and the employee data frames. Okay, the employee data frames are ready. We have two data frames called EMP data 1 and EMP data 2, and you can see the data for both of the data frames. Now, if I scroll down, you can see the sequence of the columns for both the data frames are same, and the data types are also same. Employee ID string, department ID string, name, and other columns are also string. Now, in both the cases, the sequence and the data types are exactly same. First, we will begin with union. Union is basically a process to combine two data frames into one, but there is one condition. All the columns from both the data frames should be same, and the data type should also be same. But for union and union all to work, we also need the column sequences to be same. So if we see the EMP data 1 and EMP 2 data frame, both the data frames have same columns with the same data type. So we can easily combine both of them into one data frame using union. Let's do that. We can write EMP is equals to EMP data 1 dot union, and we can put the second data frame, that is EMP data 2. If we run this, nothing happens. Let's see the data. If you see, we have combined both the data frames into one, which is EMP. Now, what is the difference between union and union all? We can also write union all, and we can run. The same thing will happen. We'll have the same data set. The reason is we don't have duplicates in both the data frames. If we have some records which are present in both the data frames, in case of union, there will be no duplication. Only unique or distinct records will be put into the single data frame. Now, consider a case where you have same data frames, for example, EMP data 1 and EMP data 2, but the column sequence is not same. Implies both the data frames have same columns and same data type, the column sequence is different. Can we do a union of both the data frames? The answer is yes, and that will be the bonus tip for today. Now, since we have already created our EMP data, let's write a simple sort based on the salary in descending order. So our SQL query is select star from EMP, order by salary descending. In order to sort the data, we first need to import the descending function or the ascending function from our PySpark SQL functions library. Let's import that. Let's create our EMP sorted data frame from EMP data frame based on order by salary. We'll write order by, and now our column for sorting is salary. So we'll write column salary dot. Now we have to sort by descending. We'll write DESC. We run this, nothing happens. Let's see the data. If you see, our data is sorted based on salary column. We have 75,000, which is the highest one, and we have 45,000, which is the least one. Now, if you want to sort it based on ascending order, you just need to change it to ASC. And if we run, the data is sorted based on the ascending order. We have the least 45,000 in the top and 75,000, which is the highest, in the bottom. Aggregations are basically one of the most important part of data analysis. We basically combine and find out a result in the process of aggregation. So consider an example where we need to find out the count of employees grouping based on the department ID. So in order to do that, first we need to import the count function from PySpark SQL functions. Let's do that. Let's write our EMP count data frame from EMP sorted data frame. Now, in order to aggregate, we first need to do the group by. So we'll write group by based on department ID. Now we need to aggregate the count of employees. So we'll write dot agg for aggregation, and we'll write count, which is our function, and put the column name, which is employee ID. Now if we run this, awesome, we have the count of employees based on department ID. But if you see the column name, this is count of employee ID. So is there a way we can rename this column to a proper column name? The answer is yes. We just need to put dot alias after count, and we'll put the column name as total department count. See, the column name is fixed now. Let's see one more example where we'll group the data based on department ID, and we'll find out the total salary as per the departments. Now we know we need to first import the sum from PySpark SQL functions. Let's write our sum data frame. We need to group by based on department ID. Now we can write our aggregation as .agg. We can call the sum function as sum, and we can put the column name, which is salary. Now we know we can alias the column using alias. Nice. We have total department salary based on department IDs. You can see the sum of salaries according to the department IDs. Now, there can be a condition where we need to put a having clause. What is having clause? It is based on the aggregation. So consider we find out the average salary for department using department ID as group I. But we are also checking that the average salary for the department should be greater than 50,000, which acts as a filter condition as well. So to do that, first we need to import the average from the PySpark SQL function. Let's write our EMP average data frame. We'll first do the group by based on department ID. Now we'll write aggregation as .agg, and we'll call the average function based on salary. Now we got our average salary. Let's rename that. Okay, now we have our average salary, but we need to also put a filter based on the average salary greater than 50,000. So to do that, we'll just write a filter condition. We'll put dot where. Now our new column that we have generated is average department salary. So we'll write average department salary greater than 50,000. Let's run this. Nice. If you see, now we have only 1, 2, 3, 4, 5, 6 departments, whereas we have total 7 departments. So one of the department might have an average salary less than 50,000. Time for bonus tip of the day. Now, if we know to do a union, we need the same columns with same data types, but the column sequence should also be same. Now, consider you have two data frames, EMP data 1 and EMP data 2 other, where you have same columns with same data types, but the column sequence is different. You see, the column sequence is different. You have second column as department ID, here it is salary. Now, is there a way to combine this type of data frames easily? Yes, Spark provides us with union by name, which helps us to join two data frames with jumbled sequence, but with the same name and same data type for columns. Let's write emp fixed equals to emp data 1 dot union by name, and we'll use the second data frame, which is emp data 2 other. Let's run this. Awesome. If you see, both the data frames are now combined and the data is properly organized as per the columns. Now, one more tip for today. Spark by default provide one count aggregation based on the data frame level. So consider you need to find the count of the total records for a data frame. You can directly write emp.count, and this will provide you the count of the total number of records in a data frame. I hope by now you would be confident enough to write basic transformations in PySpark data frame query. Today we are going to understand how we can get the unique or distinct data from a data frame. We are going to see window functions, and in the end we are going to get familiar with Databricks Community Cloud. If you are new and you have not seen our previous videos, I would recommend you to go back and watch our previous video first. Click the I button at the top to check out our playlist. I am in my Jupyter Lab environment. We are going to generate the Spark session object, and we are going to use the same employee data that we have been using in our previous session. Let's quickly run the cells. Great, we have our EMP data frame ready. This is the data in that employee data frame. All the columns in the employee data frame are string. To begin with, we'll first see how to get the unique data from a data frame. Now consider we need to get the unique data from a data frame. we would see distinct on the complete record set. In order to do that, let's write our EMP unique data frame. Now we need to write EMP dot distinct. If we run this, we get our data frame with unique data. Since we don't have any duplicates in our EMP data, the EMP unique and EMP data would be same. But you understand how can we get the distinct from a data frame. Now consider a case where we need to select distinct department IDs from the EMP data frame. To do that, we'll write our new data frame EMP department IDs. We'll select the department ID column. We'll write select, and in select we'll select the department ID column. Now we'll select the distinct of the department ID. Let's run this. As you can see, we have got the distinct department IDs from our EMP data frame. Now let's discuss about window functions. Window functions basically provide us aggregation over a window of data. Consider a case we need to find max salary over partition by department ID and order by salary descending. We'll put this in a new column called max salary. To do this, we need to import few things. The first is window function, the second is max, and the third is the descending function. Let's import those. Okay, we need to import window from PySpark SQL window module, and we need to import max, column, and descending from PySpark SQL functions. Now, first we need to write our window specification, which is partition by department ID and order by salary descending. Let's write our window specification. So we'll write window that we just imported dot partition by, our column is department ID, and we need to order by, column is salary dot descending. Our window specification is done. Let's write our max function. For that we will write max function is equals to max of our column, which is salary, dot over our window specification, which is window spec. Great. Now we have created our max function, which will have the max salary, and our window specification is also there. Let's write our new column max salary in emp1 data frame. We'll write emp1 is equals to emp dot with column. We'll create our new column called max salary, and we'll put the max function. Let's run our query. Great. If you see, for department ID 101, we have a max salary as 70,000, which is the max among all these three salaries. Similarly, if we check for department ID 103, we have a max salary of 62,000, which is the max among these four salaries. So our window function is working great. Let's do one more example. Consider we need to find the second highest salary of each department. For that, we will use the row number function over partition by department ID and order by salary descending. In the end, we'll put a filter of row number equals to 2. So we know we need to import window, row number, column, and descending first. Let's import our window function and other required functions. Great. Let's write our window specification, which is as same as that we did just now. Let's write that again. Dot partition by, which is our column department ID, dot order by, which is our column salary, dot descending. Okay, let's write our row number function. For that, we'll write rn equals to row number dot over our window specification. Great. Now our row number function and window specification is ready. Let's write our new column rn, then we'll put the filter rn equals to 2. For that, we'll write emp underscore 2 equals to emp dot with column. Our new column is rn, and put the rn function. Let's see the data first. Now, if you see for department ID 101, we have row number 123, where 70,000 is the highest and 45,000 is the least. So our row number is placed based on the descending salary for that particular department. Similarly, for 102, you can find we have 55,000 being highest and 48,000 being lowest, and we have row number 1234. Now, we need to find out the second highest salary, which is rn equals to 2. So to do that, we can just put the filter where rn equals to, let's run it now. Great. Now for each department, we have the second highest salary, and this solves our problem. Now, if you find window functions confusing, there is one more simple way to do it. That is using EXPR. Let's import that first. Okay, now we have already used EXPR a lot in our previous sessions. We know how to do it. Let's create our new column Rn using EXPR. For that, we will create a new data frame called EMP3 from EMP. Now our new column is Rn. We'll just put EXPR, and within this, we'll copy this whole window function. Great. If we run this now, you see, we have the same data frame ready. We just need to put the filter now in order to get the second hash salary. Let's do it. We put where Rn equals to 2. Now if we run it, great. Same solution. Now, in certain cases, if you find PySpark API is difficult, you can just write the SQL expressions within EXPR to get your work done. This is as simple as that. Okay, time for bonus step of the day. Today we are going to see Databricks Community Cloud as a bonus step. Now, in order to create a free account for Databricks Community Edition, you need to go to community.cloud.databricks.com and you can just sign up. Once you sign up, you will land in a homepage like this. Now, you have several tabs on the left-hand side. The important ones are Compute and Workspace. First, you need to create a Spark cluster for yourself. For that, you need to go to Compute and click on Create Compute. Once you are in this page, you can just type a cluster name and you can just click on Create Cluster. Once that is done, you will have a cluster like this up and running in few minutes. Now, Databricks will provide you a shared compute cluster with 15 GB of memory and 2 core. If you can see, the Apache Spark version is 3.3.0 and you also have Scala installed in this cluster. You need to go to Workspace and you have to create a notebook. Once you have a notebook created, you can just go ahead and type Spark and run it. If you can see the Spark session message, it means your Databricks notebook and your cluster is up and running. Now, Databricks provides us with Spark session by default. You can use this Spark session and start running your code immediately. So consider you need to create the employee data frame. You just have to copy this, paste it here, run it, and just go back, copy the create data frame command, run it. And now if you run emp.show, see, your EMP data frame is ready. So if you are not able to create a local environment in Docker, you can get started with Community Cloud Databricks right now. Today we are going to discuss a few more important topics, which are data repartitioning and joins in PySpark. Now, if you have not seen our previous video, I would recommend you to go back and watch our playlist. Click the I button at the top. I am in my Jupyter Lab environment. As usual, we will use the same employee data that we have been using in our previous sessions. As you can see, this is our employee data and we have employee schema where all the columns for the employee data frame are string. Other than this, today we will create a department data frame that we will be using for joining the datasets. For department, we have department ID, department name, city, country, and budget. All the columns for the department are also string. Now, to move forward, let's create our employee and department data frames and our Spark session. We'll run through the cells quickly. Okay, our cell execution is complete. This is our employee data set, and similarly, this is our department data set. If we see the schema, all the columns for employee and department are string. We will use department ID, which is the common column between employee and data frame, to join the datasets. But before that, we will see how Spark handles data repartitioning. We know Spark works on data partitions. To see the number of partitions for each data frame, we can just write emp.rdt.getNumPartitions. And if we run this, we have 8 partitions for our employee data frame. Similarly, we can see the data partitions for department. Okay, our department data is divided into 8 partitions. Now, what if we want to reduce or increase the number of data partitions as per our requirement? Spark provides us utilities such as Repartition or Coalesce to do that. Let's consider an example where we will create a new EMP partition data frame with 4 partitions. For that, we'll write EMP partitioned and we'll write emp dot. Now we have to reduce the number of partitions to 4. We can write repartition and we can put 4. If we run this, nothing happens. Let's see the number of partitions for emp partition. See, the number of partitions is reduced to 4. Now, can we increase the number of partition? The answer is yes. If we put the number of partition as 10 and if we run this, you see the number of partitions has increased to 10. Can we increase it to 100? The answer is yes. If we run this, the number of partitions for the data has increased to 100. Now, Spark has one more utility called Coalesce. The benefit of Coalesce is you can reduce the number of partitions without data shuffling, but you cannot increase the number of partitions for a data frame. So for our employee data frame, we had 8 number of partitions. Now, if we put Coalesce and if you run this, see the max number of partitions that you can get is 8 because Coalesce cannot increase the number of partitions. But what if we have to decrease? Consider we want to make it 4. See, we can decrease the number of partitions. The benefit is Coalesce will reduce the shuffling between the executors. Now, if you don't know what is executor, I would recommend you to go back and watch our playlist, how Spark works. What if we want to repartition the data based on a column? Consider we want to repartition the data into 4 partitions, but based on department ID. We can write, if we run this, see the number of partitions is 4, but this time the data is partitioned based on department ID. It implies same department ID will lie in the same partition. But there is one big demerit of repartition. Repartition will involve shuffling. It implies in order to make the desired partitions, the data would be moved across executors. Now, we are discussing this as theory. What if we want to see how the data is moved across partitions? To see the partitions information, we can import Spark partition ID from PySpark SQL function. Let's import that. Now, let's create a new data frame called emp1, which will give us the information about the partitions. To do that, we will write emp.withColumn to create a new column called partition number, and we will use the function Spark partition ID. If we run this, as you can see, we have partition number info. So the first 2 records are in the partition number 0. Similarly, we have the last 4 records in the 7th partition. But if you see, the same department ID is in different partitions. So here 102 department ID is in the first partition, and again the 102 department ID is in the 3rd partition. So in this case, we can repartition the data to bring in all the similar department IDs into the same partition. Let's do that. Let's put emp.repartition, and we'll put 4, and we'll do the department ID partitioning. You see, all 102 department ID is in the first 0 partition, and similarly 107 is also in the 0 partition. Now in this case, you can see all 102 is in the 0 partition. There is no 102 department ID in different partition. So we have segregated department IDs in the similar partition. Now you might be thinking, why are we doing this? There is a huge optimization benefit when we repartition the data properly. We will see this when we discuss the advanced optimization techniques in PySpark. For now, you just need to know to repartition the data, we can use repartition or Coalesce accordingly. Let's discuss about joins. We know join plays a very crucial role in SQL to join 2 datasets. So to understand join in PySpark, let's use this example. We have a SQL query where we will join employee and department as inner join. Based on the condition employee.department ID is equals to department.department ID, and we will select few of the columns from each of the datasets. To do that, we first need to write emp dot, we need to join, we'll write join, and we have to join with department. We'll write DEPT, which is our department data frame. Now, how are we going to join? So the how is equals to inner, and we are going to join on condition, which is emp dot department ID, and we have to put a equality condition, which is double equals to, and we have to put department dot department. This concludes our join. If we run this, here is the joint data frame. You can see all the columns from both the data frames, but we need to select few of the columns. We don't need to select all the columns. So we can write dot select emp dot emp name. See, we have the joint data frame with the department name column, the department ID, name of the employee, and the salary. Now, if you have seen here, we have done aliasing. We have used emp and dept dot. The reason is because we have a department ID column which is ambiguous, which is in both the sides, emp and department. So to do aliasing, you can write the data frame dot department ID. But consider your data frame name is big and you want to short it down. You can put dot alias during the join condition, where you can put E for employee, and for department you can write alias, which is D. In that case, we can write E dot name, D dot department, D dot department, and E dot salary. Now you see, we get the same output, but this time the aliasing happened on the alias. But if you're doing an alias, you need to put in double quotes because this is a column name now. We did an inner join in our first example. What if we need to do left outer join? The example remains same. We need to use the same column names, but this time in place of inner, we'll do the left outer join. Let's copy the same query. But now in place of inner, we will write left outer. And if we run this, same solution. But we need to select the columns. So we'll put dot select. I think now you can understand how we can do the joins very effectively in PySpark. Time for bonus tip of the day. Now, we have seen joining conditions which are pretty simple, but we know we might have certain cascading join conditions such as and, or, and we have to also put conditions such as not null, null. To do that, we will see how we can write such cascading joining conditions effectively in PySpark. Consider we will do a left join between EMP and department data frames, but we will do it based on department ID and only for departments 101 and 102. Let's write our final data frame. We'll write emp dot join. Our joining condition is with department, and we are joining as left outer. Now, our on condition is very important. We have to join based on department ID and also based on departments 101 and 102. So we will write on equals to. Now, for each cascading, you have to open and close brackets. So our first condition is based on department ID. So we'll write emp dot equals to equals to. Now, our second condition is and emp dot equals to 101. And our department can be 102. So we can write one more condition. But for cascading, we need to make this in bracket. So we'll make this in bracket. Then we'll write our or condition, which is or, and we'll again write in bracket, which is our second condition, which is department ID is equals to 102. Now let's run this. Great. If you see now our joining condition is only based on department IDs 101 and 102. For all other department IDs such as 103, the values for the join condition is null. Now, what if we need to put not null conditions? For that, we can write one more and condition, which is and. We can open and close bracket. We can write emp dot salary dot. For conditions like null and not null, Spark provides us utility like is not null and is null. You can write is not null and you can run this. We'll have the same output because all our salaries are populated. There is no null salary. Now, if you put it as null, you see all the conditions has been removed. Everything is null because we don't have a null salary. This is why the joining is not happening. I hope you understand how we can write the cascading joins in PySpark effectively now. It is very important to remember that for each of the cascading join, you have to include them in brackets. And for an and condition, you need to use and percentage. And for an or condition, you need to use a vertical pipe. Till today, we covered a lot of basics. From now onwards, we will deep dive into Spark. Today, we will see how to read CSV files. Reading CSV files is not so important. The importance is we will understand how Spark works in the background with the help of Spark UI. We will also see how to handle bad records, and we will understand the read modes available with Spark, which are permissive, drop malform, and fail fast. Now, I am in my Jupyter Lab environment. As usual, we will start by generating our Spark session. Let's run the cells. Okay, our Spark session is generated. Now, let's check our Spark UI. Our Spark UI is present in port number 4040. Let's refresh our localhost 4040. Awesome. Our Spark UI is up and live. You can see there are multiple tabs in the top of the Spark UI. We'll try to explore majority of them today when we run through our code. Let's go back to our Jupyter Lab environment. Now, I have two CSV files available with me, the emp new.csv and emp CSV. Let's open the emp CSV file. As you can see, we have multiple columns in this file, which includes employee ID, department ID, name, age, gender, salary, and hire date. So we'll try to read first the emp CSV file. To read a CSV file into a data frame, let's write our code. We will name the data frame as df. To read a file, you need to write it as spark dot read dot. Now we will put the format as CSV. So we'll write format which is CSV. And to load the file, we will write dot load, and we will give the location of the file, which is dataset data slash input slash emp.csv. Now, before I run this command, we know this is a transformation. We know the difference between a transformation and an action. The actions are something which creates a job in Spark, but reading the data is not an action. So if I trigger this code, nothing should happen, right? Let me trigger this one. Okay, this code successfully run. Let's go back to our Spark UI and refresh our job tab. Wait, what? Spark created a job. But why? Let's go back to our Jupyter lab and see what are the columns that Spark read. We'll put df.print schema. Okay, Spark identifies 7 columns. So we can understand the job which was triggered was to identify the metadata. Let's go into the job. You can see there is only one stage. Now, if we expand that stage, we can see there is only one task that is executed. And the task read only one record. This is what Spark did proactively to identify the metadata. Because Spark cannot optimize the read or the functions what you're going to write later if it is not able to identify the metadata. This is why Spark proactively ran one job just to identify the metadata. Okay. Now we have only one job here. Let's go back and try to see. Spark identified the metadata, but not the headers. Now, how do we ask Spark to read the headers? To do that, we will ask Spark to use option, which is header. We'll put it as true. Now, if we run this, again go back and refresh. Okay, only one job. If we go into the job, one stage. And if we go into the stage, only one task. Again, one record. Now, if we go back and refresh our print schema, awesome. Spark read all the 7 columns and again the column names as well. Now, if you see the column data types, everything is string. Now, if you want to get the data type from the data itself, so Spark will do that for you as well. So we'll put one more option, which is infer schema. We'll put it as true. Now, what this infer schema does is it asks Spark to go back and look into some of the records of that file and identify the data type for each of the column. So if we run this now, we go back to our job tab and we refresh. You see, now there are 2 jobs created. Okay, why 2 now? If we go to the first job, if we expand the stage and we go into the task, we see Spark only read the first record. Spark read this record to identify the headers. Now, if we go back to the job and see the second job, we see there is only one stage. And again, if we expand, you see Spark has read 21 records. Now, this is what Spark did to identify the schema. So if we go back and refresh our print schema command now, we see Spark has identified the schema correctly. It has put the employee ID as integer, department as integer, name as string, and again, that hire date as timestamp. So we understand what is happening in the background. Spark UI gives us a lot of information about it. So if you see, it gives us the information about the number of tasks launched, how many stages are there, and how many jobs. If you remember our previous video where we discussed how Spark divides a particular job into stages, and a stage will contain tasks which will be executed in parallel in multiple executors. Now, if we run our action, say df.show, Spark will create one more job. Let's go back and refresh our job tab. Job number 4 has been created as source string because Spark has already identified the metadata in job 2 and 3, and now it is performing the action in job number 4. If we expand this, we see there is only one stage, and we expand the stage, we see there is only one task created, and it has read 20 records because one record is header and 20 is data. Let's go back. Consider a case if we have a schema. What will happen in that case? So we know Spark proactively goes and reads the metadata. But if the schema is specified, Spark does not need to go and look into the file. Here is the schema for that file. So we can see the columns employee ID, department ID with the correct data type as integer, gender as string, salary as double, hire data as date. Now let's read the data frame again, but this time using schema. We'll name the data frame as data frame schema, and we'll put at spark.read.format, which is for our file, which is CSV. And this time we will mention schema as underscore schema, which is our schema string, and we will put load as the file path, which is the data slash input slash emp.csv. Now, before I run that, let's see the job tab. We have only 4 jobs here, right? Let me run this. Let's go back and refresh our job tab, nothing. Because this time Spark does not need to go into the file and look for the metadata. We have already supplied this. This is why it is important in production to specify the schema of the file that you are reading. This will help Spark to optimize the code. Else, Spark has to identify the header, read the file to identify the data type, which might cause problem while reading files which is coming from different sources. Let's run an action now, which is show. Awesome. But we see the first row as null. Why is it null? Because our file has a header, but we have not specified it. Let's put it as an option, which is header, and we'll put it as true. And now if we run this, again, if we go and refresh, this is because the source string that happened right now. If we run the source string again, awesome. Now we are able to identify the header, and we have all 20 records displayed. If we go back and refresh, we get one more job, which is 6, which is the source string. So Spark only launched one job here, not multiple. This is because Spark already knows the metadata through the schema. Now, before we jump into different discussions, let's see what are the options that are available with Spark read. So if we go into the CSV file for the Spark documentation, you can see a lot of options which are available, which includes the separator, which is comma by default for a CSV file. But if you have a different delimiter, for example, a vertical pipe, you can specify that option using SCP. Again, you can specify the code header as false, which is by default, but we are specifying as true because we want Spark to identify the header. Again, if you see the info schema is false. Similarly, there are a lot of options available here. You can look into these options, but the most important here is the mode. Mode is very much useful to handle bad records. When I say bad records, it means the records which does not confine your schema. We need to specify schema in order to use mode. You cannot use mode using info schema. You need to apply schema while using mode. The default mode which Spark provides for reading CSV file is permissive. There are two more modes available, which are drop, malformed, and fail fast. We'll see all three one by one now. Now, the first mode, which is the default one, is the permissive. Permissive means it will allow Spark to put the error record or the bad record into a different column, which is the default column that Spark uses is underscore corrupt record. Now you can specify that corrupt record column in the schema to see the data which is bad. So I have a different file called emp new, which has some bad records. Now if you see the salary column, which is a double column, I have a string called low here. Again, for higher date, I have a data which says no date in place of a correct date. We'll read this file and we will see how Spark behaves with different mode. So we will see how the permissive works. Before we do that, let's bring our schema, which is now let's write our data frame, which is data frame. I'll put it as P, which is permissive. We'll write Spark dot read dot format, which is CSV, and we will force the schema, which is schema, and we will write it as underscore schema. Now we will put option. First is the header, which is option. Since our file has the header, we'll write header, and which is true. Now we will load the file, which is data slash input. Now we'll read the emp new CSV file. Let's see the schema first. We'll write dap.print schema. Awesome, it read our schema, right? Now if I go and see the data, so I'll write df underscore p dot show. Nice, but if you see now, it has not rejected the records. Rather, it has put null for the corrupt values. If you remember, it was low for the salary and there was no date for the higher date. So it has put as null. Now, how do we identify which all records are corrupt? For example, the record number 11 and the record number 7 are corrupt because we have corrupt data for salary and date. So to do that, Spark provides a metadata column, which is corrupt record, and the data type is string. Now, this column is an inbuilt column that Spark provides for the corrupt data in permissive mode. Let's run the cells. We have the column which holds the corrupt record here. Let's run the show. Now, if you see this, for the corrupt data, we have corrupt record populated. But for all other records, we have the value as null. So you know which all records are corrupt. In case you want to filter out the record, you just need to put where corrupt underscore corrupt record is not null. This is to find out all the records which are corrupt. If we run this, we get 2 records. Now, if we put it as null, we get all the records which are correct. So, is it mandatory to put the column name as corrupt record? No. Spark provides you with an option to handle the corrupt record column, which is called column name of the corrupt record. You can specify this in the option and change the column name. Let's do this. I'll copy this option. I'll go back to my code and I'll just change and I'll just put option. I'll name the column as bed record. And I'll similarly change my schema as bad record. Let's run this. Our schema has the bed record column now. Let's run this. I'll remove this filter condition and run this so. Now you see the column name has changed to bad record. This is how we can use the permissive mode in order to work with our files without failing. Now there are two more modes available. The first is drop malform. We can write df_m. This is for our drop malform. We'll use spark.read.format and we see the schema first. This is again the 7 columns that we have in the file. Let's see the data. Okay, we have the corrupt records here. You can see the null values in salary and hire date. Let's specify the mode. To do that, we'll write option and we'll put mode as drop malformed and we'll rerun this. Nothing is changed in the print schema. Let's run the so now. If you see, we don't have the record number 7 here and the record number 11 here because drop malform drop the records which are malformed, which are bad records. So in case you want to drop the records which are bad records, you can use the drop malform as the mode. Now, what is fail first? Now, if you have seen in both the cases, our job ran fine. We were able to see the data. Our job did not fail. So we can specify one more mode, which fails the data if our data does not confine with our schema. Let's put our schema here. We'll copy this from the top. It's the same schema that we are going to use, but this time the mode is going to fail fast. Now, if we run this, nothing happens. Let's see the schema. Okay, same schema. Let's view the data. We'll write df_m dot show. Now we know whenever we trigger the action, it actually creates the job and Spark basically does the lazy evaluation. Let's run this. You see, now this time it has failed because fail fast ensures if the data does not confine with the schema, it will fail the job. So we have seen 3 modes. First is the permissive, which is the default mode. For permissive, you don't need to specify the option mode as permission. It is by default. The second one is the drop malform, which basically drops the record. And the third one is the fail fast. It fails the job as soon as a bad record is hit. Now, you can find out the use cases in a production scenario. In case you want to filter out the bad records into a different file, you can use the permissive mode. In case you want to drop the bad records, you can use the drop malform. In case you want to fail your job, consider there is payment data coming in. Payment data is very much important. You cannot drop the record or you cannot do your analysis with few of the records, filtering out the bad record. It's not wise. In that case, you can use fail fast to fail your job immediately as soon as a bad record is hit. Time for the bonus step. Now, if you have seen, we are writing options again and again. What if we have to write multiple options? There is one more option available, which is you write a dictionary as underscore options, putting all the options that is necessary. So consider we want to use the header as true, we want to infer the schema as true, and we have specified the mode as permissive. Now, in this case, if we want to read the data frame, we can use the options method and we can expand our dictionary to be used for all the options available. Let's run this. If we run this so, you see the data is printed correctly. In our last video, we saw how to read CSV files. Now, CSV files are plain text data files. It implies you can open a file and see the data inside that file. But there are certain complex data format files like Parquet, ORC, or Avro, which you cannot open and see the data. Today, we will understand how to read those files in Spark. We will understand what is the difference between a row and a columnar data storage format. We'll also see the benefits of Parquet columnar data format. Let's begin. Now, before we start writing our code in PySpark, let's understand what is a row and a columnar data format. Consider we have a table where we have 3 columns, employee ID, employee name, and salary. We have 3 records. As you can see in the table, we have 3 employees, Dexter, Tom, and Jerry, and their salary and their employee ID. Now, whenever we store the data in row format, the data is stored in the fashion where we have the record stored all together. For example, if you can see the highlighted one is the first row, and this one is the second row, and this one is the third row. This is how a data is stored in a row format. But in columnar format, the storage is different. In a columnar format, all the data of a particular column is stored together. So you can see the highlighted one is all the employee IDs stored together, similarly the name, and similarly the salary. Now, what is the benefit of having a columnar format over a row format? So consider a case you want to do some aggregation based on salary. If we have to access the data in a row format, the system has to go and read all the records in order to find out the salary from each of the record, which is 500, 600 and 1000. But in a columnar format, the system has just to read the last column, which is having all the data all together. So it can skip all other columns to read. This is how only reading the required column in data analysis can provide you a lot of benefit when you have a storage format which is columnar. Now, this is just a simple representation to make you understand how the row and columnar data format stores the data. Actual implementation logic can be more complex than this. Now, there are many complex file data formats available, but the three popular ones are Parquet, ORC, and Avro. On my screen is a detailed comparison how you can see the different file formats along with the properties on the left hand side. You can pause the video and have a look and understand what is the difference between Parquet, ORC, and Avro. But I'll just give you one small example of use. In case of Spark and Delta Lake, we prefer to use Parquet. Even Parquet is the default file format for Spark. With the introduction of Hive, ORC was popularized. ORC was the famous file format that being used for Hive. And similarly, for Kafka, we use Avro. Now, one thing that is important for all these three file formats is all these three file formats saves the metadata, which is the schema, along with the data in the files. Now, the underlying process of doing it is a bit more complex, but you can look up on internet to understand how these three file formats handles the same. The most popular one that are being used in data analytics are Parquet and ORC. In majority of our course, we will deal with Parquet files. Avro has its own benefit when it comes to schema evolution and streaming data. For now, we will keep ourselves busy with only these two file formats, which are Parquet and ORC. I am in my Jupyter Lab environment. Now, I have the ORC and Parquet data in my input folder. You can see the sales data for ORC and the sales data stored as a Parquet file. We will go ahead and generate our Spark session and start reading this data. Our Spark session is up and live. Let's go ahead and read our Parquet data. We will create a data frame df_Parquet. To read a Parquet file, we will follow the same format that we did for CSV file. We'll write spark.read.format. Now we will specify format as Parquet. And we will write load and we'll put the data location, which is data/input/sales data.Parquet. Let me run this. As you can see, it has correctly determined the column name and the data types from the file itself, because Parquet stores the metadata along with the data. Now, let's view the data. Nice. We can see all the columns printed along with the data. Let's go ahead and read our first ORC file. We'll write the data frame as df_ORC and we'll write the same code, but we'll use the format as ORC. Awesome. We can see the column names and the data printed properly. Now, it is a case where we have a single file as Parquet and single file as ORC, but that is not the case always. You can have a folder where you will have multiple Parquet files stored in it. You can see on the left, we have a sales total Parquet folder where we have around 8 Parquet files stored in it. Now, in order to read all the files under this folder, we just have to change the name to the folder name. So we will remove the sales data.Parquet. We will write sales total Parquet. Now, if you only want to read Parquet files, you just put star.Parquet. We run it, same schema and column names. We run the show command. We get the data properly. Same thing for ORC. We want to read the data for the sales total ORC. We just need to change it to the folder name. We'll put at sales and we'll put star.orc to read the ORC files into that folder. As you can see, we have the same column names and the data stored properly. Again, if you want to specify options that we did for CSV files, you can do it. You can just specify dot option and you can specify the required option. Now, the list of options for Parquet and ORC are available in documentations. You can go into the Parquet documentation and you can see the available options here. So for example, the compression. The default compression for Parquet is snappy. Similarly for ORC, the default compression is also snappy. You can have a look in the ORC files as well. Now, we know both ORC and Parquet are columnar data format. We will consider this example for Parquet. So, if in a columnar data format, you read only the required columns, you have a benefit. Let's see that. Here's a Python decorator that I have written to find out the execution timings of a function. We will write two functions. In the first, we will read all the columns from a Parquet file. And in the second one, we will read only the required columns and we will see the difference. Now, if you don't know what's a Python decorator, you can go out and check the documentation in internet. Let's write our first function to find out the timing when we read all the columns from a Parquet file. First, we will write the decorator, which is the get time. Then we will write our function, which is def x, and we will read the data frame, which is park.read.format, which is our Parquet, and we will load the same sales Parquet file. So we'll write data/input/sales.parquet. Now we will just make a count. So we'll write df.count. Let's execute the cells. We will first run the decorator and then we will run our function to find out the timing. Okay, took 672 milliseconds. Let's write the same code now, but we will only select the transaction ID column. So we will put df.select and we'll put the transaction ID column. And we'll run this again. Do you see the difference? It's almost the half time. This is how the benefit is. In a columnar data format, if you read only the required columns for your data analysis, you have a benefit. This is why the columnar data format is so popular for data analysis. Time for bonus tip. Consider a case where you have to read the data recursively. For example, you have two Parquet files, Parquet1 and Parquet2, but those are in some recursive data folders. For example, first it is in sales recursive data folder, then under this it has a sales1 folder, and the second Parquet file is under the sales2 folder, which is again under the sales1 folder, which is under the sales recursive folder. I know this sounds confusing. Let's see this. So we have the sales recursive folder. If we expand this, we have sales1 and we have the first Parquet file here. But our second file is again inside a sales2 folder, which is there. Now we know we can read the files individually. Let's do it. Let's run the df1, which is park df_1.show for this file. I can see there's only one record. Let's see the second file. I'll copy the same command, but I'll put sales2 folder here and I'll change it to 2.parquet and I'll run this. Again, you see there is one more transaction ID here. So collectively, these two Parquet files contain two data records. Now, if we want to read it together, we can use one option, recursive file lookup. So I'll copy the same command, but I will read the top folder. I'll not go inside that folder. I'll read the sales recursive folder and I'll put one more option here. I'll put option and I'll write recursive file lookup and I'll put it as true. This instructs Spark to go inside the folders and look for the files recursively. Let's run this. You see, we have collectively read both Parquet files. Till today, we have seen how to read CSV files and complex data files. Today, we are going to read JSON files in Spillage. We are also going to parse complex JSON structures. We are going to look into some important JSON functions such as toJSON, fromJSON, and we are also going to explore array data. We are going to look how to write JSON schema easily just by looking at the data. Now, if you have made till this far and you are liking my content, thank you very much. If you wish to buy me a coffee, here is a QR code from PayPal that you can scan. Thank you. Let's move on. I am in my JupyterLab environment. But before we can begin, you must know what is array or list data type or what is a struct or map data type in Python. If you're unsure of this, I'll recommend you to go back and refresh your Python skills. Here is the data with which we are going to work today. We have two JSON files. One is a multi-line JSON file and another is a single line JSON file. Here is the JSON data with which we are going to work today. This JSON data is spread over multiple lines. If you can see, it started from line number 1 and it ended on line number 17. It implies it's a multi-line JSON. Now, what do we have in the data? We have order ID, customer ID, order line items, which is actually the line item of the items. You can see we have two items. The first one is item ID I001, which has a quantity of 6 and the total amount is 102.45. Similarly, we have another item with item ID I003, which has a quantity of 2 and amount of 2.01. We have a contact field, which is again an array field, which is also a list in Python. We have two contacts for this customer who has this order. So this is a multi-line JSON. We can have the same JSON spread in a single line. You can see in this, we have one line item which contains the whole JSON payload. Now you understand what is the content for both the files. Okay, now to start with, let's generate our Spark session. Here is our Spark session ready. Let's go ahead and read the single line JSON first. So We know to read a file, we just need to create a data frame with read and we have to specify the format. Let's do that. We'll create a data frame df underscore single line, which will be spark dot read dot, will specify the format as JSON, and we will load the file which is inside data input order and we'll load the single line JSON. Let's run this. Okay, now let's see the schema. We'll type df single dot print schema. If we run this, awesome. You can see Spark has automatically identified the JSON schema. Now, it has identified contact as array field, which contains elements which are long. Now, our phone number is identified as long. Customer ID is identified as string. Similarly, order ID as string. And now we have the order line items, which is again an array, which contains elements which are struct, which is also known as dictionary, or the JSON payloads, which contains amount, which is a double, item ID, which is a string, and quantity, which is a long. Now, we can see the schema properly. Let's see the data. Great. We can see the contact, which is an array field here. We can see the customer ID, which is C001, order ID O101, and order line items. But you can see the order line items are identified but not expanded. We'll see how to expand this JSON in few moments. Before that, let's read a multi-line JSON file. So to read the multi-line JSON file, we'll create a data frame df underscore multi, and we'll again read at spark.read.format, and we'll put the format as JSON, and we will load the file data input order multi-line. But Spark out of the box does not support multi-line JSON file load. So to do that, we have to specify an option, which is option multi-line, which is true. Let's run this. Let's see the schema. Nice. It is the same schema that Spark has identified. Let's view the data. Great. We can see the same content. Now, we have seen in both the cases, Spark has automatically identified the schema and expanded the values for us. It has distinguished contact, customer ID, and order line items. But consider a case we don't want to expand the data and keep it in a single column. How can we do that? Let's read the single line file and we will try to keep it in a single column named value. We'll create a data frame df equals to spark.read.format, which we will specify as text, and we will load the single line file, which is data input order single line. Let's run this. Let's view the schema. Nice. You can see it created only one column. Let's view the data of that column. We'll put df.show. Great. You can see it has kept the raw data as is. You can expand this so to view the data. Let's do it. We'll write truncate and put it as false. Nice. You can see the whole JSON payload is kept into the same column, which is value. Okay. Till now we have seen that whenever we read the JSON data, Spark automatically identifies the schema. What if we have to enforce one schema to this particular payload? Consider we only want to read order ID, the customer ID, and the contact. Can we force this schema on top of this payload? The answer is yes. Let's do that. Let's write our schema, which is schema, and we'll put it as customer ID, which is string, we'll put the order ID, which is also string, and we'll put the contact, which is actually an array field, and we'll specify it as long. Let's read the data frame again. We'll put it as df schema, and we'll do it as spark.read.format. We'll specify it as JSON, and we'll specify the schema this time. We'll put it as schema, and we'll load the multi-line file. So we'll put data input order single line. We'll read the single line file. So we'll run this. Let's view the data. So we'll write df underscore schema dot show. Now you see we have just read only the 3 required columns from this particular payload. So if required, you can enforce a schema. What if we want to write a complex schema? You can also do that. So for this schema, whatever we found in the multi-line, let's write our complex schema. So I'll paste this here just to view the cell, and we'll write our schema. So we'll put it as schema, and we will write our schema. We'll copy this contact, which is an array field. So we'll write array. Now the element for each array is long. So we'll put it as long for the array. Now our next element is customer ID, which is again a string. Our next column is order ID. We'll put it as string. And our next item is the order line items, which is again an array. For this, we have to put this triangular bracket, and inside this, each element is struct. So we'll write the elements for this array as struct. And for each struct, we have three values. The first one is amount, which is double, followed by item ID, which is string, and quantity, which is long. This is our whole schema. Let's again read the data frame with this schema now. So I'll put df schema new, and we'll write as spark.read.format. We'll put the format as JSON, and we'll enforce the schema. Let's make some changes. We'll specify the contact, which is array of long, as string. So our phone numbers are string now. Let's specify this. So we'll put a schema, and we will load the single line file again. We'll data input order single line. Let's run the schema first. Okay, we forgot to put the double quotes. Let's put the double quotes and rerun this. And now let's run our data frame. Let's view the data frame schema. So we'll put data frame schema.new.print schema. Awesome. You can see this is an array of string now. Let's view the data. So we'll put df schema new.show. Nice. You can see the same data printed, but this time our contact is string in place of long because we enforced a schema as of our choice. This is how you can specify a complex schema using simple string statements, just like we do for our normal DDL. Now, Spark has provided us with some important functions related to JSON that we can use. First, we will see the from JSON. The from JSON is basically used to parse a JSON payload that is stored in a column. But we also need to specify the schema for that particular payload. We have already created that schema. So let's copy the schema. Nice. Let's import the from JSON function from PySpark SQL functions model. So I'll do it from PySpark. Great. If you remember, we already have a data frame which contains the whole payload in a single column. So I'll just show you that. So I'll write df.show. You can see we have the whole JSON payload in the value column for the data frame df. We will expand this one with the schema. Let's do that. So I'll write df expanded. We'll use df dot, we'll create a new column called with column. I'll write it as parsed, and I'll use from JSON, and I'll put the column which is df dot value, and I'll pass in the schema which is schema. If I run this, nothing happens. Let's view the schema. I'll write df underscore expanded. Nice. If you can see, the parsed column contains our parsed JSON data. Let's view the data. So I'll just type df expanded dot show. Nice. Our parsed column contains the parsed JSON payload from this value column. We'll expand this in few moments. Before that, we will see one more function, which is toJSON. toJSON is used to convert a parsed JSON data into a string JSON data. So to do that, we'll write a data frame called df unparsed, and we'll again read parsed JSON data. So our expanded data frame contains a column which is parsed. So we'll use that column to unparse the data. So we'll put it expanded dot with column. We'll put the column name as unparsed, and we will write as toJSON, and we'll put the column name from the expanded, which is parsed. So I'll put as df.n.parsed. Now, before we can do that, we have to import the toJSON. Let's do that. Let's run this cell now. Let's view the structure. So I'll put as df unparsed dot print schema. Great. We have one new column called unparsed, which is actually a string column. Let's view the data for that particular column only. I'll just write df.unparsed.select. Great. You can see that JSON payload. Let's truncate. Let's switch off the truncate. Put it as false. Great. You can see the whole payload as unparsed. So now you understand the use of from JSON and toJSON. If you want to parse a data from a particular column using a schema, we need to use from JSON. But if you want to do the opposite, if you have a parsed data and you want to convert it into a string, you will need to use toJSON. Now, we have already parsed the data, but we have not expanded or exploded the data. When I say expanded, it means extracted the value for each of the columns, or we have not exploded the data, means we have not expanded the array fits. Let's do that. So we already have a parsed JSON data frame. So we'll use that df expanded. I'll show the data first. So I'll do as so. We have a parsed column. Let's view that column. So to do that, what I'll do is I'll write one data frame called df1. I'll use this expanded data frame. So what I'll do is to view the columns, we know we have multiple columns in this. So what I'll do is I'll write select parsed dot star. This star will expand all the columns which are present in this parsed as a struct data. Let's run this. We can see the data now. I'll write df underscore one dot show. Nice. You can see we have expanded the columns customer ID, order line items. Now we need to expand this order line item as well. And within this order line item, we know we have amount, item ID, and quantity. But before that, this order line item is an array which contains structs. Now we first need to explode this array. So to do that, we'll write another data frame df2, and we'll do it from the df1. So we'll say df1 dot, we'll write with column, and we will say expanded line items, and to do that we'll write explode, which is our column which is order line items. Now before we can run this, we need to import explode. Let's do that. Let's run this now. Let's view the data. I'll write df2 dot show. Great, you can see two lines now. If you remember, our order line items contain two order lines, the item ID I001 and I003. So the explode has exploded that particular array column into two records. Now let's expand line items which contains amount, item ID, and quantity. To do that, I'll again write a data frame called df3, and I'll expand this. So I'll write df2 dot select. Now we have to select all the columns. So I'll put contact. We will use the expanded line items. So we'll put expanded line items dot star. If we run this, nothing happens. Let's see the values. I'll write df dot show. Nice. You see that particular column is expanded. What if you need to expand only one single column? Say, for example, I just need to extract item ID. So we can just do that by writing item ID in place of star. If I run this, you see only item ID is extracted. What if you need to extract the quantity? You just put QTY and you run this. You see you extracted only the quantity field. So in a particular struct, you can use dot notation in order to extract a particular field, or you can put a star in order to extract all the fields. Now we still have the contact as an array. We need to explode that as well, right? Let's do that. We'll write our final data frame, which is df final. We'll write as d3 dot. We'll write one column called with column, and we will put that as contact expanded. And we will again use that explode because it's an array field. We'll put the column name, which is contact. And let's run this. Let's view the schema first. I'll write df final dot print schema. Nice. You can see the particular contact column is still an array field, right? But we have expanded that to contact expanded. Now, before I write the show command, what do you expect? What will be the number of records now? Pause the video and try to guess. Now, if you have guessed the number as 4, you are right. Each record for this particular contact will be exploded into 2. Let's view the data. We'll df final dot show. See, we have 4 records. These are the expanded or the exploded data. We still have the contact column. We can drop it. We can write dot drop, and we can put the contact column name, and we can again run. This is our expanded data, or you can say the flattened data. This is how we also expand or flatten a JSON payload or a complex JSON structure. I know this is too much to learn, but practice can help you to understand this concept very easily. Pause the video and try to understand wherever you are finding the things complex. Today we will see how to write data in Spark. We will look under the hood to understand how Spark writes data. We will also have a look within the Spark UI to understand the same. We will see what are the write modes available, and we will also see how writing data with partition works in Spark. Before we can jump in and write our code, let's understand how Spark works under the hood while writing the data. Now, to illustrate how writing works in Spark, let's consider we have a file layer which is marked in blue, and we also have a cluster which is marked in yellow. In our cluster, we have 2 executors marked in green. So you can see the executor 1 and executor 2. Each executor has 2 cores. So we have marked the core in red, which is 0 and 1 respectively for both the executors. Now, we know that Spark reads the input files in partition. So consider we have an input file. Now, for that input file, Spark creates 4 partitions, which are marked as 0, 1, 2, and 3. So the partition 0 would be processed by the first task, and similarly other partitions by the other tasks. So let's consider this partition would go to this core, this partition would go to this core. Similarly, the fourth partition would go to this core. And once the data is processed parallelly by all of the 4 cores, they will write the data back into the file layer. So consider the first task will write a file, which is a single file, which will be the part 0. Similarly, the second would write part 1, and part 2, and part 3. So each of the file would be for individual partitions that has been processed. So if you consider you are writing a file called emp.csv, then a folder would be created called emp.csv, under which we will have 4 files, because there are 4 tasks which are executed for 4 partitions. So for each partitions there will be 1 file. So 4 files will be created: part 0, part 1, part 2, and part 3. I hope you understand how this writing of data works. Let's understand with an example now. I am in my Jupyter 11 Power. Now we know how Spark writes the data. Let's run our Spark session to proceed forward. Now, before we proceed forward, let's see the number of available cores with Spark. So to do that, I'll write spark.sparkContext.default parallelism. So in my machine, I have 8 cores. Right now, I'm running the Spark session in local. So 8 tasks can be launched in parallel in my machine. Let's go back to our Spark UI and refresh the screen. Okay, here is our Spark UI. If we go to the Executors tab now, you can see I have only one executor, which is the driver. Since I'm running the Spark session in my local machine, which only have one executor, which is the driver, but the total number of cores that is available for that executor is 8. So right now our setting is one executor with 8 cores. You can also find the total number of cores here, which says total. Now, if we have more than one executors available, you can see the total number of cores here. You'll see all the executors listed in this page, along with the number of cores and the memory and other informations that is available. Let's go back. Okay, now this is the same employee data that we used to use previously. I'll use the same employee data today. So this is our employee data, and this is the schema of that data. So we have employee ID, department ID, names, age, string, gender, and hire date. Let me run this. Let's create our employee data frame. Okay, the data frame is created. Let's view the number of partitions that is available for the data frame. So to do that, I will write emp.rdd.get num partitions. If I run this, the number of partitions that Spark used is 8. Let's view the data as well. So I'll write emp.show. Okay, this is the data that we have. Now, to write the data, we will use the write method that is available with Spark. So consider we are writing the emp data. To do that, I'll write emp.write. Now, we need to specify the format in which we need to write the data. Consider we will be writing the data in Parquet. So I'll write format and I'll put Parquet. Now, to save the data at a particular location, we need to write save, and we need to provide the location. So consider we are writing it at data output. I'll put it as 11. I'll put it as 2, and I'll write the Parquet file as emp.parquet. Now, if I run this, okay, now we know that writing of data is an action. So if we go back and refresh our jobs tab, you'll see save. This is where Spark has used all the 8 tasks. Since we had 8 partitions, all 8 partitions are executed within 8 tasks by the 8 cores. So if you see, you have informations of the number of records read by each of the task ID. So all 8 tasks are executed in 8 cores in parallel. Okay, so you can see the number of records mentioned here and the size of the data that is available. So if we go back and open that location, which is data output 11 and then 2, and if you see, we have an emp.parquet folder. Now, if you remember, just now I have explained that whenever we put the name of the location, it creates a folder. So it has created a folder called emp.parquet. Now, if I expand this, since we have 8 partitions processed by 8 tasks, you see there are 8 files created. Now, if you see part 000, which is the first partition data, similarly 1, 2, 3, 4 up till 7. So we have 8 partitions and we have the data for 8 partitions in 8 files. Now, to understand this better, let's view the data in the partition. So we know to view the partition information, we need to import Spark partition ID. Let's do that. Now, to view the partition ID, I'll just write with a column, I'll write emp dot with column. I'll create a column called partition ID, and I'll call the Spark partition ID function here. And I'll just write show because I just need to see the data which is available in which partition. So I'll run this. Awesome. There are different employees in different partition. The partition ID is mentioned on the partition ID column. Let's write this data again back using in the format of CSV. So to do that, I will again write the EMP data. So I'll write EMP dot write dot format, and I'll put CSV as the format. And to specify the header in the file, I'll put option, which will be header as true. This will ask Spark to put header in the file. Now again, I'll write it as data output. This time I'll write in 11.3 and I'll name it as emp.csv. Now let me run this. Okay, let's go back to 11, and in 3 we know there's a emp.csv folder. If you see, we have 8 CSV files. Now let's view. We have employee 001 and 002 in partition ID 0. Let me open the first file. If you see, we have employee 001 and 002 in this first file. So this file has been written by the task which has processed the first partition. Similarly, if we go back and see the last partition, which is the 7th partition, we have 4 employees in that partition. Let me open the final partition. You see, you have 017, 018, 019 and 020. This is processed by the task which has processed the last partition. So now we know how Spark processes the data in parallel. It uses tasks to write multiple files in parallel in order to make sure that the data is distributed parallelly. So each partition is processed by a task, and that task is writing that particular file. Now, consider we want to partition our data before writing to the output location. So in our EMP data, consider we want to partition it based on department ID. So to do that, it's very easy. Consider we have to write the partition data. So I'll write emp dot write dot format, and right now I'll write it as CSV, and I'll partition it. So the partition by would be department ID, and I'll put option as header because we need to see the data headers. So I'll put it header, and I'll save it in the data output location. So I'll write it save data output. I'll put it in 11/4/emp.csv. Now, if I run this, the job completes. Let's go back to 11. I'll go to 4 folder in the EMP CSV. Now, if you see, we have partitioned the data based on department ID. So what Spark has done is Spark has created different folders as per the partition. And this is how Spark denotes the partition folder. It gives the partition column name equals to the partition number. Now, this is what creates a performance benefit. Consider you want to read the partition for 105. In that case, Spark don't need to go and read all the folders. It will just come to that EMP CSV folder, and it will only open the 105 folder, and it will read the data for that particular files that are present under this folder. So let's go back to our partition IDs. Now let's see. Consider you have department ID 101. If you see, the department ID 101 is in the 0 partition as well as in the 3rd partition. Now let's go back to the department 101 folder. You see, it has the part 000 file and part 003 because both the 0th partition and the 3rd partition has 101. So if you open the 3rd partition file, you will only see the employee ID 007, which is this one. Okay. Again, if you open the 0 partition, you will see both the employees 1 and 2, which are part of the 0 partition ID. Okay. Similarly, if you see this partition 7, which is part of all the departments 5, 4, 3 and 2. So I'll go back, I'll open partition 105. This is 017 would be the record that would have been processed from the partition 7. So I'll open the partition 7 file. You see the employee ID 017. Similarly, for 015, again the 012, this is from the 4th partition. You see part 0045. So this is how Spark writes different partition data into different folders. So if one task has a partition ID which consists of more than one partition columns, it will write the data in individual partitions in individual files. So this 7th partition would be written into 4 different department partition in 4 different files. Now, before we move forward, there is a very important concept, write modes. Now, as we know, for read, we have 3 modes, permissive, drop malform, and fail fast. Similarly, for write, we have 4 modes available. The first one is append, the second one is overwrite, the third one is ignore, and the fourth one is error. We will not see all of them, but let me explain the meaning. Append means whenever you have a data and you put the write mode as append, it will again add the data in that folder. It will not touch the data whatever is there. So you can consider it as insert only as well. So if you see, we have written the data in the third folder here. What if I write the data again into that same location? This time I'll put the mode as append. Now, before I run this, let me go to the third folder. You see, you have 8 files. Let me run this. If I refresh this, see now this file number has increased to 16 because it has appended the data. What if I make it overwrite? See, Spark has now created only 8 folders. The number of time I run this overwrite folder, every time it will clean up the folder and again write the data. Similarly, if I put it as ignore, it will first check if the data is available. If yes, then it will do nothing. So if I run this, nothing will happen because the data is already available. But in this case, if I put error, it will fail if the data is already present. Let me run this. See, the job failed because the data is already present in the EMP CSV folder. Now, bonus tip for the day. Consider you need only one output file of the process data to share with someone in the downstream. How can you achieve that? For this, we need to use repartition or coalesce. So let me do with repartition. I will write emp dot repartition. I'll put the repartition as 1. Then I will write the data. I'll put format as CSV and I'll put option as header, which should be true. And I'll save the file again to the data output 11. This time I'll write in the 5th folder, I'll write emp.csv. Now, if I run this, I'll go back and I'll open the 5th folder. You see only one file created because Spark has repartitioned the whole 8 partition into 1. Here, the data shuffling has happened. Only use repartition in case it is necessary. Let's view the data of our file generated. So our file is generated with only one task because all the 8 partitions has been read, then converted into 1. So if I open this file, you see all the employee records along with the header. Now, if you need to rename the file, you have to do it manually using some Unix or Python script. PySpark does not have ability to rename the file because once you put the name as save, it creates a folder with that name, not the file name. Till today, we have executed our code in our local environment. Today, we will see how Spark execute code on cluster. We will see what are the different resource cluster managers available, and we will see what is the deployment mode available for Spark. We will also see some of the Spark properties or configs which are available for cluster management. But before we run our code, let's understand how Spark works on a cluster environment. Now, to understand how Spark works in a cluster environment, let's understand with this example. Consider we have a driver program marked in yellow. And we have a resource manager which is marked in blue. Again, we have a cluster which is having 2 worker nodes, node 1 and node 2. Now, what happens when we submit a program? So we know Spark session is the entry for our Spark program, right? So whenever we submit a program or an application, the Spark session connects with the resource manager first. It asks the resource manager for the required resources. Consider you have requested 4 executors with 2 cores each. So total we will have 8 cores, right? Now the resource manager will contact with its cluster. It will create the required executors. So for each worker node, it created 2 executors. And for each executor, it created 2 cores. So once this resource is allocated on both the worker nodes, resource manager will get back to Spark with the required information. Once this information is supplied to the driver program will start connecting with the executors to execute the code. So first it will copy the Python program to all of the executors. So this Python program will now be available for all of the executors. Once this Python program is available with the executors, now this Spark session will instruct the tasks that it need to perform. So all the cores will now have their tasks that they need to perform in order to process the data. And once this processing is done, executors will report back to the driver program with the required result. Now, based on the status, whether the program has success or failure, driver program will now communicate again with the resource manager to shut down the required allocated resources. Once the resource manager gets all the information, it will scrap off all the executors it has created for that application. And this is how generally a Spark program works. Now, we know this resource manager is something which is responsible for allocating the resources to the driver program or the Spark session, right? So it plays a major role. So resource manager is also known as cluster manager. So there are majorly four type of cluster managers available. The first one is standalone, which is basically a Spark cluster. The second one is Yarn, which is basically a Hadoop cluster where Yarn is the resource manager. The third one is Apache Mesos, which is now deprecated, so it is no longer available. And the fourth one is Kubernetes. This is for the containerized environment. So these are the four types of resource managers that are available. Now, whatever I explained right now was the client mode of execution. So there are two deployment modes. Whatever I explained right now was the client mode in which our driver program is sitting into the client machine. Now, there's one more mode available, which is called the cluster mode. Now, in case of deployment mode where it is clustered, this whole driver program will also sit inside the cluster in an executor. So, Spark session will sit inside the node into an executor. So, in this case, resource manager will create one more executor in which this particular program will sit, and it will communicate with the executors and the tasks from the same executor itself. In this case, you can see the only responsibility for the client is to submit the program. Once the program is submitted, everything is on the cluster. Once the execution is done, the cluster manager will communicate with the driver program sitting on the cluster, and it will terminate the cluster accordingly. Now, there is one point to note. The executors that the resource manager is creating is nothing but JVM process. So these are some Java virtual machine processes that the resource manager create within which the tasks are executed, what is supplied by the Spark session. I know for the first time it might sound confusing, but don't worry, we will look into this with a live example. I am in my Jupyter Lab environment. Now, I have my Spark cluster up and running. This is a standalone Spark cluster, which has two worker nodes. You can see the information of the worker nodes here. This is worker 1 and this is the worker 2. Both the workers have 8 cores each, and the total memory for the worker node is 6.7 GB each. Now, till today, we were running our programs in local. Today, we will execute this in our standalone cluster. To do that, we have to change our master to the Spark master, which is running at 7077 port. So I'll copy this and I'll paste this here. So our master is now Spark, and this is the location where the Spark master is running, and this is the port. So if I execute this now, okay, my Spark UI is ready. Let me go and refresh it. Let me go to the Executors tab. In the Executors tab, if I scroll down, now you can see it has two executors running, 0 and 1. Okay, and each one is having 8 cores. So if we go back to our Spark master and refresh our tab, we can see one application running, and the name of the application is cluster execution, which is the same app name that we provided within our Spark session. So we go back and expand the application. We see we have two executors, each one generated in each worker. So our first executor ID is running in the first worker, and the second one is running in the second worker. And each executor has 1024 MB memory and 8 cores each. Now, this is the default setting that Spark provides. We have this whole configuration listed in the Spark documentation. If I search for executor memory here, you can see it is 1 gig, which is 1024 MB. So can we change the value for this particular configuration? The answer is yes. Before we do that, let's write a sample data frame, which will only write 10 values, and we will write it as a form of CSV in data output 15 to as range.csv. Let's run this cell. Okay, our data is ready. We can see the second folder and range.csv, in which we have multiple files here. Let's go back to our Spark UI and refresh our job tab. Okay, the save command has run with 16 tasks. It implies that the data that we had 16 partitions. If we expand this and if we scroll down to the stage and expand this, we go into the task, we can see all the 16 tasks executed in parallel. So this particular task has executed on the cluster. Now, we have only two executors, each one of them running in each worker node. right? Let's create two executors, each in one worker with 4 cores and a different memory size, say 512 MB. To do that, I'll go back to my Spark application and I'll add to Spark config. I'll add dot config and I'll write Spark dot executor dot instances. I'll put it as 4 because we need 4 executors. Now again, I'll put it as config. All right, Spark dot executor dot cores. I'll put it as 4. It implies each executor will have 4 cores. Now I'll put the memory setting as well. So I'll write config Spark dot executor dot memory. I'll mention it as 512 MB. Let me stop the Spark session first. So I'll stop the Spark session. Once I do that, I go back to this application. And if I refresh this, this comes into the completed application because we stopped the Spark session. Let's rerun our Spark session. So I'll rerun this. Our Spark session is created. Let's go back and refresh this. Awesome. You see a new application is created. This time it has 16 cores and 512 MB per executor. If I expand this, you see we have 4 executors, which is what we requested, and each executor had 4 cores and 512 MB of memory. So this is how we can also change the configuration. Now if we run the application will run in 4 executors with each having 4 cores. So let me run this again. So I'll run this, and this time I'll write it to say location 3. I'll run this. Let me go back to the Spark UI. I'll go to the jobs tab. I'll open the save. This is again 16 tasks because 4 executor, which 4 tasks each. So I'll expand this. You see, now we have 0, 1, 2, and 3. 4 executors having 4 tasks each, and all of them are running in parallel. You can see the executor IDs mentioned here. We can also go to the executor tab to see the same. You can see we have 4 executor IDs other than our driver program, which is running in our local. We have 4 cores each, and we have 93 MB storage memory. We will discuss about this memory setting later when we discuss the Spark advanced topic. Now, this whole execution is happening in client mode. The reason is this whole Spark session is sitting in our local machine, which is the driver is there in the local machine. You can see the driver is not on the worker nodes because this is a different location which is on our local machine where the driver is sitting. So this execution is happening in client mode right now. Now, whatever configuration I just put into the Spark session was just to show you how Spark behaves when we execute a program in the cluster setting. But this is not the way how we submit a Spark program to a cluster. The best way to submit a program to a Spark cluster is using the Spark submit. That is a command that is available with Spark that is used to execute your code on cluster machines. So to demonstrate that, I've just created a Python file where I have removed the master because we will provide that runtime configuration using the Spark submit command. I've just made the application name. I've just put the DataFrame commands that we are going to run. This is just a sample demonstration how Spark submit works. Now, to run the Spark submit command, I am inside the Spark installation folder, which is /spark in my case. For your case, it might be different. So be very sure where the Spark is installed. Now, we can find the Spark submit command in bin Sparks submit. Now, before we can push our program to this Spark submit, we can define the informations that we need. The first one will be the master. In our case, this will be the Spark cluster. So I'll again go back to the Spark cluster, copy the Spark master location. I'll put it as master. Now, there are runtime configurations that we need to supply to get the number of executors and cores. So to get a number of executors, I'll write num executors. I'll run with, say, 3 executors. And this time I'll use each executor with 2 cores. So I'll write executor cores, and that will be 2. To set the memory, we can write executor memory 512 MB. And now I'll provide the Python file which I need to execute. So I'll write /home/Jupyter PySpark 020 and my file which is 12 understand cluster.py. Now I'll just press enter to execute this. Awesome. Our application execution just completed. So you understand how we can use the Spark submit now to submit our job to the cluster. And this is how the jobs are submitted in production environment in Spark clusters. Now, since we are working on clusters, today we will understand one of the important concepts, which is user-defined function on Spark. User-defined functions are certain functions which are written by a user for a specific purpose. It can be a domain-specific code or a generic code, but it should do some process that is defined in the logic of that function. We will also see how Spark works with UDF. And when we talk about UDF, there are certain demerits of a Python UDF. We will also look into that. Now, before we can start with our coding, let's understand how Spark works with Python UDF. Now, consider we have a Spark application running where we have a driver and we are running this program on a cluster which has two nodes, node 1 and node 2. Once we write a Python UDF to process our logic, Spark copies this Python UDF to individual worker nodes. And once this is available, Spark spins up a Python process. Once this process is ready, the data is now serialized in the format that Python can understand. And the data is processed row by row. And once this data is processed, the results are reverted back to the JVM process, upon which the JVM reports back to driver with the result. Now, if you can see, this Python process also resides in the same node where the JVM resides. Again, since the Python process is separate of that of the JVM process, the JVM process does not have control over this Python process. Thus, Spark does not have control over this Python process. If this Python process grows in size and exceeds the memory limit, we will run out of memory on the node and there will be out of memory error. So, if we try to understand the demerits here, first the data needs to be serialized and deserialized. Next, the costly Python process has to be spin up. And once this Python process is up, the data needs to be processed row by row. Now, we know that writing a Python UDF can be expensive. Then what is a solution for this? The first solution would be not to write a UDF, rather utilize higher order functions. If that is not possible and we need to write a logic, then the UDF needs to be written in Java or Scala. Once we register this Java or Scala UDF, that is already present in JVM, we don't need to spin up this Python process. And we can reuse this Java or Scala UDF within the Python code itself. Let's get into code and write our first UDF. I am in my Jupyter environment. My Spark standalone cluster is already up and running. We have two workers which are having 8 cores each and 6.7 GB of memory. Now, to run my code on the cluster, I am pointing my master to the standalone cluster. And I have done 3 config properties. The first one being Spark executor cores, which implies each executor will have 2 cores. And the maximum number of cores this application can use is 6. That implies if we have 6 cores and we have 2 cores each executor, we will have 3 executors, each with 2 cores. And the memory for each executor would be 512 MB. Let's generate our Spark session first. Okay, my Spark session is up and ready. Let's go and refresh our Spark UI. Let's go to the Executor tab. Great, we can see 3 executors up and running, each with 2 cores. So total, we have 6 cores. If we go to our cluster and refresh the page, we get one application which is having 3 executors, each with 512 memory and 2 cores, in which one worker node is hosting 2 executors and one is hosting only one. Let's go back to our code. For this example of UDF, we will read employee data. We already have our employee data in the output location. And this is the schema that we will use to read the employee data. Let's create our employee data frame and check how many number of partitions are present for that employee data. Great, our employee data frame is ready and the data is read in 4 partitions because the output for get num partitions is 4. For this example, we will try to create one column for bonus, which will be 10% of the salary. Now, to do that, what I have done is I have written a function which will take in salary and it will return the 10% of that salary, which is the bonus. So I've named this function as bonus. Now, to create a UDF from our function, we need to import UDF from PySpark SQL functions module. Let's do that. Okay, now our name of the UDF would be bonus UDF. And we will write UDF and we will put the name of the function, which is bonus. Now, before I can run this, let me run the function first and I'll generate the UDF now. Now, we have our UDF up and ready. To add a column, we know we can use with column. Let's do that. We will write emp dot with column And we will create a new column called bonus, and we will use our UDF to generate that column. I'll write bonus UDF and I'll pass the salary column. Now I'll just write so to view the data. Let's run this. Awesome. We can see a bonus column created, which is almost the 10% of the salary. So our UDF is working fine. Let's go to the Spark UI to view what has happened in the background. I'm in my Spark UI. I'll just go to the Jobs tab. If you can see, we have 4 tasks running for this source string, 1 in a separate job and 3 other in a separate job. If I expand one of them, let's go to the stage. If I scroll down, you can see it has taken too much time in the deserialization. This is because it is deserializing the data which the Python UDF has written. Now, how do we see that Spark has generated a Python process to process this data? Let's do one thing. Let's go back and add a slip in this function so that it is up and running while we go back and investigate. To do that, I'll import the time function and I'll just put a slip command. So I'll write time dot slip and I'll write 10 so that after each record processing, it will slip for 10 seconds and we can go back and see what is happening in the background. Let's run the cells again. Now, before I run this show command, let me connect to one of the worker node so that we can see what is happening in the background. I have connected to one of the worker node. I can write PAAUX to see what are the running process. You can see there are Java process running, but there is no Python process running right now in the worker node. Let's go back and run this command now. So this command is up and running now. Let me go back and again write PSAUX. You can see the Python process has started. So this is the Python process that Spark has initiated in order to process the data using the UDF that we have written in Python. And this is a bigger demerit because the data needs to be serialized and deserialized while using this Python process. Now, this bonus UDF is available for the DataFrame API. What if we need to use with Spark SQL or Spark SQL expressions? For this, we need to register it, right? So for registering, we need to write spark.udf.register and we need to provide a name for that UDF. So I'll write bonus SQL UDF, which will be available for the Spark SQL, and I'll give the name of the function, which is bonus, which we have written, this bonus, and we'll have to provide the data type which it will return. So the data type that it will return will be double because we have 0.1 multiplying with the integer salary, so the return will be a double. Great. Now before I rerun this register, let me remove this slip command. Let's run the cells again. Okay, our Spark UDF is registered. Now to see it in the expression, let me bring in the expr. To do that, I'll write. Okay, now we have imported the expr method. Let's use that to see it in the Spark SQL function. I'll write expr and within double quotes, I'll write the whole function. I'll remove this salary double quotes and I will add that bonus SQL UDF. Same solution. But now this is available for Spark SQL. You can use Spark SQL to write this UDF directly in string methods. Since this Python UDF is expensive, it is always recommended to use only if it is at most necessary. Now, we can do this bonus without using a UDF. We can just use expressions. So let's do it with expressions. So I'll write emp dot with column, and again I'll name the column as bonus, and I'll write this expression, which would be salary into 0.1. Now, if I run the show, you will see same result. But for this, you will not have Python processes created because this is happening within the JVM itself, which is the executor. Now, what if it is very necessary for you to write a UDF? You can't avoid it. In that case, you need to write that UDF in Scala and you need to register that UDF like this in Scala. Once that UDF is registered, that UDF will be available to use in any language. Then you can write this in expressions to get that UDF and the work done that is required for that column or the UDF. So today's video is going to be too much interesting. We'll be looking into the background of Spark's working. Now, this will enable us to start working on the advanced topic of Spark going forward. Now, if you have not seen our videos previously, I would recommend you to go back and watch our previous videos. Today we will understand what is Spark's explain plan. We'll also see what are directed acyclic graphs or tags. We will understand what is SUPL and what are its impact on stages and tasks. and we'll also see how data frames are made up of. Now, this is very important that you understand these concepts clearly. So, without any delay, let's begin. Okay, to understand and demonstrate today's example, we will consider two data frames. This is data frame 1 and this is data frame 2. Both the data frames consist of even numbers. The first data frame will have only one column called ID and it will have even numbers till 200 with a step of 2. Same thing for the second data frame, we will have the same ID column, but this time the step will be 4. And again, we will have the even numbers till 200. Now, for next step, we will repartition both the data frames with 5 and 7 respectively. And later, we will join both of them to create one data frame called sum, in which we will find the sum of the IDs. This will be the complete flow for our demonstration today. Now, I understand this example looks simple, but this will help us to understand a lot of things today. So, I am in my Jupyter Live environment. As usual, we will generate our Spark session. For today's example, I'll consider the master as local. Before we will generate our data frames and we'll process them, I'll disable some of the configurations which are enabled in Spark 3.0, which helps in optimization. For today's example, I will disable the adaptive query engine and the broadcast join. Now, we will understand more about this AQE and broadcast join in future sessions. For now, we will just disable them so that we can see what is happening in the background. Let me generate the Spark session and disable the configurations. Okay, let me check the default parallelism so that we can know how many tasks can run in parallel. So to do that, I'll write spark context dot default parallelism. Let me run this. Okay, it is 8. It implies 8 tasks can run in parallel. Okay, here is our first data frame and the second data frame. So as mentioned, we are going to create two data frames with a range of 200 with a step of 2 and 4. And both the data frames will contain even number. There will be only one column called ID so that we can join both the data frames. Let me run this. Okay, our data frame is generated, but we have not triggered any action. So if we go back and refresh our Spark UI, nothing will happen. Let me go back. Now, the second step is we will repartition both the data frames into a different number. Now, before that, if you want to check how many partitions the data frames are read, we can write df underscore 1 dot rdd dot get num partitions. Okay, you can see it has been read in 8 partitions. Similarly, for the second data frame, again 8 partitions. So we understand both the data frame will be read by 8 tasks in parallel. Okay, now let's repartition the data. The first data frame in 5 partition and the second data frame in 7 partition. So I'll create 2 data frames, 3 and 4. I'll run this. Completed. No actions done. So there will be nothing in the Spark job yet. Good. Let's go back and see the number of partitions now. So I'll write df underscore 3 dot rdd dot get num partitions. So you can see 5. So the number of partitions has changed from 8 to 5. If I run it as 4, you'll see 7 because we have made the repartition as 7. So after repartitioning, we will need 5 tasks and 7 tasks each. Okay. Now, next thing, we are going to join both the data frames based on the ID. And this joining will happen on the data frames that are repartitioned, which are 3 and 4. Let me run this. Still no action. So nothing should be there in the jobs tab. Correct. Let me go back. Now, we are doing a sum. The sum is based on the ID column and we are renaming this as total sum. So this sum will happen on the joined data frame. So let me run this. Still, this is a transformation. There is no action yet. So if I go back and refresh, nothing is there. Now we have the action, which is so. So whatever sum is generated, let's view this. So as soon as I run this, we'll see a job triggered in the Spark UI, which will do all these operations that we have done till now. Let me run this. Awesome. We got a sum of 4,998. Now, if I go back and refresh the Spark job, great, we have one job here. Now, if I expand this, okay, there is a lot of things happening in the background. Now, why this is happening like this? We have around 6 stages and each stage is doing something. If I go down, okay, there is the information about the stages. Now, before we deep dive more into the stages, let me go back to the job once more. Here, You can see we have completed 6 stages and the total number of tasks triggered is 229. Now, before we see this in the Spark UI, is it possible for us to understand how this is 229? The answer is yes. Let me go back and make you understand. Now, there is a concept in Spark called pipelining. It implies whenever possible, Spark will try to pack as much as transformations possible into a single stage. And whenever it encounters a supple or an exchange state, it will create a new stage. So, if we see, we are reading here in 2 data frames. So Spark will create one stage each. And since there are 8 partitions, so 8 tasks will be involved in reading both the data frames. Now, next we are doing a repartition of both the data frames. So, for the first data frame, there is a shuffle because this is an exchange where 8 partitions are being converted into 5. So, there's a shuffle stage involved here. So, Spark will again create one more stage where it will involve 5 tasks because we are converting 8 into 5. But the data that would be read for this will be read from the 8 disk. So what it has to do is it has to write the data somewhere and this step has to read that data. Similarly for DF4, again we will read the data from DF2 and it will again create one stage with 7 tasks. So till now we have 4 stages and each having 8 and 7, 8 and 5 respectively. Next, we are going to join this both repartition data into one. So again there is a shuffle involved. And in this shuffle, this join is going to read the data from these tasks which are writing the data from 5 and 7 partitions. So it will create one stage which will read data from 5 and 7 tasks respectively and it will write data to 200 partitions. Now why this is 200 partition? Because the default shuffle partition for Spark is 200. You can go into the Spark config and you can check that out. But we can also check that configuration and we will do that when we will work on the optimization. For now, the default configuration for Spark for shuffle is 200. So this join data will create one stage which will write the partitions into 200. And next there will be one stage again created for the sum which will read the data from this 200 shuffle partitions and only create one task because we have to do sum on all the data. So all the data will be read and processed by only one task which will create the sum and show to us. And this is how it is being done. So if you note here, we have one stage, two stage, 3, 4, 5 and 6 stages. So we have 6 stages each with 8, 8, 5, 7, 200 and 1 respectively. So these are the total number of tasks. So if you add them up, they are 229, which is what we have seen in our plan. Let me expand this one. Let me go back. And if you see, we have 8 tasks for reading the first data frame, again 8 tasks for the second data frame, then we are repartitioning with 7 and 5, then there is a shuffle partition of 200 and then all the data being read and processed by only one task. And this is how you can determine the number of tasks required. I hope you have understand the background. Let's see the DAG now. Now, if you see the DAG, there are 2 stages where we are reading the data. This is the first stage and this is the second stage. And in both the stage, we are reading the data. This is because of the 8 tasks each in which we read the data for both the data frames. Now, there is an exchange. This exchange is because of the repartition of data. If you see the second stage and the third stage has 5 and 7 tasks where we are doing the repartition. So this is the stage where that repartitioning is happening. And after that repartitioning, both the data are read in stage 4, which is for the join, where we are generating 200 shuffle partitions, which is by default. So both the exchange data, which is the repartition data, are read and joined. And then that data is being pushed to one partition in order to do the sum, which is being done in the last stage. So the thing that you have to notice here, for the first 2 stages where we are reading the data frame, we are writing the shuffle data. And if you notice, the same shuffle data is being read by the repartitioning data. And again, it is writing the data which is being read by this task. So this two, if you join, both of them contributes to 8.2 KB, which is being read by this task to join the data. And it is writing 11.2 KB, which is for the 200 shuffle partitions, which is being read by the last task and which is providing us the output. So I know this can sound confusing for the first time, but now you know how this is happening in the background, how this DAG can help you to understand what is happening in the background. Okay, before we move on, let me show you the explain plan for this. So to see the explain plan, you just need to type the data frame name dot explain. If you run this, it will print out the physical explain plan. Now, to read the explain plan, we go from bottom to up. Now, the first thing that you see is a range. This is where we read the data. Now, if we go back to the DAG, you see this number 3. If we go back and you see this number 3, this implies this DAG is reading the data which is mentioned here in the explain plan. Similarly, if you see this line, it says 1 and it is again the range. If you go back and you see 1, this is the DAG which is doing. And then the exchange is happening. Now, if you see the exchange here, now this is where it is repartitioning the data because it mentions here repartition by number. So it is doing that repartition here. And then this exchange is going to the second and fourth step, which you can see in the DAG here as second and fourth, which is being used to read in and join the data. Now, if I go back and you see the join is happening at 5. Now, if we go back, this is 5 where the join is happening. Now, if we see again, you see this 5 being used to do the hash aggregate and the 6 is what is giving us the result. If you go back and see this 5 is going to 6, which is giving us the data. And this is how you can understand an explain plan. An explain plan can help you to understand what is happening in the background. And it can also help you to optimize a lot of things. And we will see that in our future sessions. We will try to understand an explain plan and we will try to optimize our pipelines accordingly. Now, in some of the cases, you can see some skipped stages. Now, what is the skipped stage? There might be situations where Spark can launch more than one job to do a particular task. For example, in the previous example, we have done the sum till here. Now, if we want to do an union with the data that we have in sum with the same data frame that we had here for the repartition DF4, let me run this again. Now, let me do the so. If you see, we have two jobs now. For the first job, it has processed till the sum. That we know because we can see 229 tasks. And for the union step, it has done an extra job which skips all the steps and read the data and processes the union. Now, if I go into this, you can see all of these stages are skipped because this is already processed in the previous job. So what it has done is it has skipped it and then used the data to do the union here. And this is how it happens. In certain cases, you can see more than one job launched and Spark will skip the stages which are already processed or done. And this is how Spark optimizes its DAG. Now, there is one important thing to notice here. Whenever there is a shuffle or exchange, Spark writes the data and in the next stage, it reads the data. What is the benefit here? There's one benefit. If it fails in the subsequent or the next stage, it can read the data from that shuffle write. It does not have to trigger the previous states. So if I go back to the job that we created for the sum, so consider it failed in stage 2. In that case, it does not need to trigger the stage 0. It can read the shuffle write, which has been already done by the stage 0. It can read the data again and it can process the stage again. So this helps Spark to process the data in later stages, even if that stage or that task fails. And this is very important to understand about shuffle. And to confirm that, let me run the explain plan for union. If you see, we have a reused exchange here. It provides you the ID, what it is reusing. So it is reusing the ID, which is 410. It implies it is reading the data from this exchange directly. It is not running this range again. So if you want to confirm that, just go back to the Spark data frame tab. You see the source string where it has triggered two jobs for that. You just expand this. You can see the whole DAG here. Now, if you see from this exchange, it is reading this arrow mark is going directly to where it is doing the union. So it is directly reading that shuffle write, what it has done previously after the exchange, which is for the repartitioning. It is directly reading and doing the union. It is no longer again triggering the stage to create the range and do the exchange. It is reusing that shuffle write. And this is one of the benefit of shuffle writing data. Now, I understand it can be too much to consume in a single day, but you can stop and revisit this video whenever you want. The next thing to understand is how data frames are made up of. Now we know that the data frames are abstraction of Spark core APIs, right? And the Spark core is built up with RDDs. RDDs are resilient distributed data. So each data frame is by default an abstraction of RDD. To view that, let me go back, and this is the data frame that we created from the range. Let me run this. If I do .rdd and I run this, you see this is a RDD. This implies any data frame that you see is an abstraction of RDD. And RDD was very popular concept when Spark started. Now, to make things easier, Spark has done a proper abstraction of RDD and provided us with data frame and data sets. And it also recommends us to use data frames and data sets going forward. So it brings us with a question when to use RDD. RDD is only recommended when you have to distribute the data physically with help of your code, or you have to work extensively with Spark core APIs. If that is not the case, then RDD is never recommended. We always prefer to go with data frames, and that is what we have been seeing from day one. But we will visit RDD when we come to the closer of this course. So I hope today we have learned a lot of things. Now you understand how to look into DAG and explain plan. Now that we have seen how DAG and explain plan works in Spark, today we will understand Spark shuffle operation and how Spark handles shuffle data. We will also see how to optimize shuffles in Spark. Now, before we can begin, if you have not seen my previous videos, I'd recommend you to go back and watch our playlist from the beginning. Let's begin with some theories today. Now, till now in theory we know that narrow transformations only work on a single partition. They do not involve other partitions while working. But a wide transformation can involve multiple partitions. So what Spark does is, there is a concept in Spark called pipelining, where it will combine multiple narrow transformations into a single pipeline and will try to execute this whole pipeline on a single partition. And it will try to execute similar pipelines on all the partitions of the data. But if we encounter a shuffle in between, which is a wide transformation, Spark will break down this pipeline here and will again create a new pipeline with other narrow transformations which are there after this shuffle step. Thus, we know that this pipelining are the stages. Now, but we know that this shuffle stage will break down the pipeline into multiple stages. So what Spark will do? In the first stage, it will execute all the narrow transformations possible, and in the end, it will write shuffle files. Now, the shuffle files are something which are encoded in tungsten binary format. We need to know that this is tungsten binary format, which is also known as unsafe row format. Now, once these temporary files are written, in the next stage, this would be something that Spark will read in the first step and will process the remaining narrow transformations. And this is how Spark breaks down the whole pipeline into two processes. The first process will start reading your data and will write shuffle temporary files. And the second portion would read your shuffle temporary files and would process the remaining steps. Now, an important point to note here is these shuffle files are written to disks and which are sent over to other executors using the network. So this involves here the disk IO operations and the network, which is a costly operation in Spark. This is why it is very important to avoid shuffle where is it possible. But you cannot avoid shuffle always, because sometimes we need some wide transformations to happen. Thus, the only way to deal with it is how to optimize shuffle, which we will see today. I am in my Jupyter Lab environment. Today we will work with employees data. Now, if you see on my screen, we have a CSV file where we have multiple columns for this particular file. We have a salary column in this file for which we will be calculating the average salary as per the department ID today. This would be our record set for the whole operation. Now, before we can begin, I'll generate my Spark session. For this, I'll run the code on my Spark cluster. The maximum cores that we can have is 16, and each executor can have 4 cores. This implies we will have 4 executors with 4 cores each. The memory is defined as 512 MB. Let me run this cell. Okay, our Spark session is ready. Let's go back into the cluster and check the setting. So I'm in my cluster. Let me refresh the screen. Okay, here is the application that is running. If you see, it has 16 cores. Let me expand this. You can see we have 4 executors with 4 cores each, and each of the executor has 512 MB memory. So this is our Spark UI for the operation. Now, before we start, let's check the default parallelism. Now, we know that we have 4 executors and 4 cores each. So total, we can execute 16 tasks in parallel, and that should be our default parallelism. Let me run this. Okay, it is 16. Now, for today's session, I'll disable the adaptive query engine. We will discuss about AQE and the adaptive query engine later in our course. So don't worry about it. Let me disable it for now to make you understand how shuffle works. This is done. Now, EMP CSV file that I explained in the beginning is having around 10 million records. Now, before we read that, I'll use the schema for that file. So I'll paste the schema here. This is the schema that we have for that particular file. I'll read the file into a data frame emp. So I'll write that. I'll write emp is equals to spark dot read format. The format is CSV. Now we'll specify schema, which is underscore schema, and we have header in the file. So I'll specify option header, which is true, slash input slash datasets and our employee records.csv. Now, if I run this, nothing should happen, right? Because we have already specified the schema. Let me go back and refresh the Spark UI. Nothing is there. Since we have already read the file, now we will find out the average salary per department and we will write the output in no-op format in order to benchmark. Before that, let's write our data frame for average salary. So I'll name that as EMP average is equals to, now we'll read the EMP data frame, we'll do a group by, which would be on department ID. Now, since we are doing average, so we have to do aggregate. So I'll write AGG. Now we have to import the average function. So that I'll do. Now I'll write average and I'll do average of salary. So I'll write average of salary and I'll alias this column as average salary. So I'll write alias and the name of the column would be average sal. So we have written our data frame for average calculation. Now let's write this data. Now today we will use no-op. So I'll show you how to use no-op for performance benchmarking. So to write this data frame, I'll write EMP average. Before that, let me trigger this. Dot, I'll write, and the format we will use as no-op. No-op are just used for benchmarking. Whenever you write using no-op, it will not write the data anywhere. However, it will traverse through the whole data for performance benchmarking. So to do that, we'll write dot mode, which should be overwrite, and we'll just write save. So this will read the whole data for performance benchmarking, but it will not write the data anywhere. This is how we simulate Spark for benchmarking. Let me run this. Awesome. Now we have triggered our action, right? Let me go back and refresh the Spark UI. Great. We have our first action here. Let me expand this. Okay. Now if you see, we have an exchange here. This is happening because of that group by. Now, if you see, Spark has divided it into two stages. The first stage is with 16 tasks and the another one with 200 tasks. Now, first stage, it is reading the data, whole 93 MB file, and it is writing the shuffle, which will be input for this 200 task. Now, why this is 200? Because Spark default partition is 200. Let's check the Spark partition setting. To do that, I'll write spark.conf.get, and this is spark.sql.shuffle.partitions. If I run this, you see this is 200. By default, Spark has a shuffle setting of 200. So this is why 200 tasks are created. Now, let's expand our first stage to understand more. If I scroll down, we can see all the 4 executors here, but we can see 40 records has been written by each. Why this is 40? Let me go back and show it to you. Now, we know we have a function called Spark partition ID in order to show the partition number of the records. Now that we have imported the Spark partition ID, let's view the partition formation. To do that, I'll write emp dot with column. I'll create a new column called partition ID with Spark partition ID, and I'll put a where condition on the first partition to show you what are the data in that partition. So I'll write partition ID equals 0. Now I'll just do a show here. Okay, you can see there are multiple departments in the same partition, right? So we know that each partition will contain more than one department. And that is why there is 40 records each, because each partition is being processed by each task which contain 10 departments. This is why we have 4 tasks each executor and 10 department per task. This is why 40 records are being written. Now, why only 40? Because each task is already doing the aggregation of average before writing it into the shuffle file. And we have this aggregation written in the shuffle files. And these shuffle files are sent over network. And in the next stage, these files are being read and the next narrow transformation happens. So let me go back to the stage 2. This was the stage 2. if I expand this, you see so many tasks are executed because we have around 200 tasks for this. But if you notice, the number of records read is very less in comparison to the number of tasks involved. And even multiple tasks have done nothing. Only few of them has read the records. And this is where it's overkill of the CPU usage. You have to decide the number of shuffle tasks properly in order to optimize this. Now, if we go back to the data frame, we see it took 11 seconds in order to execute the first action that we did, right? So let's do one thing. Let's properly decrease this shuffle partition into an appropriate number and again run this task. To do that, I'll write spark.conf. Now we'll set this, so I'll write .set. Again, I'll use the same configuration, which is spark SQL shuffle partitions, and I'll reduce this to a number called 100. Let's see what happened when we reduce this to 100. So I'll run this. Let's validate if it is set to 100. Yes, it is 100 now. Let me rerun the writing of the data. So I'll run this. Let's wait. Okay, it's executed. Let's go back to the Spark UI, refresh this tab. You see, again, a job is created, and this time it has executed within 3 seconds. If I go into this particular job, again, the shuffle stage has happened, but if I scroll down, this time it has only used 100 tasks. Now, if I again open this, so many tasks executed, but again, this is an overkill because much of the tasks are doing nothing. Only few of them are reading. Now, since we know that this is only few of them are going to read this data, which is very less, can we reduce the shuffle partitions again? The answer is yes. Let's reduce to a number, say 16. Let me run this. If I again run this, let me go back. Before that, let me run this write operation again. Let me go back and refresh this. See, now it has reduced to 1 second. So we have directly established a relation between that configuration, which is Spark SQL shuffle partitions, with the duration of the execution. Now, if I expand this job, 16 tasks are executed this time for the second stage. If I expand this, now we can see there is very less overkill and much of the shuffle read are being processed by much of the task. Now it brings to a question, what should be the appropriate shuffle SQL partition size? Now, we know that reducing the shuffle partitions can improve your tasks, but can we reduce it to a much lower number? The answer is no. You have to be very careful while configuring this property. Sometimes configuring this to very lower number can make your task run out of memory, which can lead in issues. Consider you have a lot of shuffle data which has to be read, and you have reduced the number of tasks to such lower number that each task had to do that operation again and again, and this will again decrease your performance. So you have to be very careful and you have to identify a proper number before setting this up, but this has to be done very carefully. Now that we have seen that shuffle partitions can improve your performance, but the data that we have read previously was not partitioned. What if we read a partition data? Will that improve the performance? Let's check it out. To do that, what I'll do is I'll read a partitioned CSV data, which is already present in EMP's partition based on the department IDs. So I'll read this data. So I'll write EMP partition, which is for partition. I'll write spark.read.format, which is CSV. And again, we will put the schema, which is underscore schema, and we will write the option, which is headed true. Then I'll load the partition data. For that, I'll do /data/input emp partition.csv. So I'll run this. If I go back and refresh the job, you'll see nothing. Let's do the aggregation again, but this time on the partition data. So I'll copy this query from the top. So I'll copy this aggregation query, but I'll change the data frame to EMP partition this time. Let me run this. Now again, for performance benchmarking, we'll write this data. So I'll copy this and we will run this. Awesome, the job completed. Let me go back to the Spark UI. If I refresh this UI now, you see we have a job which completed within 2 seconds. Now if I expand this, you can see first one has only used 15 tasks to read the data, but this time the shuffle write was very small. Why this is small? If I expand this and scroll down, you can see the write for each of the tasks was only one record, because each of the task is reading a particular partition of data. There is no mix and match for that particular task, so it has to write only one record per task. That is why this is much easier this time. And each of the executor is writing 5 or 6 records. And that is where, if we go back, now again, if we see the second stage, again, since our shuffle partition was set to 16 tasks are reading the shuffle files and completing the aggregation. So we can see there's a performance benefit whenever we read a partition data, and that is what it is. Now, partition data provides you a benefit during shuffle. We will see more about it when we look for the optimization for joins. For now, you can just keep in mind, if the data is partitioned properly, it can give you a benefit on shuffles as well. Now that we have understood shuffle in great depth, before we can conclude, let's understand a few more important points. The first one being, always try to work with good shuffle. This implies avoid unnecessary shuffle wherever possible, because shuffle is a costly operation, so always prefer wherever necessary. Do not go for shuffle operations without any need. The second one is repartition your data. This implies make sure your data is properly partitioned, which can reduce in shuffle. The third one is push the filter as early as possible. This implies filter your data before doing the aggregation or shuffle operation. This will reduce the data, hence reducing the shuffling amount. Today we will see how Spark works with data persistence. We will see what are cache and persist methods. We'll understand how caching works in Spark. We'll also see what are the different level of data persistence or caching in Spark. Now, if you have not seen our previous videos, I'll recommend you to go back and watch our playlist. I am in my Jupyter Lab environment. Today we will work with sales data. Before we can begin, let's view the data that we are going to use today for our demonstration. So for that, I'll write head, and I have a file called newsales.csv. If I run this, you can see the columns that are in the CSV file. We have multiple columns like transacted data, transaction ID, retail ID, description, amount, and city ID. This file is approximately of 700 MB, and it has around 7.2 million records. We'll try to cache this file and see the behavior of Spark today when we try to read the data from this particular piece of file. Now that we know the data we are going to work, let me start with the Spark session. For this, I've just restricted the memory for our executor to 512 MB. I'll be using my local machine for this particular demonstration. Let me run this. Okay, our Spark session is ready. Let me go ahead and refresh the Spark UI. Nice, our Spark UI is up and running. Before that, I'll go into the environment tab and I'll see the memory that is set for this particular executor, which is equals to the 512 MB, which we have defined in the Spark session. Now, as already mentioned, we are going to read the sales CSV file, which is approximately of 512 MB of size, and 7.2 million records are there in that sales file. If you see the schema, we have the schema defined for that particular sales file. What I have done is I put the amount column as table. Rest all the columns are string for now. Let me go ahead and read this CSV file into a data frame. I'll name the data frame as TF. To read, I'll write spark.read.format, which is CSV. I'll specify the schema, which is underscore schema, and the option, which is header. Since we know we have a header in the file, I'll put it as true, and we will load the file, which is at data input new sales.csv. Now, before I run this, since I've already specified the schema, there will be no job created for reading this file. So let me run this. This has executed successfully. Let me go back and refresh the job tab. Nothing is there. Now, before we begin to understand cache or the caching mechanism in Spark, before that, let's view some of the records for this particular data frame. So what I'll do is I'll put a filter where the amount is greater than 300. So for that, I'll write df dot where we have a column called amount, which is greater than 300. I'll just make a so. If I run this, okay, we get an output where the amounts are greater than 300. Let me go back and see there for this particular job. So we have this job completed. Let me expand this. Now, if you see this DAG, the first step is scan CSV, where it has scanned some of the rows for that particular output. So now we understand if we run it against the data frame, it is going to hit the CSV file every time. Let's begin with our caching mechanism. So to do that, first you need to understand what happens when we do a cache for a particular data frame. To do a cache, you need to write df.cache. Now, if we run this, you can see output for a data frame. But if you go and see the storage, nothing is there. Even if you go back to the job, nothing is there. The reason is cache, you have to trigger an action. So that action can be count or write. The importance of count and write is count and write method will try to read the whole data frame rather than reading a partial data frame. Let me show you. If I put a count here and now if I run this, now that we got the output for the count, let me go back and refresh the storage tab. If I come back and refresh the storage tab, you can see the cache is created. But notice the storage level. It is disk memory and deserialized. So whenever we specify the cache for PySpark, the default is disk and memory, and this is deserialized. Notice one more thing here. Some of the data is in memory and some is spilled to disk. The reason is we have a data set which is greater than the memory of that executor. Now, if I go back and if you see this cache now, let me run the same query, which is the filter query from this cache. So what I'll do is I'll copy this query now and I'll run it again. Now, if you see, this has completed so quickly this time. Let me go back and open the SQL DataFrame tab. You see the difference? First time it took around 2 seconds. Now it completed in 0.2 seconds because this is reading from in memory. Let me show you the DAG. If you see this, the scan CSV, the number of output rows is 0 because this execution has not hit the CSV. Rather, it has hit the in-memory table scan, which is the cache we just created now. Now, let me go back. So we know this cache has created in memory and disk. And this is what is the storage level for the data frame and data set in PySpark. So if you run cache in data frame and data set in PySpark, the default storage level is memory and disk. But for RDD, it is memory only. Now, there's one more question. Consider we create a data frame out of cache and try to do the count of that particular data frame. And then we try to read the original data set with the filter condition. What will happen in that case? Before we do that, let's remove the cache first. So to remove the cache, you need to write df.unpersist. If we run this, again we get a data frame. Now let me go back and go to the storage tab. See, the cache is removed. Let's go through our example. Consider we create a data frame df cache here. And rather than doing count here, we will do the count of dh cache. So I'll remove this here. And in the next step, I'll do df underscore cache dot count. Now, after this, if we try to read from the original data set, which was df, what will happen in that case? Take a moment and try to guess. Let's see what happens. So I'll run this cell first. Nothing will happen because to cache, we need to run the count. So we'll run the count again. Now, since we got the count, it means our data is cached. Now, it is not necessary that you only need to do a count. You can also write the data set with no operations format that we have discussed in our last session, if you remember. So let me go back and see the storage level. Yes, our data set is again persisted. You can see the same deserialized, and this time again the memory and disk data is there. So let me go back, and this time I'll again run this where query. But this time we will refer the original data frame, which is df, rather than referring the df cache. So what will happen in this case? Let me run this. You see, we have got the data instantly. If I go back and if I refresh this SQL data tab, you see this source string. And again, this has completed in 0.1 second. So we can understand that this is running from cache. Let me go back and see this. See, the scan CSV is 0. Again, this is an in-memory table scan. So this is how Spark understands. Spark keeps a lineage and knows whenever you cache a data and you refer the original data frame, it will try to read the data from cache rather than reading it from the original data source. So in this case, even if we trigger any query against the original data frame, which was df, it will try to refer the cache. And this is the reason why it is always told that the cache should be done properly. Consider a case where you have done the cache on a particular piece of data. Let me put a filter here. Say you put the cache as amount greater than 100. So let me first unpersist the data. Now if I go back and if I refresh, the cache is gone. So let me come back. Now, if I cache here, you can see the cache will happen on partial data. Where is the amount greater than 100? Let me run this and let me again run the count. Now, you can see a different count here because this is on the filter data. Let me go back and refresh the storage tab. You can see this time it has fitted all the data in memory because the data volume was less. There is no spillage on disk. Now, if I come back and if I do amount, which is greater than 50, for example, because we have done a filter on amount greater than 100. What if I do an amount greater than 50 on the original data frame? Let me run this. It has completed successfully. Let me go back and refresh this. Let me go to the source string. You can see this time it has hit the CSV file. The reason is the filter has triggered a partial cache. So now if you point the original data source, that cache will be invalidated and Spark will again read the data from the original source, which is the CSV file. And in this case, you can see there is no reading from cache happening. It is reading from the CSV file and it is going down to the collect limit. If you want, you can see the job as well. Let me go to the job. If you see, there is no cache involved. It has invalidated the cache. So if we go to the storage tab, you can see we have an amount greater than 100 filter because that is what we have created. But if we put a different filter, which is greater than 50 on the original data source, Spark will direct read the data from the original source. And this is why partial cache is very dangerous if you are not doing it properly. Now that we have understood how Spark works with caching with a full data set and a partial data set, let's see the different storage level involved with caching. Now, if you can see on my screen, there are multiple storage levels that are involved with caching. Now, for cache, we know the default is in PySpark, memory and disk, and that for DataFrame. But if you want a different setting, you can use the persist method. To do it, for example, we can write df underscore persist, and we can use the original DataFrame, which is df dot persist. And in this, we can specify storage level. To do that, first we need to import PySpark. So I'll write import PySpark, and now we can specify the storage level. So we'll write PySpark dot storage level dot the storage level we need. For example, consider we need memory only. For that, we can put it like this, memory only. But before we can do that, let me unpersist the existing cache. So I'll run this. If I go back and refresh storage, the cache is still there. To remove all the cache, you can write spark dot catalog dot clear cache. If I run this and if I go back and refresh again, you see all cache is gone. Now, let me run this. And if I come back, nothing will happen because we have not triggered any action. So let me trigger the action. So I'll write df persist dot, this time I'll use the no operation, right? So I'll write write dot format and we will use the no op, and we know that no op will do nothing. It will just simulate. So I'll write overwrite and dot save. So if I trigger this, let me go back and run the storage, and this time you can see the memory is serialized. The reason is cache puts the data as unserialized, but if you put it with persist, the memory, the data will be serialized in the memory. And you can see the size of the data is 217 MB in memory. There is no spillage on disk. Now, there's one more thing that you might be thinking. How did Spark fit all the data in memory right now? Because in last time when we saw that in cache, it was spilling some data to disk. The reason is the data here is serialized. So you have to be very sure when you see this. For cache, the data was unserialized. This is why the data was getting spilled to disk. But when Spark is encoding this in JVM serialized method, it is putting every data in memory because it is able to do that. Now, what will happen if Spark storage setting is memory only and the data is still not able to fit in memory? And that will be a time where you will see an out of memory error. So be very sure of the storage level setting you have mentioned in your jobs. It is very important the size of data that needs to be fit in. If your size of data is greater than the memory that you have specified, always remember to use memory and disk. Now, for memory only serialization, this is for Scala or Java jobs. For PySpark, whenever we do memory only or memory and disk, by default the data is serialized. So you cannot use memory only serialization or memory and disk serialization in PySpark. Now, what does this memory only do? Let's do it. Let's put memory only 2 here. And before that, let me clear the cache. So if I run this and go back and refresh, the cache is cleared. Let me run this and this time again the overwrite. Now if we come back to the storage and refresh, you can see this is 2x replicated. It implies this is replicated twice in all the executors. Now, before we can conclude today's session, the important difference between cache and persist method you need to keep in mind. In persist method, you can define the storage level you need to use. And in cache, the default storage level is memory and disk, and that too, the data is deserialized. Today we'll look into one of the most important topics, which are distributed shared variables. Spark has two types of variables that it has to offer in distributed manner. The first one is broadcast variable and the second one are accumulators. Now, both have a great deal of significance if you understand them very perfectly. You can tune some of your jobs using these variables. Before we can begin, if you have not watched our previous video, I would recommend you to go back and watch our playlist. You can click the I button at the top. So, without any delay, let's begin. Now, before we can understand what are the different type of distributed shared variables we are going to look, we are going to use the employee records.csv as a dataset today. It has many columns like first name, last name, job title, and in the end we have salary and department ID. This will be the dataset that we will use today for our demonstration. Now, for today's session, I'm going to configure my cluster setting as Spark Core Max as 16 and the core executor as 4. This will enable to spin up a cluster with 4 executors and 4 core each. The memory setting is closed at 512 MB. Let me generate the Spark session object first. Our Spark session object is generated. Let me go ahead and refresh our Spark UI. Okay, our Spark UI is up and running. Now, before we understand the broadcast variable, let's understand the problem statement that we are going to use. Since we know we have an employee record set where we have ID as a column. Consider a case we want to populate department name according to the department ID. What are the options that we have? First option, we create a department data frame and we join it with the employee data frame and populate the department names. Now, the problem with this is this will involve shuffle. Then what can be the second approach? The second approach is we can create a lookup variable like this and we can send it with an UDF or a map operation. But the problem here is if we create a variable will be serialized along with the task. So every time when this task would be deserialized, this variable would be deserialized. And this deserialization and serialization will happen row by row. So what is the problem here? The problem is, since this looks like a small variable, this is easy. Consider a case where you have a lookup table or a machine learning model that you need to use. In that case, it will create a bottleneck, right? So for this comes in rescue is broadcast variable. Benefit of broadcast variable is it is sent over and cached in each of the executor. So whenever we create a broadcast variable, it is sent to all the executors that we have. And this is cached in all the executors. Now, since we have the partitions of data residing in all the executors, they can use this broadcast variable which we have sent and can join or do the operation that is required. And once this is done, all the executors can send out the result sets separately. They don't need to shuffle data in between them. And this is why it is known as distributed shared variable, because this particular piece of variable is distributed across the cluster. Now that we know what is a broadcast variable, let's see this with an example. So for our example, we have created variable which is a dictionary with the department ID and the department names. Now, this is something that we'll use to join with the department ID in the employee data and we'll try to populate the department data. Now, to use this variable and send it to all the executors, we need to broadcast. And for that, we need to create a broadcast variable. So to create a broadcast variable, let's name the broadcast variable as broadcast department names. And to broadcast this variable, I'll write spark context dot broadcast. And we'll put the variable name, which is department names. Now, let me run this first and let me run this second. Now, we have created this variable. If you want to see the type of this variable, in Python, we can just write type of this variable, which will give us the type. Now, if you see, this is a broadcast type variable. Now, if you want to see the value of this broadcast type variable, you can just write types dot value, and it will show you the value of that particular broadcast variable. Now, if we go back in our jobs and refresh, still nothing is there because we have not executed any action yet. Now, as per the theory, we know this variable would be cached in each of the executor. But to use it, let's create a UDF. So for that, I'll import the UDF functions. I'll write PySpark.sql.functions import UDF. And let's create our UDF. So I'll write def and we'll get department names. And for that, the input would be department ID because we'll look up on department ID and we'll populate department name. So I'll write like this. And to look up the value, we need the broadcast variable, which is broadcast variable department names. And I'll put dot values dot get. And this will pass the department ID, which is the key for this broadcast variable. Now, this is a function now. Let's create it as UDF. So I'll just write UDF. Now this is an UDF. Let me run this. Our UDF is ready. To use this UDF, we'll create a new column in the employees data frame. So I'll create EMP final as a data frame, and I'll use the EMP data frame with which I'll create a new column called with column, and the name of the column would be department name, and I'll use this UDF. So I'll put this get, and I'll pass the column name, which is department ID. and we created our department name column. Now before we can run this, let me import the column as well. So I'll put the column as well, and let me rerun both of them. Now if I go and refresh, nothing will be there because I've not called any action yet. Let's view the data. So to do that, I'll write emp final dot show. Okay. Okay, we see the department name as null. What might be the problem? So understand the problem. We have not done the return here. So I have to write return. The value should be written. Let me rerun this, and run this again. Let me zoom out for you. Awesome. If you see, the department names are populated correctly this time. So let me go back and refresh the job. Since we have run the show 2 times, you can see both of them. Now let me just expand this for you. And if you see, this whole thing is happening in a single stage. There is no shuffle involved because we have distributed broadcast variable in each of the executor, and that is being used here with the help of an UDF. We are not using any operation that is leading to shuffle. And this is how a broadcast variable can be helpful when you need to supply some lookup table or a machine learning model to your data frames. Now, there is a very good implementation of this broadcast variable that we know of, which is broadcast joins. That we will see when we will optimize our joins. We'll see how a table being broadcasted in order to make and optimize the joins. Okay, now that we have understood the broadcast variables, let's look into the other type of distributed share variable, which are accumulators. Now, to understand accumulators, let's consider a use case where we need to calculate the total salary of a particular department 6. Now, we know that the data is distributed into multiple executors for that particular department. So the data will rely in different partitions in each of the executor for that particular department. And in order to do the count, we have to bring in all the data from all the executors to a particular executor. And here we need to do the sum. Now, if you see, we have involved shuffle in this operation. And this brings us to one more question. Is there a simple fault tolerant way to do this operation? The answer is yes. We have another variable called accumulators, which will be processed row by row in a distributed fashion in each of the executors, and that will be updated every time a row is processed. And once this particular variable is updated from each of the row that is lying in all of the executors, we can get the final value for that accumulator, which can provide us the sum which is required. I know this can sound confusing for the first time. Let's see this with an example. Let's first try to calculate the total salary for department 6 in the usual way. To do that, let me import the sum function first. So to do that, I'll write PySpark.sql.functions import sum. And now let's write our aggregation. For that, I'll use the emp data frame. So I'll write emp.group by. But before that, let me put the filter, which is where, and we just need it for department 6. So I'll write department ID equals to 6. And we will do on a group by of department ID. And we'll do the aggregation. I'll write AGG, and we need to do the sum. So I'll write sum, and we need to do the sum of salary. So I'll put salary. Okay, and I'll just do a small so here. So I'll run this. Let's wait for this to complete. Awesome. We got our sum of salary here, but this is in exponential format. Let me cast this. So I'll write dot cast here, and let me do it in long. So I'll write long. Let me rerun this. Nice. We got our sum here. But if I go back and refresh my Spark UI, let me go into this. Now, if you see, there is an exchange involved, which implies there is a shuffle done. You can see AQE shuffle read. This implies there was a shuffle involved, right? We can also go into the jobs and see that same. So I'll go into the job and I'll click on the first source string here. Here the exchange happened. Let me go back and see the second one. So this is the second one. If I go back, you see the data is read in the first, and then all the data is brought into one task to do the count. Now, how to do this in one more way, which is using the distributed variable accumulators. Now, to define an accumulator, say department sal, I'll write spark.sparkContext.accumulator. And this will create our first accumulator named department cell. Now we need to provide the default value. Since we are trying to calculate a salary, let me put the default value as 0. I'll run this. If I go back and I'll refresh the job tab, you'll see nothing. 5 is the highest job ID here. Okay. Now that we have created our accumulator, let's write our for each function. This for each function will allow us to go through all the records for that particular data frame row by row. So to do that, I'll write emp.for each, and in this we'll write our inline function. So I'll write lambda, and we need to parse each row, right? So it will be row by row. So our lambda row, and then we need to pass the department ID and salary of that row to a particular function which will add that to our accumulator. So consider our function is calculate salary. So I'll write calculate salary and will pass department ID. So I'll write row dot department ID, and again of that row will pass the salary. So I'll write row dot salary. Now these are the columns that we have for that particular row, right? Now we need to define this particular function first. So what we'll do is I'll copy this definition here and I'll write the function first. So I'll write def and I'll put that function which is here, and I'll remove this row dot. I'll just make it department salary and department ID and salary. And now we'll check if the department ID is 6, then we'll add it to accumulator. So I'll write if department ID is equals to 6, then we'll add it to the accumulator. So I'll write department sal dot add and we'll add it to the salary. Okay, let me run this. Let's wait for it. Awesome, this completed. Let me go back and let me refresh the job tab. If you see this for each, it completed with 16 tasks. And if I open this, you'll find it in a single stage. It is all map operation and map partitions because it is happening row by row into the same data frame. It is not doing any shuffle. So this is happening in all of the 16 executors in distributed fashion, right? Let's see the value of our accumulator, so which is department sal. So I'll let department sal dot value. Let me run this. Awesome, we got the total salary. Now if you see, this is same as that what we got in our data frame previously. I hope you have understood how broadcast variable and accumulators are used. This was just a simple use case. You can use it for many other use cases, and there are a long list of use cases for these two variables. Today we'll cover one of the most important topic in Spark, how to optimize joins. Now, optimizing joins can lead to performance benefit in your job. Today we will see how we can optimize a big and a small table join and a big versus big table join. We'll also understand the different type of joining strategies that Spark use: shuffle hash, short merge, and broadcast joins. We will see how bucketing strategy can load your data faster. And we will also use Spark UI to understand the data read by the task or partitions in join. Now, understanding and optimizing joins is a very important topic, and I want you to pay very close attention to it. Make sure you understand this concept very clearly. So, before we can begin, let's understand few concepts in theory so that it will help us in our hands-on session. Now, before we can proceed and optimize joins, we need to understand how joins work in Spark. Consider we have two tables, sales and city. And for sales and city, we have a common column called city ID. And we will join both of this table, sales and city, using this city ID column. Now, here is the data for city ID column in both the tables. Now, if you understand data warehousing concept, you can understand city ID as a dimension and you can understand sales as a fact table. Now, we have the key columns as city ID in both the table, right? And we know Spark reads data as partitions. So consider we have a cluster where we have 4 executors in the cluster, 1, 2, 3, and 4. If Spark wants to join the data, first of all, Spark will read the data in partitions. So consider it is reading the sales data like this. First 3 keys goes in the first executor. The next 3 goes in the third executor. The second last 2 goes into the fourth executor, and the last one goes to the second executor. Similarly, it reads the city data. Consider it first and second goes to the third executor, third and fourth goes to the fourth executor, and the fifth one goes to the second executor. Now, Spark has completed reading the partitions, right? But if you see, the first executor does not have any city ID, whereas the second one has the city ID as 5 for cities, and for sales, it has the city ID as 2. So the joining is not possible within the executors, correct? So in order to join the data, first Spark has to shuffle the data in order to bring similar city IDs in the same executor. So on the left hand side, we have the data from the sales, and on the right hand side, we have the keys from the city, right? Now Spark will shuffle the data. In shuffling, what Spark will try to do is, it will try to bring similar keys that we have used for joining into the same executor. So consider it brings 1 after shuffling from here. Similarly, it pushes the 2 to this executor. And once the data is shuffled for the sales, consider it will also shuffle the city data. So it will bring 1 and 2 from this to the first executor. It will bring 3 and 4 from fourth executor to third executor, and it will bring 5 from here to here. Now, if you see, 2 still needs to go to the second executor. Okay. Now, since the data is shuffled properly, Spark can join the data properly now. And this is how Spark joins the data. Now, if you see what are the steps involved, first Spark read the data, then it did the shuffle, and in the end, it joined the data. And after that, you might need to write the data or you do the count of the data. This is a basic concept of joining of data in Spark. Let's understand the different joining strategies that Spark offers. Now, let's understand what is shuffle hash joining strategy. Now, in shuffle hash strategy, the steps are like this. First, the data would be shuffled. Second, the smaller data set would be hashed. And third, the hashed data set will be matched with the big data set. And fourth, the joining will happen. Now, in our case, the smaller data set is city. So once both the data sets are shuffled, the smaller data set, which is city, will be hashed. And this data set will be matched against the bigger data set, which is sales in our case. And once that matching happens, the joining will happen. Now, in this case, if you note, there is no sorting and only hashing is happening. So this is a reliable strategy when you have at least one smaller data set which can fit in memory. So let's see the sort merge. So in sort merge, the first step would be shuffle. So both the data sets, city and sales, will be shuffled. After shuffling, there will be a sort step. The sort step enables that the keys that we are going to join are sorted properly. And once the keys are sorted, those keys will be joined, right? And third will be merge. And thus, this is known as sort merge, right? But in this, we have a step called sort. And this is why it can be an inefficient join if not used properly. And where is this useful? When we have two big data sets to join. In that case, you can prefer sort merge join. And the third one that we are going to see is broadcast join. In broadcast join, we have a good performance benefit if we can broadcast at least one data set. Now, if you have seen our previous video, you can understand what is broadcast because we have talked about broadcast variable in our previous video, right? So in broadcast variable, there is no shuffle step. The smaller data set is always broadcasted to all the executors, right? Once that data set is present in all the executors, the joining happens, which is the hash joining, broadcast hash joining. Okay, in this you can consider one big table and one small table. Now the benefit is the small table will be broadcasted to all the executors and then we can join it with big table very efficiently. And this is one of the important joins that we have right now, which gives us a performance benefit. And again, this is one of the most important interview questions that is being asked everywhere. So you need to keep in consideration when you have a smaller data set to join with a bigger data set, you can always broadcast the smaller data set and make the join efficient. But again, there is a limitation to broadcast join. The default value for the smaller data set should be 10 MB. Now this can be increased to 8 GB. But if you try to broadcast a bigger table, the join will fail and you will see out of memory errors. So you have to be very careful. If you have a smaller table, then only you need to do the broadcast. And you have to be very careful about the size of the table that is being broadcasted. Now that we understand all the three types of joins, let's go ahead and run our code to understand how we can optimize different types of joins. Okay, now that we have understood joins in theory, let's see the data sets that we are going to use today. Let's first start with the sales data. So for that, I'll write head new sales.csv. So if you see, we have a city ID column in this data set that we will use. Again, this data set has approximately 7 million records. And for the city data set, we have around 2 million records. So you can understand both of these data sets are big. Okay, and similarly, we have employee and department data sets that we have used in our previous sessions as well. Now, before we switch over, let's see the city data that we have. If you see, we have the city ID column here as well. Now, we are going to use city ID from both the sides to join the data sets for sales and cities. So I'm back in my Jupyter notebook. Now, before we can execute, we need to create our Spark session. For today's session, I'll be creating a cluster with 16 max cores and 4 executor core each. This will enable us to create 4 executors with 4 cores each, right? And again, 512 is the max memory for each executor. Let me create the Spark session first. Awesome. Our Spark session is generated. Let me go ahead and refresh the Spark UI. Okay, our Spark UI is up and running. Great. Now, for today's session, I will disable AQE and broadcast join. We will do those specifically, but in order to understand it better, let me disable it. Okay, this is done. Now, joining small and small table is easier. We don't need to see optimization when we join small versus small table. So we will start with big versus small table. So here we have the employee data in CSV. The number of records in employee data set is 10 million. And again, the number of departments that we have in employee is 10. Similarly, we have the department CSV data for which we have around 10 records, which is for each of the department. Now, I can open the department data and I can show it to you. We have 10 records for each department. But if we open the employee record, you will find department ID column in the employee records as well. Now, for joining employee and department, we are going to use the department ID. Now, I'm not going to write reading data today because we have done this from last few sessions. So I'm going to read it as CSV. I've provided the schema. We have header in the file and we are reloading the employees record CSV. So I'll run this first. Now that we have specified schema and we have not triggered any action, there should not be any jobs. Okay. Now, similarly, we'll read the department data. Let me run this again. We have the header option true for department as well. Okay. Let me go ahead and refresh. Nothing should be there because we have not triggered any action yet. Okay. Now, first we will join employee and department data normally. We will not use any broadcast join first. So to do that, I'll write df joined is equals to, and we will put emp dot, will join the employee data and we'll join it with department. Now, we'll write the on condition on which the join will happen, which is emp dot, I'll copy the department ID column and which is equals to, we also have the department ID column in department. And now we'll specify the how. In all the cases, we'll do left outer join because employee is a bigger table and department is smaller. We want to retain all the records from employee, so we'll make a left outer join. So I'll write left outer. Now, this is our joining condition. Let me run this. Nothing will happen yet because I've not called any action. Okay. Now, for today's session, for benchmarking the data, I'll write all the join data sets in NoOp format. And we have seen how NoOp works in our previous session. So I'll write the df joined in the format of NoOp. And we'll put the mode as overwrite and we'll save the data. Now, once I trigger this, this is an action and it will create a job. Now, NoOp is something that will simulate and read the whole employee and department data frame and simulating the whole data set, allowing us to benchmark the timings and understand the joins better. So I'll do this. Okay, the writing of data is complete. Now, before we go and check the Parquet, let's check the explain plan. So for that, I'll write and we'll just see the physical plan. So I'll run this. Now, if you see the joining strategy that has been used is sort merge. Now, there is exchange in both the sides. You see this? Now, the file has been read first, the data is filtered, and then there is an exchange happening on both the sides. And after that, there is a sort happening, which is as per our sort merge join, right? Let's go ahead and see the Spark UI. So I'll go and refresh the data frame tab. Let me expand this. If you see, on the left hand side, we have 10 million records read for the employee data, and we have 10 records read for the department data. Now, if I scroll down, you see exchange at both the sides. This is because the department data and the employee data are exchanged for joining. And once this is done, both the data sets are sorted, and then the joining is happening for sort merge. Now, let me go to the job first and show you how the shuffle worked. If I come to job, this is the DAG that has happened. Both the data sets are read and then the exchange happened and then the joining happened. If you see, employee data took 16 tasks to read and the department took 1. Both of them wrote the shuffle partitions, right? And then this 200 shuffle task read the shuffle data and wrote the data. And this is how a simple sort merge join works. Okay, now we know that if we have a bigger table and a smaller table, we can do a broadcast join. So to do a broadcast join, what I'll do is I'll import the broadcast from PySpark SQL functions. Let me do that. Now I have imported the broadcast. I'll just change the joining condition by broadcasting the department. So for that, I'll write broadcast and I'll put the department into the brackets. This will inform Spark to broadcast the department data now. Now let me run the join again. And again, I'll do a no op write. Okay, it completed so quick. Let me run the explain plan again. Okay, this time if you see, we have a broadcast hash join. Now, if you see the file scan here, this is where we have the CSV data that is broadcast exchanged. It means that the same data is broadcasted. Okay, let me go and refresh the Spark UI first. Okay, if you see the difference, first in the sort merge join, the job took around 57 seconds and in broadcast join, it took just 8 seconds. Let's go ahead and see the DAG first. Now, if you see, we are reading the department data here and 10 million records of employee. Okay, here the data is broadcasted, and when the data is broadcasted, this data is present in all of the executors. So there is no shuffle required, and we can directly do the broadcast hash join here. Right? So we have avoided shuffle in case of broadcast, and this is very important. If you have a smaller data set and a bigger data set, and the smaller data set can be broadcasted, you should always prefer broadcast hash join. Okay, let's go back and check the job. So I'll go and I'll open the first job that is here. Now, if you see, it has just done the broadcast in the first job. Okay, and if I go to the second job, it has scanned the CSV and 16 tasks has processed the data. There is no shuffle involved. And this is how we avoided shuffle using broadcast join. Okay, now that we understand how to optimize a big and a small table, let's see how we can optimize to big table joins. Okay, so we have sales data here and city data here. For sales, we have around 7 million records, and for city, we have around 2 million records. Both the data sets are huge. We will use city ID as the joining column from both the sides. Okay, so first of all, this is a CSV file for sales, and this is a CSV file for cities. There is no bucket, nothing involved, no partition, no bucketing. Let's read the data first. So I'll run this, and then I'll run this. See, there is no action. So if I go and refresh, nothing will be there. Okay, we have read both the data. Now, first we will do the default join. For that, I'll write df sales join, and I'll write sales join, and we will join it with city, and on is sales dot, we have city ID both sides, so I'll use city ID equals to city dot city ID, and again the how would be left outer because we need to read all the data for sales, so we'll put left outer. Okay, I'll run this. Nothing will happen because I'm not called action. Let's again write this in NOAA format to see what is happening. So I'll write df. Okay, let me run this. Okay, the joining completed. Let me go back and refresh the Spark UI. I go and expand the DAG. You can see we have around 2 million records here. 7 million is read from the sales. And again, there is an exchange happening here. And after that, a sort and then a sort merge join. So Spark has preferred doing sort merge join for this. So let me go ahead and show you the job here. Let me expand the job. You can see 16 tasks used to read the sales and similarly 16 to read the city data. Both the stages are writing shuffle data and that is being read by 200 tasks. That is the setting for our default Spark SQL shuffle partitions. So that is being read and the data is being written, right? We can see the same in the DAG here as well. Now it brings a question here. What if we try to broadcast the city? Now we know that we don't broadcast a bigger data frame, right? But let's do it. Let me run a broadcast here to make you understand what will happen when you do a broadcast of a bigger data frame. So I'll write broadcast and I'll do the broadcast of the city here. Let me rerun the joins again. Let me refresh the Executors tab. Now, you see the job started failing. You can see the lot of failed tasks that is happening here. The reason is we are trying to broadcast here a bigger size of data. You can see the input has come up to 1.1 GB and this is what is leading to failure of tasks. Okay, so let me kill this job. Okay, now that we have killed our last job and restarted our Spark session, let's understand what is bucket. And this time we are going to use bucketing strategy in order to make our joins. Now, let's understand how bucketing works. So we have sales and city dataset, and we have the city ID column with the values 1, 2, 1, 3, 4, 5, 1 for sales and 1, 2, 3, 4, 5 for city. So consider we want to divide it into 4 buckets based on the city ID column, both for sales and city. Okay, so in Spark we have a hash mechanism called murmur. Based on the column that is being selected for the bucketing, it will try to assign that particular ID into a particular type of bucket. Okay, so consider we want to divide the data in 4 buckets for sales and city, correct? First, the sales data, 1 will go to the first bucket. Similarly, 2 will go, say for example, to the third bucket. Similarly, 1 will again go to the first bucket, 3 will go to the second bucket, 4 will go to the fourth bucket, 5 will go to the second bucket, and 1 will again go to the first bucket. Similarly, for city, consider 1 will go to the first bucket, 2 will go to the fourth bucket, 3 will go to the third bucket, 4 will go to the fourth bucket, and 5 will go to the third bucket. Now, if you notice something, that 1 and 1 has always gone to the first bucket because this hashing algorithm works on the same city ID column with the same value. So whenever we put 1, it will always go to the first bucket irrespective of the data sets. Similarly, 2 has gone to the third bucket and similarly 4th has gone to the fourth bucket. Similarly, 3 and 5 has always gone to the second bucket. Now, the data is broken into 4 buckets, 1, 2, 3 and 4 for both sides, right? And this is what happens. So when we try to join a bucketing data, these 2 buckets will be read by the same executor. Similarly, these 2 buckets will be read by the same executor. Again, this 2 will go to the same executor And finally, the fourth bucket on both sides will go to the same executor. Now, since both the same type of bucket data is in the same executor, the joining can happen very efficiently. There is no requirement of shuffle if the data is bucketed properly, but the bucket numbers should be same. So in this case, if you see, both the buckets, one from both sides, will reside on the same executor. Similarly, 2, 3, and 4. And in this case, bucket numbers are same. And this is very important while we are joining data with buckets in Spark. Now that we understand buckets, let's write our sales data into buckets. So we have our sales data here, right? Let me rerun both the data frames here. Let's read our sales data frame and write it as buckets. Now, bucketing can only work when we save the data as table. Now, to write the data in bucketing, let's write sales dot write dot format. Format is the data format in which we'll write. We'll write it as CSV files. So I'll write CSV dot, I'll put the first option, which is header, and I'll mention it as true. Now before that, I'll bucket it. So we have to bucket it on city ID because that is our joining column. So we'll write bucket by, and we will bucket it into 4 buckets, and we'll put the column which is city ID, which will be used for bucketing, right? And we'll again put one more option where we will specify the path where we have to write the data. Since we are saving it as table, so we specify the path. I'll write data, and I'll write it as save as table. We'll name the table as sales bucket. Okay, this is done. Let me put mode as override. So I'll write dot mode and I'll put it as override. Okay, let me run this. Okay, the writing of data is complete. Let me open the sales bucket.csv folder. Now let me expand the side panel. Now, if you see closely, for each partition of data, we have 4 buckets created because we had around 16 partitions of data. So for each partition, 4 buckets. So the total number of buckets that we have is 16 into 4. Okay, now if you can see the bucket number 0000, 0001, 0002, and 0003. Similarly, for partition 1, you can see 4 buckets, and partition 2, 4 buckets. Similarly, up till 15, we have 4 buckets each. So that is 16 into 4 buckets, right? Now, similarly, we'll write the city data as well. So I'll copy the same query now, and I'll just change it here. So I'll write E, which is our data frame here, city, and we will use the same format. We will bucket by 4 and city ID here as well. We will change the path here. So I'll write city bucket and I'll make the name as city bucket. Let me run this as well. Awesome. This also completed. Let me go to the data set. Let me go to the city bucket. If I scroll to right, you can see again 4 buckets for each of the partition, right? So we have same number of buckets, 4 and 4, based on the city ID that we have for each of the partition, right? Now we have created 2 tables here, sales and city bucket. Let me see those tables. So to do that, I'll write spark.sql and I'll write show tables in default, which is our default database. Because we have not created any database, this will be in default. So I'll write show. If I run this, see, we have both the tables here. Now that we have created our sales and city bucketed data, let's read that and see how bucketing can improve the sort merge join. To do that, I'll create a data frame called sales bucket, and we will read it as Spark. Since we have the table, so we will read it from the table. So I'll read and I'll put table and I'll name the table, which is sales bucket. Similarly, I'll read the city bucket as well. So I'll write city data, which is in city bucket. So I'll write city bucket. And this is the same we are going to read. So I'll put it here as well. Let me run both of them. Okay, both the data frames are created. Let me join this. So to join, I'll write df joined bucket and I'll put it as sales bucket dot. So let me run this. Okay, this is done. Let me write the data set in Nova formats. I'll just copy this from top. So come here, I'll copy this right from here and I'll paste it and I'll run this. Let's wait for it to complete. Okay, it completed. Now let me go back and refresh this. Okay, you can see we have taken 22 seconds to complete this. Now, if I expand this, You can see there's no shuffle involved. We are reading the sales bucket and city bucket, and then we are joining it. Now, before I go back, let me show you the whole plan. So I'll open this. Now you see bucketed data for sales is red. Similarly, the city bucket is red, and we are doing a sort for the city bucket in the same, but we are not doing any shuffle here. Both the data are being sorted, but there is no shuffle step. You cannot find any shuffles or exchange step, right? And the sort merge join is happening, right? So we have optimized this join. Now see the timings. It took around 22 seconds to complete the bucket join, right? But the same join, when we didn't do without bucket, it took around 2.2 minutes because there was shuffle involved in this join. So if I open this, you can see shuffle is there. But for the same data set, if we have a bucketed data, there is no shuffle. And this is how bucketing can improve your performance. But there is some catch to it that we will discuss. So before that, let me show you the explain plan again. So I'll put it here and I'll put explain. And if I run this, you can see sort merge join. We have short step, but you cannot find any shuffle step here. Both the data sets are filtered and sorted, but there is no shuffle involved. Great. Now, there is one more thing I want you to know. Now, let me go back to the tasks for this join. So I'll come here and I'll expand this. Okay, you can see the number of tasks that are being used is 4, right? Because we had total 4 buckets. Now, each task is reading a set of buckets from both the data sets. You can see the record count here. Let us verify this. So I'll come back to the terminal here. Okay, I'll change it to sales bucket.csv. Now, let me do a lslh to show you the data set. So we can see all the data sets, right? So let's see the 0th bucket for all the partitions. So to do that, I'll write ls minus l and I'll put part and I'll put a star. Then I'll put the 0th bucket, which is this. I'll copy this and I'll put it here. Now, if I run this, you can see all the buckets for that, right? Now, let me count the total number of rows for sales. So what I'll do is I'll put WC minus L and again I'll put this here. And let me run this. Let me copy the total number to a calculator. So I'll put it here and I'll put a plus. Same thing we'll do for the city. So we'll try to see the 0th bucket for city. What is the total number of records? So I'll change it to city bucket and I'll run the same query. For 0th bucket, what is the total number of rows? So I'll run this. I get this number of rows. So I'll copy this. So I'll add both the rows. I'll put it here. Now you see 20, 26, 206 minus, since we have header in all the files and we have 16 partitions for city and sales, so we'll minus 32 records, right? So we'll get 20, 26, 174. Now let me go to the first partition. You see the number 20, 26, 174. So first partition read all the 0th bucket records for both sales and city. And once it read the data, it joined the data and it wrote the data. Now, one thing to notice here is spill in memory and spill in disk. This we are going to see in our later video of optimization for spillage. Now, we have done 4 bucketing here. So you can increase the number of bucketing and you can optimize the performance further. Now, how to decide the number of buckets? That completely depends on how much volume of data you have. Now, if the joining column is different than the bucket column and we have the same bucket size, means both the data sets with same number of buckets, then we will have shuffle on both the sides because the joining column is different. You need to have the same joining column that is of the bucketing column, right? The second condition is if the joining column is same on the both side and you have only bucket in one table, then you will see shuffle on the data set which is not bucketed. Okay. Now, if the joining column is same and you have different bucket size, for example, the sales have 16 and the city has 4. In that case, whatever is on the smaller bucket side, for example, here city is smaller, so the city will see the shuffle. Okay. Now, if you have joining column same and same bucket size, then you will have no shuffle and you will have faster join. Okay. So there are a few more points that you want to see. It is very important to choose the correct bucket column and the bucket size. Now, you have to decide the bucket size very effectively. The reason is if you decide and make the bucket number too high, then you will have a small file issue. What is small file issue? Is you will have too many number of files and the record set and the data set in these files are very less. So you want to avoid that. You want to make sure that you have a sufficient number of records in each of the file and you don't run into small file issues. And again, if you have both the data sets as small, prefer shuffle hash join. Today we are going to discuss one more interesting topic, which is dynamic allocation on Spark. Now, Before that, if you have not seen our previous videos, I would recommend you to go back and watch our playlist from beginning. Today we will see resource management on cluster. We'll also understand what is the difference between static and dynamic allocation. We will see how to configure dynamic allocation on a standalone Spark cluster. We will also understand how dynamic allocation is different than Databricks cluster scale. So without any further delay, let's begin. Consider we have a cluster with 2 worker nodes. And for each worker, we have around 8 GB of memory and 8 cores each. Consider user 1 has an application app 1, which requires a resource of 6 executors with 2 cores each, and each needs 2 GB of memory. So once the user executes this job, this app will communicate with the resource manager to get the required resources, right? So consider the resource manager allocates the resources like this. So first it allocates the resources here and again the remaining here for the first app. So out of this, a total of 6 into 2, that is 12 cores are exhausted, and 6 into 2, that is 12 GB of memory is already allocated for app 1. Now comes another user who runs app 2, which requires 6 executors with 1 core each and 1 GB of memory. So given the app 1 request for the resources, our cluster does not have enough resource now. Correct? Because the required amount of resources is already captured by app 1. Even if it might not be using all of the resources, but it is still capturing the required amount of resources, and it will not release the resources until app is terminated or the app succeeds, right? So in that case, the app 2 has to wait for the required amount of resources. Now, this type of allocation of resources is static allocation, in which we already define the amount of resources that is required by our application. And even if the app is not using that much of resources, it will still hold the resource in the cluster. Now, to avoid this problem where multiple users are using the same cluster or multiple apps are running on the same cluster simultaneously, there comes another scenario called dynamic allocation. Now, the benefit of dynamic allocation is the executors will be scaled up and scaled down. When we say scale up and scale down, it implies whenever an executor is required, it will be procured. And as soon as the work is done for that executor, it will be scaled down. The resources for that particular executor will be released. Similarly, another app running on that same cluster can use or consume those resources. Now, this is one of the best feature of dynamic allocation. Now, in order to make dynamic allocation work, we need to set up some Spark properties that we will see today. I am in my Jupyter Lab environment. Let me go back and show you the Spark standalone cluster that I am using. This is my standalone cluster. So in my cluster, I have total 16 cores and 13.3 GB of memory. And if you see, I have 2 workers up and running. Each of the worker is having 8 cores and 6.7 GB of memory. Now, whatever executors are scaled up and scaled down will be created in this worker nodes. Now, before I discuss the Spark properties that we need to enable for dynamic allocation, we need to keep 2 points in mind. In order to make dynamic allocation work, we first need to enable dynamic allocation. And the second property is we need to enable an external shuffle service. Now, external shuffle service are something that would be required in order to preserve the shuffle data so that the scaled up or the newly created executors can access to that shuffle data. Now, Spark also provides you an option to provide shuffle tracking enabled. Now, if you have shuffle tracking enabled, Spark will make sure that the shuffle data, whatever is written, are being tracked and made sure that the executors have access to this data. So let's discuss the properties that we need to set in our Spark session to work with dynamic allocation. If you see, I've configured the master as Spark. So I'm running this in a standalone cluster. So the master is pointing to the Spark cluster that I have. Now, the other property that you see is Spark executor cores. This will enable that the executors that will be created will have max of 2 cores. Next is the memory. And the executors that will be created will have 512 MB of memory. Now, following all the properties are for dynamic allocation. Now, we first need to enable dynamic allocation. So we need to set spark.dynamic allocation enabled as true. Once this is done, the next step is to set the minimum number of executors. This is the minimum number of executors that your application can have. And the next one is max executors. It means it is the maximum number of executor that your application can have. So in our case, I have set it to 5. It implies the maximum number of cores that you can have is 5 into 2. And the maximum number of memory is 5 into 512 MB. The next property I have configured is initial executors. It implies as soon as the Spark session will be created, one executor will be assigned to this particular application. Now we need to take care of the shuffle service. Now I have not configured an external shuffle service here. Rather, I have used shuffle tracking enabled as true. This will make sure that the Spark keep tracks of the shuffle service and provides it to all the executors that are scaled up. The next two properties are for deallocating the executors. It implies these are the property that will help us to scale down the executors. So the first one is executor idle timeout, which I have set to 60 seconds. So once an executor is ideal for 60 seconds, it will automatically scale down. The next one is cached executor idle timeout. It implies even if we have a cached data or a broadcasted data in an executor, it will scale down if it is idle more than 60 seconds. So once all of our properties are ready, let's generate our Spark session. So I'll run this. Okay, my Spark session is up and live. Let me go back and refresh my Spark cluster UI. So you can see I have this app running. Now, as I mentioned, the initial executor as 1. So by default, Spark has allocated me 1 executor. If we wait for 60 seconds, since the idle timeout is set to 60 seconds, Spark will automatically kill this particular executor. Let's wait for 60 seconds and we'll refresh this page. I have refreshed this page and you can see the state has changed to killed. After 60 seconds, since this executor was idle, the driver killed this session. So if I go back to this application, you can see number of cores is right now 0. Because the minimum number of executors that we set was 0. So in an ideal running scenario, we'll have no executor right now. Now, for today's session, I have used the same data for sales and cities that we have used in our previous session when we were discussing optimizing joins. Now, if you have not seen that session, I'll recommend you to go back and watch that session. So I'll first read the sales data. Now, again, reading with this schema is a transformation. So if I go back and refresh this UI, you see still the cores are 0 because I have not called any action yet. Let me read the city data as well. Now, since we are doing join, now this is the joining statement that I'm using. We are joining both the data sets based on city ID and we are doing a left outer join. Now, before I run this, let me go and refresh the Spark UI. Okay, our Spark UI is up and running. Let me run this. And we'll write the data in no-op format. Now we know that we use no-op format for performance benchmarking, and that is what we are going to do today. I'll run this to make sure that the join happens. Okay, the job is running right now. Let me go and refresh the jobs tab. You can see the jobs running. Now, if I go to the Spark master and refresh the screen here, you can see an app created and number of cores assigned as 8. Let me expand this. You can see 4 executors created right now for this particular application. Let me refresh. Now, if you see, Spark has automatically added one more executor to this job as per the requirement. And this is the max number of executors that this application can assign. Let's wait for this job to complete. Now, let me go and refresh. You can see the job completed. Let me open this. Now, you can see the executors here being assigned automatically for this particular application, right? Let me go and refresh this. You can see still 5 executors are there and they will scale down gradually as per our idle time setup. So let me refresh this after 60 seconds. As you can see, it has started scaling down. Now, once I refresh this, you can see all of the executors are killed. Now, there may be some case where the executors will not be killed immediately after 60 seconds because they are busy in garbage collection or other activities that are required before the executors can be killed gracefully. This is why sometimes you cannot see the executors being killed immediately after 60 seconds, but they will be gradually setting down. Now, if I come to the job, you can see the executors being added in the event timeline, right? Let me refresh this job now. Let me go back to the save again. And now you can see the event timeline with the executors being killed. You can see the executor 4 was immediately killed after 60 seconds. Here it is 1612 and here it is 1613.04. So after 60 seconds, the ideal executor was killed. But all of the other 4 were having some cached data. This is why it has to go to the garbage collection process and other process properly kill the executors that has the cache data. This is why it took more than 3 minutes in order to get killed. But the executors are gradually scaled down. If I go to the application again, let me refresh the Spark Master UI. If you can see, the number of cores is made as 0. Now, if I open this app, you cannot see any of the executors running. All of them are killed. And this is how the resource for a particular cluster can be managed using dynamic allocation. Now, that brings to the last topic for this session. What is the difference between dynamic allocation in Spark and the Databricks cluster scale up, scale down? Now you can easily understand. In this case, we have a fixed cluster where we are running multiple applications into that fixed cluster size. But in Databricks, whenever we scale up and scale down, a new worker node itself is added to that cluster. So it's a scaling of workers, not executors. When a worker is added in a Databricks cluster, automatically a new executor spin up in that particular worker node. But it itself is adding a worker node rather than creating executors into the same worker node which is pre-existing. And this is what is the difference between a dynamic allocation situation and a Databricks cluster scale up, scale down. Now, since that we are working with optimizations, today we will see what is skewness. We'll also understand how skewness leads to spillage. We'll understand the types of spillage, and we'll try to fix skewness using a famous technique called salting. Now, this salting technique is very popular because it is used to balance the partitions properly in order to avoid skewness. So we'll also see how skewness can be fixed with this salting technique today. Now, if you have not seen our previous video, I'd recommend you to go back and watch our playlist from the beginning. So without any delay, let's begin. I am in my Jupyter Lab environment. Today we are going to use an employee set of data along with a department data. We are going to join both the data sets. Now, this employee data is skewed. So when we join this with the department data set, we will see some spillage happening, and we will try to fix that with the sorting technique that we are going to discuss today. For today's session, I am going to disable the AQV in order to demonstrate how skewness can be fixed with sorting techniques. For the Spark session, I am running my master on my Spark cluster. The max number of cores that I'm going to use is 8, and the executor max core is 4. So we'll have 2 executors with 4 cores each, and the memory is set to 512 MB. Now, let me create the Spark session first. Okay, my Spark session is created. Let me go ahead and refresh my Spark UI. Okay, my UI is up and running. Let me go to the Executors tab. Okay, you can see we have 2 executors, 0 and 1, and each one is having 4 cores. Let me disable the AQE. Cool. Now we have the employee data as employee records skewed.csv. We have a header in the data, and the total number of records for this data set is 1 million. We have specified the schema for this particular CSV file. Let me read this one. Okay, our employee data frame is created. Now let's create the department CSV data. Now this is the same data that we were using from our joins. So we will read the department data, which contains 10 records. Again, this data set has header, and we are going to read it with schema. So let me run this. Now, since employee and department both are read with schema, so none of the jobs should be created. So let me refresh this, and you see no jobs created because we have not called any action yet. Now, the next is to join employee data with department data. Now we are going to use department ID, and we are going to do left outer join. Now, this is the same join that we have seen to optimize joins. Now, if you have not seen that video, I'd recommend you to go back and watch that video first. So let me run this first. Done. Now, let me run the action of write with no off format. Now, we know that we use no off for benchmarking, and this will trigger the join. Let me run this. Okay, the job completed. Let me go back to the Spark UI first. I'll go to the Spark data frame tab, and we can see one job created. Now, before we go into that, let's check the tag. Okay, now if you see, we have exchange, sort, and sort merge join here because we have disabled broadcast join, which was by default for AQE for smaller data sets. Now, since we have disabled the AQE, this has taken the path of sort merge join. That's okay for us because we are going to see how to fix skewness today. Let me go back to the data frame tab. Cool. If we expand the job now, we should see 1, 2, and 3 stages. First stage would read the CSV file for employee. The second one would read the department, and then the join will happen. Now, since we have the default Spark shuffle partition set to 200, we can see the third stage has around 200 tasks for reading the 200 shuffle partitions that are written. So let me expand the third stage. Now, if we go to the bottom, you can see we have a spill memory and spill disk in both the executors. And you can see the spill memory is 64 MB and the spill disk is 36.1 MB. Similarly, 79 and 40.3. So let me come down. And now you can see the number of records processed by each of the tasks. Now, since the default shuffle partition is 200, you can see 200 tasks being called. But only few of them has processed the data. Rest all has done nothing. So the shuffle partition for 200 is a waste for us. So we have to fix that. That is one. Now, for 2 of the tasks, you can see spillage here. If you compare, all other tasks has processed less amount of data, but these 2 are processing a huge amount of data. And this is the reason why we have spillage. Spillage and skewness come hand to hand. This is skewed data. When we say skewed data, it means for our data set, since our joining key was department ID, few of the department ID has data significantly more than other department IDs. And this is why this department IDs are creating spillage. Now, we can see 2 types of spillage memory and spillage disk. What is spillage memory? Spillage memory is the amount of data that is deserialized and that will be spilled to disk next. So 79 MB is the deserialized data which is spilled to disk, and in disk it is written in 40.3 MB, which is serialized in disk. So this is the amount of data which was deserialized in memory, which is written to disk, which we called spill to disk because it was not able to fit in the memory. So this is why it was spilled to disk, and the data was written in serialized format with 40.3 MB. Now, spillage can create issues in your job. The reason is, since the data is written in disk, so Spark has to now read the data again, perform IO operations, then perform the job on that particular data. So it is always advised to fix the skewness so that spillage does not happen in your data. Okay, now let's see how is the skewness for our data set. So let me go back to my Jupyter lab. Okay, now that we know two of the tasks spilled the data, so there might be two of the partitions which are having huge volume than other of the partitions, right? And to see the partition information, we know that we can use Spark partition ID. So let's write a query and see the partition information and the count of data in each of the partition. So for this join data, I'll write this. So I'll use this df joined, and we'll create a column called partition number. So I'll write with column, and I'll write partition num as the column name, and I'll use Spark partition ID as the partition number. Okay, now that we know that we'll get the partition number for all of the data, we need to group by and see the count. So for that, I'll write group by partition number, and we need to see the count. So I'll put count, and we'll just do count of one. So I'll use lit for it. So I'll write lit of 1. And let me alias this column. So I'll write alias count. Okay, now I'll give a name to this particular data frame. So I'll write part df is equals. Okay, now that we have aggregated the count, so let me see the count. So I'll put part df dot show. I'll run this. Awesome. If you notice, for few of the partition number, we have huge volume. Like for partition 122, we have huge number of volume. Similarly, for 174, we have huge number of volume, right? Let me go back to the task. And if you see, and if you try to notice the count here for this partition, it is 419505. Let me go back, and you can see here 419504. This is because this partition was processed by that task. Now, one record is from the department to join. Similarly, if you see 420474, if I go back and you check 420475, one record from department. It is 420474 from employee plus one record of department. So we have two of the tasks which are skewed, which have huge number of volume in comparison to others, right? Other than this, if you see, we only have 10 partitions in which data, but our Cephl partition is 200. So 190 partitions has no data. And this is why we need to configure our Cephl partitions properly. Only 10 of them has data out of this, and 190 of them are empty. So now let's check what are the department IDs which are creating this skewness. So to do that, I'll write the query to check the department information. So we know how to do group by for department, right? So I'll write that query quickly. So I'll write emp dot awesome. If you see, for two of the department 9 and department 10, we have skewness. So now we know the reason of the skewness, that two of the department has huge significant amount of volume in comparison to others, which is being read by two of the partitions, which is being processed by these two tasks, which is not able to fit all of the data in the memory. That is why it is spilling the data to disk. And now we understand the reason for the spillage. Now, what are the measures to fix this? The first one is repartitioning of data. Now, since the joining column itself is on department, even if we repartition the data, both the departments will again come back to the same task. So we'll again have skewness for this data. What can be the other way? Other way is to break down this skewness data in such a way that we have even data for all of the partitions. If we have even data for all of the partitions, all of the data can be fit in memory and the task will not spill the data. This is why we need a technique called salting. Salting is a technique in which we add something called salt, which makes sure that your data is broken in such a way that you have the partition data evenly distributed. And thus, all of the tasks will be processing your data properly without any spillage. Now, there is one more thing to notice. If I go back to the Spark UI, you can see the timings here. this task has taken 6 seconds and this one has taken 4 seconds. If you see, all other has taken not more than 1 second, right? So these two tasks are taking more time because of this skewness as well, right? Consider if all of them finishes in 1 second, then your job will finish in 1 second. But if all of them finishes in 1 second, but this two finishes in 6 seconds, then your job has to wait for 6 seconds to finish, right? So if we fix the skewness, we also fix the duration of our job. So let's go back and understand how we can do it using sorting technique. Now, sorting technique involves adding salt to your joining column. Now, when we say joining column, both for employee and department, we have the joining column as department ID. Now, in order to add salt, consider we have IDs like this. So if you see here, 3 is skewed, right? So what we will do is we will add one salt to each of the keys. Now, what is that salt? So we consider we add 0 here for all the keys of department. Similarly, I will add one more salt called 1. So for department, we create keys like this. Similarly, we add salt randomly to department ID of employee. So what we do is we put randomly 1 0 1 0 1 1 0 0 0. Okay, now I know it might sound confusing, but just hold for a minute. Now we added two salt here, 0 and 1. We have made a cross join for department data. So what we did is we did a cross join for all the keys of department with 0. Similarly, we did the cross join with 1. So we get the number of keys of department into the number of salt. So our key was 3. So we have number of salt as 2. So total number records will be 6. That is what we have right now. Okay. Now for department ID in employee, we did the salting randomly. We added the salt as 0 and 1 to the randomly to the department ID of employee. So if the records number here is 9, then we will still have 9 records because we have just added or appended the salt here. Okay. Now, if you see here, if we join the data set now, this will join with this data set and this will join with this data set. Okay. So if you see, we have broken down this into two partitions. Correct? So the joining will now happen in two cases. We will get this data in one partition and this data in another partition, right? Earlier, it was all in a single partition, 5 records. Now it is 3 and so your data is broken down. Now, after our joining concludes, we can remove the salt and our data will still be there. So we understand what we are going to do here. Now, let's see this in practical, understand it more clearly. Okay, now that we understand the approach that we are going to do, let's first set the supple partition to 16. So for that, I'll write spark.conf.set and I'll write it spark.sql. Let me run this. Okay. Now, there are two places where we need salt. First is the employee and second is the department. In department, we need to do a cross join. So what I'll do is, so first I'll create a data frame called saltdf, which will be a range of 16. So I'll write spark.range and this will create our data frame 16. Let me show you what this will do. So I'll write sparkdf.show and let me run this. Now if you see, we have keys from 0 till 15. So there are 16 IDs in this and we'll use this for cross joining with department. Okay. Next I'll write one UDF to randomly add salt to the employees department. So for that I'll write @UDF and this will be our salt UDF. And I'll just do a return random integers out of 0 to 16. Okay, so let me rerun this. Great. Now that we have prepared our salt, let me first create the salted employee. Now, for salted employee, we know that we just have to randomly add that value to the department. So I'll write salted EMP. This will be our data frame for employee. So we will create this from EMP and we will create a new column, which will be our key now, which we will call as salted department ID. So I'll write it as salted department ID and we will concatenate the random data from the UDF. So for that, I'll write concat and we need to concat department ID. Now we'll add the underscore. For that, we will use literal because we cannot add strings directly. So we need to use literal and we will call the salt UDF to get the random number here. Okay. Now this is what our column would be. Our column would be department ID underscore and then we will add a random number that we'll get from our salt UDF. Now let me run a show command to show you the values. So what I'll do is I'll do dot show here and let me run this. So let me rerun this. Awesome. Now let me just zoom it out a bit. Okay, now if you see, we have department ID 3 and we have added a salt of 15 here. 4, we have added a 0. Now again, if you see for 3, 9. So randomly it has added salt for the department ID column. And this is our new column, salted department ID, that we will use for join. Now let's create the salted department. So for that, we need to do a cross join. So I'll write salted department is equals to, we need to do a cross join with department. So I'll write department dot join, and we need the salt df for joining, and the how is cross. Okay, so it will do a cross join, but we still have to create that column, right? So we'll create that salt column. So I'll do with column, and the name of the column would be same. I'll use the same column, salted department ID, and we will concatenate the ID from the salt df with the department ID. So we'll again write concat, we'll write department ID, and again we'll use literal for underscore. So I'll put underscore, and we need to add the column ID from salt df. So I'll write ID. Our column is created. Let's view this one as well. So I'll write salt department dot show. Now if you see, we have added the values. Let's view for one department. So I'll write dot where, and I'll use for one department ID. So I'll write department ID equals to 1. So let me run this. Awesome. If you see, for 1 we have added salt till 15. So 16 rows from 0 till 15. So we have done a cross join here. Similarly, you can view it for any department. For example, for department 9, you can see the salt has been prepared. Awesome. That our salted department and salted employee is ready. Let's go ahead and join them. The joining will be same. I'll name the joining df as salted join df, and the joining will happen same as employee. Let me copy the employee joining condition. Now, in place of employee, we will use salted employee. So I'll write salted employee. And in place of department, we will use salted department. On column would be on salted employee dot salted department ID. So I'll write salted dpt ID. And again for salted department, we'll use the same column. Let me run this. Nice. Now, before we go ahead and run the no op, let's view the partition distribution. Now, we know how to do partition distribution because we just did it for the join above, right? Let me copy the same query. So I'll use the same query here. I'll paste it here, but this time I'll use salted join df in place of df joined. Okay, let me run this. Okay, we got our information, but now if you'll see, we have distributed our data across 16 partitions, and majority of the data is distributed properly. You don't have a skewness of 400k records anywhere. Now if you see, the data is distributed properly. Now still you can see some amount of skewness for some of the partitions, right? But still this is way lot better than what happened last time. Our data was distributed within 10 partitions. Now this is distributed in all 16 shuffle partitions. Okay, let me run the join now so that we can see if there is any spillage or not. So I'll run this no op. Awesome. Our joining completed. Let me go and refresh the Spark DataFrame tab. Nice. Let me go and expand the job. And let me, now if you see, we have 16 simple tasks because we set specifically 16 simple partitions. So let me expand this. If I scroll down, you can see we have reduced the spillage. Now still we have spillage because we have some 1 million records that is running in some of the partitions. So let's do one thing. Let's increase our shuffle partition so that we get more number of partitions and we have less data in each of the partition to process. So since we have 8 cores, so I'll make it 32. Okay, so let me rerun this. Now again, we will change our sorting to 32 because we have to make sure that all 32 partitions get data. So I'll make it as 32. Let me rerun this. Awesome. Now our ID will have 32 values. So let me run this salted employee again. Nice. Let me go and run the department again. Awesome. Let me run the joining again. Done. Now let me run this partition to show you the distribution. So I'll run this. Nice. If you see, now we have reduced the volume to much more less value, right? The volume is spread much more evenly now, right? So let me rewrite this joining. So what I'll do is I'll run the joining right again with the no op. Awesome. This completed. Let me go back and refresh the data frame tab. Nice. Let me expand the job. Now, if I scroll down, we can see 32 tasks for shuffle partition because that is what we have said. Let me expand the stage. Let me scroll down. And now if you see, we don't have any spillage. So what I'll do is let me see the record counts. Now if you see, we do not have any spillage. Let me expand all the tabs for tasks so that you can see that we don't have spillage. But the data is more evenly distributed now. And now if you check one more thing, the max duration for a task is 2 seconds. It implies the maximum amount of time taken for a task to execute, maximum is 2 seconds. If you remember, it was 6 seconds previously, right? So your job is more distributed now. Okay, and this is how we fix skewness. So now if you have seen, we have done sorting technique, but we again ran into a skewness problem. Okay, but we changed our shuffle setting and we fixed that issue. And this is how we optimize code in production scenario systems. It is not one size fit all scenario. So same thing cannot be fixed for all of the jobs. You have to see the scenario and you have to fix your job. And that is how optimization is being done in Spark. I hope you understood what we did today. Now, if you want to read more about this salting, you can find an article in Medium, which I have written long back in 2022 for salting technique. You can find the name PySpark, the famous salting technique. You can read this article to again understand with an example what is happening and how we are doing the salting. I hope this will make you understand how optimizations are being done in Spark. If you have seen our previous videos, you might have understood that we were disabling AQE. The reason for disabling AQE was to understand how Spark behaves without AQE, which is adaptive query execution. Today, we will enable AQE and we will understand what are the benefits of AQE. We will see the impact of AQE in skew joins, sort merge joins, and broadcast joins. We will understand how coalescing post-shuffle partitions are done in AQE. Now, if you watch today's session, you will understand when we enable AQE, how it will be a different execution than what we were doing previously, and how this will optimize your jobs. And this is the main reason why I disabled AQE in previous sessions. So to make you understand how AQE changes your job and how this out-of-the-box feature from Spark helps you to optimize your jobs. So without any further delay, let's begin. Now, this is the Spark documentation for adaptive query execution. Now, I have specifically opened the documentation for the version that we are working on, 3.3.0. Okay, AQE is available from Spark 3.0. There were some major features of AQE that were added from Spark 3.0, which are coalescing post-shuffle partitions, converting the sort merge joins, and the skew joins optimization. Again, AQE has a very good optimization while working with Spark SQL. It makes uses of the runtime statistics to choose the most efficient execution plan. And this is where AQE dominates in a lot of optimization techniques. Now, this AQE feature for Spark SQL is available from 3.2.0. But some other features that we were discussing were already available from 3.0. So now you know what AQE provides us. And we will see all of them one by one. I am in my Jupyter Lab environment. As usual, we'll start by generating our Spark session. So for today's session, again, I have set the max executor cores to 4 and the total number of cores available for this execution is 8. This will help us to generate 2 executors with 4 cores each. And the memory setting is closed at 512 MB per executor. Let me run and generate the Spark session first. Awesome. My Spark session is generated. Let me go ahead and refresh the Spark UI. Okay, my Spark UI is up and running. Let me go to the Executors tab. Nice. I have 2 executors 0 and 1 with 4 cores each. Nice. Let me go back. Now, before we can see how AQE behaves, let's understand what happens when we disable AQE and broadcast join. We have been seeing this from our previous sessions, but we will specifically see this again today. So to disable AQE, we need to set spark.sql.adaptive.enabled as false. Now, the default value for this is true. So by default, AQE is enabled. Now, we will specifically set it to false for disabling it. Again, AQE also provides us with Coalesce partition enabled. We'll also set this as false. We'll see what this is next. But before that, let me set this to false. Again, I've set the auto broadcast join threshold to -1. This will make sure that Spark does not run automatic broadcast joins on smaller datasets. So let me run this. Great, our AQ is disabled. Now, we will be using that same employee record skewed CSV file that we were using in our previous session. Now, what this will do is, this will create a skewed data set and then we will join it with department data so that we can see the skew and the spillage happening. Now, let me run this. Great. Our employee data frame and department data frame is ready. Now we will be joining both the data set based on department ID, and the join would be on the left outer side. So let me run this. Great. Now our join is done. Now, if you have seen our previous video for Skewness and Spillage, you might be knowing what will be happening next when I run this join statement, right? So before that, let me show you the explain plan. So I'll run this. Awesome. Since we have disabled the broadcast join, we are going through the sort merge join. You can see file scans are being done. Then there's an exchange step. Then there is a sort step. And last, it is doing the sort merge join, right? So let me run this join. So for that, I'll use the format as no op and we will overwrite the data. So let me run this. Great. Our joining has complete. Let me go to the Spark UI. Let's go to the DataFrame tab. If I expand this, save, you can see the DAG. Now, if you see, we have exchange, sort, and then sort merge join. So this has taken a step of sort merge join. Now, let me go back and show you the job. If I go down and expand the third stage, you can see we have a spillage here. You can see 137 MB has been spilled to memory and that has been written to disk in 77.2 MB. Now, that spillage is happening here because we have a skewed data. Correct? So this is what we have seen in our previous session as well. Let me go back and show you the stage again. So if I go back and show you the third stage, you can see there are 200 shuffle partition tasks are created. And we know that spark.sql shuffle partition is by default 200. Okay, so when we disable AQE, Spark is taking the default setting of 200 and it is creating 200 shuffle partitions. And we know not all of them are being used to read the data, right? So if we expand and if we scroll down to the task, you can see majority of them are empty. Okay, so if I descend this as per the shuffle record, so you can see only 10 of the tasks are doing the job, rest all have done nothing. Okay, so this is where we see a lot of degradation. First, we can see a lot of shuffle partitions, which is useless. And the second one is there is a skewed data, which is creating a spillage in memory. Okay, now that we have seen the job performance without AQE, let's enable our AQE and see what are the optimizations that Spark take care of when we enable the adaptive query execution. So let me scroll and we are going to see two of them together. The first one is coalescing post shuffle. It implies, if you remember, there were 200 shuffle tasks that were being created because of the default value. Now, in order to reduce that shuffle partitions value, we had to set it manually. Now, if you enable AQE, Spark will take care of that. All the unnecessary shuffle partitions would be removed and Spark will create only required number of post shuffle partitions. Okay, so whatever unnecessary partitions were being created will not be created. Okay, other one we are going to see is skewed join optimization. Now, in our data set, we have seen because of a bigger size of partition, the data is being getting spilled because the task memory size is lesser than this. Because we are using a smaller cluster, the memory size for each task is also less. And this is why if that exceeds the task memory size, it is getting spilled, right? So AQE will automatically take care of it. It does two things. First, it will join smaller partitions. If you have many smaller partition size post shuffle, it will join those to create a medium or a balanced size partition. Second, it will break the bigger partitions. Now, in our case, that is the problem. We have bigger partition size, so it will split it out. Okay, so to do that, first we have to enable AQE. Now, to enable AQE, you have to set Spark SQL Adaptive enabled as true. Now, this is by default true in Spark 3.0. Now, since we had disabled it previously, let me enable it, putting it as true. Okay, the next one is Coalesce partition enabled as true. Again, this is by default enabled as true in Spark 3.0, but since we have disabled it in the beginning, I'll make it mark it as true again. So let me run this. Great. Now, there are two more configurations that we will do today for our job. Now, the first one is advisory partition size in bytes. Now, this is the partition size that Spark will create by default post shuffle. Okay, so the default size that has been set for Spark is 64 MB. But since we are using a smaller cluster and the task memory is less, we will set it to 8 MB. Okay, the other one is skew join threshold in bytes. Now, this is because we will ask that if the size of the partition exceeds 10 MB, we will consider it as a skew partition. So, adaptive query engine will know any partition size exceeding 10 MB will be a skewed partition. So, it has to split it into multiple partition. Okay. Again, the default value is 256 MB. Now, this two setting, I'm doing it only specifically for the job that we are going to optimize now. In your production scenario, there can be different jobs. So, you have to see the size of each task and then decide the value. In many of the cases, you don't need to touch this value. So, be very careful before you adjust the value for this two particular configurations. Okay, so let me run this. Now, once I have enabled the AQE, let me go back and rerun the joins. So this is the join, and now we will write the data in NoOp again. So let me rerun this. Awesome, it completed so quick. Let me go to the DataFrame tab now. Nice. If you see, this job completed within 2 seconds. Okay. So let me expand the third job. If I scroll down, you can see it has taken only 17 shuffle partitions now because Spark has coalesced unnecessary shuffle partition post shuffle. Okay. So if I expand this, let me scroll down. You can see there is no skewed data here. Okay. There is no spillage happening. There is no skewed data. Spark has automatically taken care and created 17 post shuffle partitions to take care of the data skewness. Okay. So this is how the skewness has automatically been taken care by adaptive query engine. Now, if you remember our previous session, we had to go through a process called salting in order to fix it, right? Now, in 3.0 Spark, if you have enabled AQE and set up your partition size properly, Spark will automatically take care of the spillage and skewness. You don't have to go ahead and do the salting technique. So this is one of the benefit that AQE offers. Now, we have seen how the Coalesce post shuffle partition and the skew joint optimization happen. Okay. Now, the next one is sort merge join. Now, if we see the third job that executed, you can see the DAG, it is still happening sort merge join because we have specifically disabled the broadcast join, right? Let's enable the broadcast join. Okay, so I'll enable the broadcast join providing the size that is required for the broadcast join, which is 10 MB. So let me enable this. Okay, this is done. Now we will again run this join, but if you see, I'll not specify any broadcasting here. If you remember our optimization for joins, we had to specify broadcast for department in order to do it if we are not using AQE. But with AQE, you don't need to specify any broadcast. Broadcasting will be taken care of by AQE itself. It will check which one is a smaller data set and it will automatically optimize your joins. So let me run the join again. I have not specified any broadcast. Okay. So let me rewrite the data. So I'll rerun. Great. It completed so quick. Let me go back and refresh the data frame tab. Nice. Again, you can see it completed within 2 seconds. Let me go and show you the DAG. Awesome. Now, if you see, AQE is automatically determined that the department is a smaller data set and it has to broadcast the data and the broadcast join has happened. Okay, so this has been done by AQE automatically. You do not have to specify broadcast here for department. AQE has taken care of the broadcasting. And this is one of the major optimization that AQE provides. If you enable AQE, AQE will automatically take care of the broadcasting. Now, in our previous session, we disabled AQE in order to show you how to do it manually. But if you enable AQE in Spark 3.0, a smaller data set would automatically broadcast it and your join will happen so quick. So if I go to the jobs, you will not see any shuffle step because broadcasting does not do shuffle, right? The first step will broadcast the data and the second job will join the data. So let me expand this. You can see the joining happening here. Okay, there is no shuffle step because this is a broadcast join. Now, we have seen how AQE optimizes our job when enabled. Now, there are certain more features that AQE provide. You can go ahead and see this documentation to find out all the configurations that you can do along with AQE. From the beginning of this course, we were writing PySpark DataFrame APIs. Now, Spark offers one more fantastic feature, which is known as Spark SQL. Again, Spark SQL is an abstraction of Spark core APIs. So whatever we have done till today with Spark DataFrame APIs can also be done using Spark SQL. This is where Spark becomes very handy. Now, if you're not aware of Python or PySpark APIs, you can always use SQL and get started with Spark from the very first day. And today we will understand how Spark SQL works. We will see the different catalog options that Spark provides. We will see how to persist metadata in Spark. And we will also see the hints that Spark SQL provides us for optimizations. Now, if you have not seen our previous video, I'd recommend you to go back and watch our playlist from the beginning. So without any further delay, let's begin. Now, I am in my Jupyter Lab environment. Spark SQL offers a lot of things. If you go and open Spark documentation, you can find a lot of things that Spark SQL offers. Now, it is not possible to cover everything, but today I will show you the necessary things that you need to do in order to get started with Spark SQL. So, as we know that in order to work with Spark, we first need to generate a Spark session. So, today I'll do it in my local. So, let me generate the Spark session first. My Spark session is ready. Let me go ahead and refresh the Spark UI. Great, my Spark UI is up and running. Let me go back. Now, we will read two datasets, employee and department, and we will do all the necessary functions in Spark SQL. Now, we know to read the dataset, we can use Spark read format CSV, and we can provide the location of the files, right? So let's read the datasets as DataFrame. So I'm reading the employee data as EMP DataFrame, and similarly, I'll read the department data as DEPT DataFrame. Awesome. Now that we have created our employee and department data frames, first understand what is catalog. Catalog is something which stores your metadata. And when we talk about metadata, metadata is the data about your data. It means it stores the information about your table, the column names, the data types, and the other metadata related to your tables or the views that you are going to create. Now, by default, the catalog implementation can be seen using Spark SQL catalog implementation. And if I run this, the default catalog implementation is in memory. It means your catalog will be created in RAM, and once this session is lost, your catalog will also be lost, right? But that's not a good thing, because if we create a table and if we want to read the table next time, it will not be available because the in-memory catalog will be lost once your session is closed. To help with that, we will also see one more catalog implementation is Hive that Spark provides. But first, let's get started with Spark SQL. We will implement the persistent metastore with Hive next. Now, in order to run a Spark SQL, you need to write spark.sql. And within brackets, you can provide any query in SQL. So consider we want to see the databases. So to show the databases in this catalog, we can write show databases. Now, if I run this, awesome. This query ran, but we didn't see any output, right? Because by default, Spark works with DataFrames. So whenever you run any query against spark.sql, that will create a DataFrame in the output. So we can assign this to a DataFrame, right? Let's make the DataFrame name as DB. So if I run this, it will create a DataFrame called DB, and I can do db.show. Nice. It gives me the only database that is available, which is default. Awesome. Now that we know how to run query, let's go ahead and see the tables available in this database. So to see the tables, I'll write spark.sql. We can write so tables in default. Now we know this will return a data frame, but to show the data, I'll write show. And show is an action. So when I run this, you can see the output. But again, if I go to data frames and so if I expand this, you can see a job executed in the background. So Spark is using the core APIs in the background. The abstraction is Spark SQL. Let me go back, and you can see right now there are no tables in this particular database, right? So let's register two of our data frames that we have created as views. So to do that, I'll write emp dot. If I press a tab, you can see multiple options. It says create global temp view. It says create or replace global temp view. Then you can see other options like create or replace temp view, create temp view. Now, what are all this? If I create a global temp view, it will be available in other sessions as well. But if I create a normal temp view, it will be available only in this session. So let's create a normal temp view. Okay. So I'll name this as emp view. Okay. Similarly, for department, we will create another view. Now let me run this. Nothing will happen because this is telling Spark to create a view for this particular data frame. Now let me rerun this show tables in default. So if I run this, now you can see two views created. Now if you see one more thing, it says is temporary is true. It means this is a view, not a table, because for a table you will see the table name plus it will be is temporary as false. Okay, so this is temporary. It means once this session is lost, this view will also be lost. Okay, now that our views are ready, let's go ahead and query the data from it. So to do that, again, we will write spark.sql, and within brackets, we'll write our query. Consider you have a multi-line query. Now, in order to write a multi-line query, you have to use triple quotes. So I will use triple quotes. Then you can press enter and you can write any multi-line query within it. So let me write select star from emp view. So if I run this, again, this will create our data frame. But now you can see all the columns for the data frame here, right? To view the data, we have to call the action, right? So I'll write show. Awesome. You can see the data for the employee, right? So let's do one thing. Let's put a filter. Now we know in SQL, we can write where. Let's put a filter called department ID equals 1. Let's rerun this. Awesome. Now you can see the data for department ID. So you now know it's so easy using Spark SQL. And in return, it provides you a data frame. So if you want to manipulate it using PySpark API, you can create a department filtered data frame from here. And then you can start using this data frame. So if I run this, it will create a data frame called EMP filtered. Now you can use this data frame to do your manipulation in Spark data frame API. So if I want to see the data, I can run EMP filter.show. Right? So you can use Spark SQL in order to generate or manipulate your data in form of data frames as well. Okay, now that we know that we can manipulate the data, can we create or remove columns? The answer is yes. Now, consider we want to create a new column called DOB year. Now, this DOB year would extract the year from date of birth. So let's do this in Spark SQL. So what I'll do is I'll copy this Spark SQL from top. I'll paste it here. Okay, now I'll use aliasing here. So I'll put EMP view as E. Okay, now I'll put e dot star. Now when I put e dot star, it will print out all the columns, right? Now I'll create a new column, say dob year. Now extract the year, we know we can use the date format function. Now all the functions that are provided in Spark DataFrame API are by default available for Spark SQL. You don't need to import anything. You just can use directly within the SQL command. So I'll use date format and I'll pass the dob column, and I need to extract the year. So I'll write YY. Okay, now let me put show in order to view the data. So if I run this, let me zoom out a bit. Awesome, you can see the column here. Let me rename this. In order to rename, we can write as dob year, and let me rerun this. Awesome, you can see the dob year column extracting the year. Okay, so right now we are filtering based on department ID. Let's remove this filter and let's rerun this. Awesome, we can see it for all the departments, right? So this is how the data manipulation can also be done. You can use the Spark SQL functions that are available with PySpark, and you can run them directly within Spark SQL. Okay, now consider we want to create a new view for this particular data frame. Okay, so consider we will write it as emp temp, and we'll put this as, so this is now a data frame, right? Let me run this. So it will create a emp temp data frame, correct? Now again we can register this as view, correct? So I'll write create and replace temp view, and I'll create a new view called emp temp view. Let me run this. Awesome, let me go ahead and show you this. So I'll rerun this, and you can see now it has created a temp view. Now if you want to see the data for this temp view, you can always write spark.sql, and within this you can write select star from emp temp view, and we will put show in order to view the data. So if I run this, awesome, now you can see the new column in this view, right? Because we have registered this as data frame, then we have written this as a new temp view. Okay, now this temp view is again available in our catalog because we have registered it right now. Okay, awesome, now that we have our tables ready, let's do a join. So in order to do a join, we know we can use spark.sql, and I'll use triple quotes here. Now we'll write the SQL query. So I'll write select, say star, and I'll write from, and we will use the new view that we created. So we'll use emp temp view. Okay, we'll write it as E, and do left outer join. So I'll write left outer join with department. So we have dept view, right? We'll put it as D, and we'll put on E dot department ID, which is our joining column. So I'll copy this here, and we'll put D dot department ID. Awesome, and this is what our join is. So if I run this, you will see a data frame created, right? Which will have both the columns from department and employee. Let's put only the employee column. So I'll write e dot star, and we will bring the department name. So I'll write d dot department name. So let me rerun this. Now you can see the department name column from department and rest all columns from employee. Right? Now again, this is a data frame. Now we have to call the action. So in order to view the data, we have to call show. So let me run this. Awesome, now you can see the data here, right? You can see the department names according to the department ID. Let me go back and refresh the data frame tab. So I'll refresh this. Now you can see another job created. Let me expand this. Now you can see the broadcast join is happening by default because the AQE is taking care of the Spark SQL. It knows that both the tables need to be joined, so it will automatically do a broadcast join of the smaller data set. Now if I come back, consider you need to provide a hint. Consider we don't want to do broadcast join, but we want to do a shuffle join. Now in order to do that, you need to provide a hint. To provide a hint, you need to put it before the column name. So this is our column name. Let me put the hint here. So to provide a hint, you need to write slash star, then you need to put a plus, and then you need to provide a hint. Now you can find the list of hints in the Spark SQL documentation. Now what I'll do is, now for sort merge join, I'll put a hint called shuffle merge. This will instruct Spark to do a sort merge join for this particular join. So I'll write E in order to make the employee data as shuffle merge. Okay, and to end the hint, you can write star, and then you can put a slash. Now if I run this, awesome, our join completed, right? Let me go back and refresh the data frame tab. Let me expand the job. Now you can see it is doing exchange, then a sort merge join. Now you know how to provide hint, right? Now consider you have to specify broadcast join. In order to do that, you can provide a hint here. So similarly, you can write broadcast, and you can provide the data set that you need to broadcast. So consider we want to broadcast the department, you can write like this. And if you run this, again, this will do broadcast join. So if I go back and refresh here. If I come back here, you can see broadcast happening for department data. Okay, so this is how it is done. Now let me write this data. Now we know that if we run this, this will create a data frame, right? So consider I'll write it as emp final. So this will be our data frame that we will create using this Spark SQL command. So let me run this. This is the data frame that is created. Let me view the data to you. So I'll write dot show. So if I run this, you can see the data frame is having the data, right? Let's write it as table. So to write a table, you have to write save as table. So to do that, I'll write emp final dot write, and you can specify a format for which the underlying data will be saved. So if I write Parquet, so the underlying data will be saved as Parquet. Okay. Now you can specify save as table, and consider I'm writing it as emp final table. Okay, so let me run this. Awesome, our data writing is complete. Okay, let me scroll to the right, and now you can see a folder created called Spark Warehouse. So by default in the present directory, Spark will create a folder called Spark Warehouse. If you expand this, you can see the emp final folder, and you can see all the data being written in Parquet format. If I scroll it to right, you can see all the data being written in Parquet format. Now you have two options. You can read this data as a table directly because it has been registered in the catalog. So if I come back here and show you the catalog, you can see emp final has been registered as a table and the is temporary is false. It means it is a table now. Okay, now if you want to read it as table, you can write emp new, and you can read it using spark dot read dot table, and you can specify the name, which is emp final, and this will create a new data frame, which is emp new, and now you can see the data emp new dot show, and this will show you the data. Okay, now since this is already registered in the catalog, can we read it in the SQL query directly? The answer is yes. So consider you want to read it using SQL query. So you can write it like this, spark.sql, because we have this table in catalog. So we can write select star from, and we can name the table here, which is emp final. So if I run this, this will create this data from emp new. Now if I write emp new dot show, this will show you the data for that particular data frame. So now you know how to create a table, register it in the catalog, and read it from that table directly. Now, all of this we were doing in the in-memory catalog. So if I show you the catalog still, it is in memory. So here is the catalog. So if I run this, the catalog is in memory. It means once I close this session, this particular catalog will be lost. So let me show you this. Let me stop the kernel. So what I'll do is I'll restart the kernel. Let me do it. Awesome. The kernel is restarted. Okay. Let me go ahead and create my Spark session again. Okay, my Spark session is created, right? So if I come back to the catalog implementation again, see this is still in memory. Okay, so now we know we can see the databases here. Okay, if I show you the databases, we have only one database default. Okay, let me show you the tables now. Now you see everything is gone, even the table is gone. Okay, because the catalog implementation was in memory, it was lost when we restarted our session. Okay, so is there a way to persist this metadata that we do not lose it when we come back and restart our session? Answer is yes, and we have to implement the Hive catalog implementation. Okay, so to do that, we have to put one more option here, which is enable Hive support. So you have to write enable Hive support. So you have to use this now. Okay, now before we do that, let me restart the kernel so we can use enable Hive support now. Okay, my kernel is restarted. Let me rerun and create the Spark session. Okay, my Spark session is created. Now let's read the data frames again. So I'll do emp read, and again we'll do department data frame. Okay, now if I come back and show you the catalog implementation, you can see it as Hive. It means now we have a persisting metadata. I'll show you where the data is persisted. Just hold on for a minute. Okay, now we can still see the databases. So I'll rerun this query. We have only one database default. Okay, now let me show you the tables in that default database. There is nothing. Okay, let me come back to the left hand side and refresh this tab. Now if you'll see, there is one folder created called Metastore DB, and this is the location where Spark will store your catalog metadata information. So whenever you are going to recreate your session from this location, it will by default read this Metastore DB location, and it will bring in all your catalog. Okay, let's see that. Let me create the employee and department temp view. Okay, that is created. Let me go ahead and join employee and department here. So I'll write employee and department, employee view and department view. So I'll write emp view and department view. Okay, I'll do a broadcast join. So that is enabled by default, but still use the hint. Okay, so let me run this. The data frame is created. I can show you the data frame here. Awesome. Let's go ahead and write this. So I'll use the same write command. We'll save this as employee final table. Okay. So the data is written. Let me go back and show you the Spark warehouse. You can see the EMP final folder created. Okay. Now, if I come back to this catalog and show you the show tables in default, you can see the EMP final created here. Okay. This is false because this is a table and this is not temporary. This will retain even if we restart our Spark session. Okay. So this table is created, right? Let me go ahead and read that table and show it to you. So I'll read this and I'll show it to you in EMP new. You can see the data again. Okay. So now that we know we have enabled Hive support, so the catalog data should be retained once we restart, right? So let me restart the kernel. Now let me generate the Spark session again. So I'll rerun this. Awesome. My Spark session is ready. Let me go ahead and show you the catalog implementation. So I'll run this. You see the catalog implementation is Hive because we have enabled the Hive support, right? So let me show you the database. So I'll run this. Awesome. We have the same default database there. Now let me show you the tables. Now you can see the EMP final is still there because it's a table registered in the catalog. It's not lost even if I restarted the session, right? So we can read this data again. So let me go ahead and run this EMP new where we are directly reading it from the SQL query. So I'll run this and again I'll run the show. Awesome. It means our data store is persisted. Okay, and this is how in a production scenario, if a Hive catalog is implemented, the Metastore is persisted in a particular location. So in our demonstration, the Metastore was created in our present working directory. Okay, you can see the Metastore DB. But in a production scenario, this Metastore will be persisted in some databases or in a location which is available for all the Spark jobs. Now that we know how we created our tables, let's view the metadata for those tables. Okay, so in order to view that metadata, you can write spark.sql, and to view the metadata of a table, you can write describe and the table name. So our table is EMP final. So I'll put .show in the end to show you the data. So let me run this. Now you can see the column name, data type, and the comment column, right? But it does not provide you all the metadata information. To see all the metadata information, you can write extended. And if you rerun this, you can see there's a lot more information available now. You can see the type of table. You can see the database where it is stored. You can even see the location if it is stored somewhere else. Now, there are many more concepts regarding Spark SQL that you can find in PySpark documentation. Now that we are learning Spark, it is very important that we understand the importance of NoSQL databases. Today, we are going to explore Azure Cosmos DB. Cosmos DB is one of the popular offerings from Azure Cloud. Today, we will see what is a NoSQL database. Why is Cosmos DB so popular? We will try to understand the basics of Cosmos DB. We will set up Cosmos DB in our Azure cloud environment, and we will try to read and write data from Cosmos DB utilizing Spark. Now, this video is an end-to-end video. We'll start by learning the basics of Azure Cosmos DB till the end, how to load and write data using Spark. So please make sure that you watch this video till the end. Now, if you have not seen our previous video, I would recommend you to go back and watch our playlist from the beginning. So without any delay, let's begin. Now, before we can go ahead and learn about Cosmos DB, it is very important to understand the basic difference between a NoSQL and a SQL database. First and the foremost difference is the NoSQL databases do not have any fixed scheme. But wherever in a traditional SQL database, we have a fixed scheme. Now, the NoSQL databases majorly focuses on scaling out. It means horizontal scaling. Whereas the traditional SQL databases majorly focus on scaling up. It means vertical scaling. Now, NoSQL databases also support variety of data. It means it can support all structured, unstructured, or semi-structured of data. But SQL databases generally supports majorly structured data. And this is some of the important reasons why NoSQL databases are so much of demand nowadays. It is very important that you learn at least one NoSQL databases while working with Spark. And today we will see that with Cosmos DB. Now, to understand Cosmos DB, consider it as a hub. Cosmos DB itself supports multiple APIs. 4 of the major APIs are listed here. You can see NoSQL databases, graph databases, key value, and Postgres. Now, out of this, you can see Cosmos DB also supports NoSQL databases. It also supports graph databases like Gremlin. It supports key value stores as well. And it also supports structured data as Postgres. So, you can consider Cosmos DB as a hub with multiple API supports. And we will see this in few minutes when we start with our demo. The popularity of Cosmos DB starts with it supports ACID transactions. When we talk about ACID transactions, it was the fundamentals when the databases were built. It supports atomicity, consistency, isolation, and durability. So all the 4 ACID properties are supported by Cosmos DB. And the benefit comes into picture with Cosmos DB being highly distributed and concurrent in nature. Now, how Cosmos DB supports its highly distributed and concurrent nature? It's with 2 factors. The first one is replication and the second one is partition. For replication, it replicates the data in 2 ways. First one is local and the second one is geo. In local case, it copies the data in 4 instances in order to make sure your data is never lost and it is fault tolerant. But if you want to make your data available throughout the globe, you can use the geo-replication method. In that case, your data will be highly available. Now, coming back to partition. Cosmos DB generally partitions your data in two fashions. The first one is physical and the second one is logical. The first one is physical, means your data will reside actually at some data centers in the cloud. But logical partition is something that we will define with the help of a partition key to make sure that our data is distributed properly across the cluster nodes and it can be processed parallelly. And this is the reason why partition key is a very important factor in Cosmos DB. Now, Cosmos DB is designed in a very simple fashion. The first one is database. Database is as similar as our databases in SQL. Now, inside the database, we have containers. Now, you can assume containers as tables for your traditional SQL systems. Now, inside containers, you can have items. And these are the things which separate NoSQL from SQL. Items can be anything. It can be a key value pair. It can be a JSON payload. It can be a document. It can be a semi-structured data. It can be an unstructured data. And we need to define two important things for each of the item. The first one is ID, which would be the unique key. It can be a combination of one or more columns. And the second one is the partition key, which will distribute your data logically. So if we try to compare it with a simple SQL system, so database remains database, containers are your tables, and items are your records. Okay, now that we understand the basics of Cosmos DB, let's go ahead and create one of the instances of Cosmos DB in our Azure cloud. Now, in order to set up Cosmos DB, you first need to log in into your Azure account. Once you are logged in into your Azure account, you just need to search Cosmos DB from the search bar. You just need to type Cosmos and it will give you the option. Just click on Azure Cosmos DB. Once you are here, you can see a message displayed here. It says you will get some of the free units if you are within the free tier. So you can see it says 20k RUs. RUs are request units that Azure utilizes in order to bill you for Azure Cosmos. Now, whenever you read or write data, some of the RUs, which is the request unit, is consumed. And based on that, Azure will bill you for Azure Cosmos DB. Now, if you are well within the limits, there will be no charge in your Azure account. So let's go ahead and click on Create Azure Cosmos DB account. Great. Now you can see all the APIs that Cosmos DB offers. It starts with NoSQL. You can see Postgres, MongoDB, Gremlin, DB for table, and Apache Cassandra. For today's example, we are going to use NoSQL API. So I'll just click on Create. Great. Once we are inside the Create page, first we need to define the resource group. I'll click on Create New, and I'll just type is with data Cosmos. And I'll click on OK. This will create a new resource group. Now, I need to provide an account name. I'll just type is with data Cosmos DB. Great, it validated and I can use this name. Now, I'll not change anything else. I'll let it be whatever the default setting is, which says availability zones, location, capacity mode, and everything. Now, if you see a message here, it says the first 1000 RUs and 25 GB is free for the free tier account. So we'll click on the apply, which is by default for apply free tier. So you'll be not charged anything if you utilize only 1000 RUs and up to 25 GB of Azure Cosmos DB space. So we'll just click on global distribution next. I'll not change anything here. I'll click on networking. No changes here. I'll click on backup policy. No changes here. I'll click off encryption. No changes here. Click on tags. Nothing to change. Click on review and create. Great. No errors here. The validation is success. And let's go ahead and click on create. It will take some time in order to create your Azure Cosmos DB. Let's wait for it to complete. Great. Our Azure Cosmos DB is provisioned. Click on go to resource. Awesome. This is our Azure Cosmos DB platform. Now, in order to see the data, you just need to go to the Data Explorer. Now, once the Data Explorer is open, you can see there is nothing in our Azure Cosmos DB. So the first thing is we first need to create a container. In order to do it, you click on new container. So in order to have a container, we first need to define a database. So I'll keep the database name as is with data. Great. I'll keep the throughput as manual because we don't want to charge ourselves, right? So I'll make it manual and I'll keep the request unit maximum as 400. Now, next step is to define the container ID. Now, since we were working with device data, I'll just type device data as my container. Now, the next step is to define a partition key. Now, if you remember our payload for device, which looks something like this, so we can define the customer ID as our partition key. So in order to distribute our data based on customer ID, we'll just copy customer ID from here. We'll come back to our Azure portal. We will put a slash and customer ID here. So our partition key will be based on customer ID. Next, we need to define unique keys. Now, unique key can be a combination of one or more keys. But in our payload, we already have event ID, which is basically an unique key. So I'll just copy this. As usual, I'll put a slash and I'll put unique key as event ID. Now, suppose if you want to put anything else which is nested, you can put one more slash and define the name of that column. For me, it's event ID. So I'll keep it as event ID. Now, this is my unique key. Now, you can have the combination of more than one unique key for a particular container. Next, I'll not do anything and I'll just click on OK. Awesome. Now, if you see on the left side, you will see our database is with data. If I expand this, you will see the container device data, which is basically the table for us. So if I expand this, right now, there are no items. It means it does not have any record that has been stored. So let's go ahead and create our first item. So I'll click on this and then I'll click on new item. Now you will see a JSON payload here, right? So we have our device data payload. Let's just copy and paste it here. So I'll copy my device data payload and I'll paste it here. So once we have pasted our device data payload, let's click on save. Nice. If I expand it to the right, you can see the customer ID has been used as the partition key, and you can see the ID, which is the unique key that we have defined, is the event ID. Now, if I scroll down in this payload, you can see some of the columns that has been added by Cosmos in order to make sure that it maintains the audit properties. Now, Cosmos by default copies and creates a unique ID, which is named as ID, which will contain the data, whatever you have defined as ID. So in our case, event ID has been copied as ID. Now you can see some underscore columns, which are the audit columns that has been added by Azure for its purpose. So you can see we have added an item here. We can go ahead and add more items. So let's go ahead and add one more. So I'll click on new item and I'll copy the device data from my sheet. I'll just copy one of the device data here and I'll paste it here and I'll click on save. Great. Now if you see, the structure for this payload is different. We do not have anything inside the devices, whereas the structure for the previous payload has some of the data inside this. So here the structure of your data itself is different. And still the Cosmos DB is supporting both the payload structure. And this is the beauty of NoSQL databases. You can have different structures for the same container. So each of the structure would be saved as a different item. Great. Now that our setup for Azure DB is complete, let's go ahead and use Spark in order to read and write the data. Now, in order to work with Cosmos DB in Spark, the first and foremost thing is you need to import the required jars. For this, we have utilized, you can see com.azure.cosmos.spark, and it utilizes a version 4.5.0. So we have imported this using the help of our spark.jars.packages in our Spark session. So let's go ahead and run our Spark session. There is no change for the other attributes in our Spark session. So let me go ahead and run this. So our Spark session is up and running. Spark has already imported all the required jars in order to make sure it can work with Cosmos DB. Now, the next important step is, in order to work with Cosmos DB, we first need to connect with Cosmos DB. So we need to define some of the configurations to make sure that we work with it. So the first config is spark.cosmos.account endpoint. It is the endpoint of your Cosmos DB. You can find this information in your Azure portal. So once you are back in your Azure DB Cosmos portal, on the left hand side, you just need to scroll down to keys. Click on keys. And here you can see the URI. Now, a word of caution here. Anything that you see on the screen is sensitive. It means this needs to be a secret. You don't need to share this with anyone. If someone gets access to your keys, they can very well access to your Cosmos DB account. But I'll show this to you today and I'll automatically rotate my keys and remove them from my Azure account in order to make sure that you're not able to access my Cosmos DB. So even if you try to use my key and access my Cosmos DB, you will not be able to do it. But let's go ahead and first put the endpoint. So I'll just copy this URI and this would be my Cosmos DB endpoint. So I'll paste it here. Great. Now we need an account key. You can see spark.cosmos.account key. Let's go ahead back to our keys and you can see primary key and secondary key. You can just copy any one of them. So I'll copy the primary key. I'll click on that show button and you can copy this key from here. And you can paste the secret key here. We are almost done with the security settings. Next is the database. So our database is same, which is is with data, and our data container is device data. So I'll just rename it to device data. Great. Our config is ready. Now, you might be thinking it's not a good idea in order to put your secrets like account key and endpoint in a script. That's correct. In the end of this course, we will see how we can hide this information and make sure that that is not written in our script. That we will do in the end. Before that, let's go ahead and read and write data from Cosmos. So in order to read the data, let's go ahead and create our DataFrame DF. So to read the data, I'll just write spark.read.format Now, the format for Cosmos DB would be cosmos.oltp. We need to define some options in order to read the data. So I'll put options, and these options would be the config properties like account endpoint, account key, database name, and container. So I'll just copy the config and I'll expand it here. So I'll put double star and I'll put config. Now, since we are reading JSON data, so we want to infer the schema while reading. So we'll put that also in the option. So I'll write option spark.cosmos.read.infer schema enabled as true. So it will read by default the schema of the JSON payload that we have saved as items in our Cosmos DB. Now we just need to put load. I'll close the brackets, and before we run this, let's go ahead and run our config, and then we run our DataFrame query. Great, our DataFrame query is complete. Let's go ahead and see the scheme. So I'll run the print schema. Nice. You can see it is reading the structure from the Cosmos DB. Now, if you want to see data, you just need to write df.show. So I'll run this. Great. Now you can see the data for both the items that we have saved in our Cosmos DB. You can see both the data here and all of the columns that we are reading from Cosmos. Now, if you are seeing, we are reading the ID and event ID both from the Cosmos, because this ID has been added by Cosmos DB in order to make each of the payload unique. Now, we have read the data from Cosmos DB. Let's go ahead and write a data in Cosmos DB. So I have some device data payloads here. So if I open this, you can see the device data JSONs here. Let's go ahead and write this JSON as items in my container. So in order to do that, I'll read that JSON first in form of JSON. So I'm writing a df as dfread spark.read.json and the JSON file, which is the device03 JSON file. Okay, let me show you the data first. So I'll run this. Great, you can see the data, right? We are going to write this data in Cosmos now. Now, in order to write the data, first we need to add the unique key column, which is the ID. Since we don't have the ID column here, we need to create it. So I'll create that column. So I'll write df.read.with column. I'll create the new column, which is ID, from the column which is event ID, because our event ID is the ID column, right? So this is our with column. Now that we have created our event ID, we need to specify the format, which is dot format, which is again cosmos.oltp, and we need to specify the configs for loading the data. So we'll write options, which is again the same config. So I'll write ** config, because we are writing to the same database, same container, using the same account name and secret, right? And we need to add one more option here. This is important. There are multiple write strategies available for Cosmos DB. It means it can update the same item, it can delete the item, it can overwrite the item, it can append the item, it can patch the item. If you see this Git documentation, it provides you the different writing strategy that Cosmos gives you. So it is item overwrite, item append, item overwrite if not modified, delete if not modified, item patch. There are multiple writing strategies. So in order to write the items properly, you need to define the write strategy. Since we are going to append an item, we'll just copy this write strategy from here. So I'll write option and I'll specify the write strategy as item append. Because we are going to append an item, we are not going to change anything. In order to make sure we are not overwriting our container, we need to specify the mode, which would be append. And in the end, we will write save. Now, you might be thinking, what is this item append and what is this append? Now, you just need to see this option is the write strategy at the item level, and this option is for at the container level. So if you want to append the data in the container, you just need to use append. Because we have already created that container, we are going to append the item, so we'll use the mode as append. But if you want to do something on the item level, for example, if you want to delete or patch an item, you need to use the correct write strategy for that item. Right now, we are just going to append the data. So I'll use item append. So let me go ahead and run this. Awesome. This is complete, right? So you can see this ID is 1450. Let me go back to my Azure portal. Okay, I'm back in my Azure portal, right? So let me go ahead and refresh. Here is the third item that we have just written. So you can see this item here. So let me expand this and you can see the items here. Here is the complete item. So consider a case if you want to update the same item. So if you have this item and you want to update some data, you need to use the item patch. So just make sure you check this timestamp here. So we'll just try to overwrite this data. So I'll just go back and I'll change this as overwrite. And if I run this again, it is complete. Let me go back. So if you see it is 1114, let me refresh. If I go back and open this, you can see it is 1179. So this data has been overwritten. So in the same way, you can delete the item as well. So consider you want to delete this item. Let's go ahead and change it to item delete, and let's run this. It is complete. Let me go back and refresh it here. See, the item is gone. So now you understand how you can manipulate the items from Spark very well. Now, coming back to the secret settings. Now, you don't want to keep your account endpoint and account key secret in the script. You want to make sure that these are hidden from the developers. So in order to do this, you need to keep them in the Spark default setting. So to do that, let me go back to my Spark install. So my Spark installation is at user local Spark. So I'll click enter and I'll just type LL. You can see here conf folder, right? Just go into that conf folder and put a LL, and you can see the Spark defaults, right? Right now it's a template. It is not being used. Let's go ahead and change this. So I'll just copy the name here. I'll write move and I'll paste it here. And again, I'll remove the template from the end. So I don't have permission. So let me put sudo in the same command. Sudo. Okay. Now this is done. So if I put this, you see the name has been renamed. Let's go ahead and add the setting there. So I'll just put sudo nano and I'll write this file. So copy this, I'll paste it here. I'll hit enter. And let me go back and copy this setting. So I'll copy this endpoint here. I'll come in the bottom. I'll paste it here. I'll put a tab, then go back. Copy this setting from here. Paste it here. Come back. Copy the account key. Paste it here. I'll put a tab. And copy the secret. So I'll copy this. I'll paste it here. I'll just save this and I'll exit. Great. Our Spark default has been changed. Now, in order to load the Spark default, we need to restart our Spark session. So I'll just go to the kernel and I'll click on restart and clear all outputs. So I'll do a restart quickly. Great, I've restarted. Now I have to remove this config, right? This is no longer required to be kept in the script. So I'll remove this and I'll go ahead and run my Spark session. Once I run my Spark session, the Spark default settings will automatically be loaded into the Spark session. So our account settings and the secrets are now available in the Spark session itself. So I don't need to specify in config. So I'll just go ahead and specify the database and the container name. So I'll run this and now we'll read the data from the Cosmos. So I'll run this. Now I'll run the print schema. You can see the schema, and if I run the show, you can very well see both the data is reading from Cosmos, right? So our Spark's default setting has been picked up automatically, and now you don't have the secrets in the script. And this is the way how production code is being implemented for Cosmos. So you don't need to keep your secrets in the script. You can very well keep them in Spark default configuration so that the developers don't have access to the secrets. Great. Now we have completed the end-to-end implementation for Cosmos DB. I hope you have learned some basics about Cosmos DB and how to utilize Cosmos DB with Spark. Now, before I wrap up this session, let me go ahead and show you how to rotate your keys in order to make sure no one else accesses your Cosmos DB. So I'll go back to my Azure portal. I'll go to keys. Now, since I have already shown you my primary key, I'll click on this button in order to rotate the key. So once our rotation about the keys are complete, no one else can use our old key in order to access our Cosmos DB. And this is how our Cosmos DB is safe. Today we are going to discuss about Delta Lake. Now, Delta Lake is getting very popular with Lakehouse architecture because it enables you to create Lakehouse architecture on top of your data lake. Other than this, Delta Lake has a lot of benefits. So if you go to this homepage of Delta Lake and you scroll down, you can see it has a lot of key features which are not available by default with your big data or the data lake. The first and the most important is ACID transactions. Delta Lake by default support ACID transactions. And the second and the most important is time travel. So in Delta Lake, you can go back in time to see what was your data. And even if you have some issues, you can roll back to that version of that data. The third and the most important is schema evolution. It means it will prevent your data from getting corrupted in case of any bad operation. And the final and the most important is DML operations. You can run update or delete queries on top of Delta table, which is not possible by default on a Parquet or a Hive table. Now, other than this, you can see there are multiple more features like scalable metadata, batch and streaming support, open source, audit history. These are all the features that Delta Lake support. And with this supported features, Delta Lake is bringing a lot of difference in the data warehouse structure that you built up on your data lake. And thus, the lakehouse structure is being created. Today, we will see the majority of them with demo. Now, before that, if you have not subscribed to my channel, Ease with Data, I want you to go back to the channel, subscribe my channel, and you can find a lot of playlists based on data engineering. The most popular are Spark Streaming and PySpark 0 to Hero. Go ahead and check them out. For today's session, we are going to use Databricks. Now, Databricks is not free for everyone. but it provides us with Community Edition. You can use Community Edition to run your queries for free. Today, we are going to use Databricks Community Edition in order to try out Delta Lake. Now, Delta Lake is by default supported by Databricks. It is an out-of-box feature that has been provided by Databricks, and Databricks is utilizing Delta Lake for its lakehouse architecture. So, if you have not signed up for Community Edition, you can go ahead and do it. For that, you just need to go to databricks.com and you have to click on this Try Databricks. Once you are on this form, just fill it up, and on the next step, you just click on Community Edition. And once you are done, you will have access to Community Edition. Now, once you have access to Community Edition, to log in, you need to go community.cloud.databricks.com. Once you are on this page, you just need to provide your email ID and password and just click on Sign In. Great, you will see a Databricks workspace available for you. The most important tabs are Workspace and Compute. Now, in order to make your notebooks run, first you need to create a compute. So we will go to this Compute tab and we will click on this Create Compute. Now, by default, Databricks allows you a shared cluster with only one driver of 15.3 GB memory and 2 cores. So just put any name for this cluster. So we'll put Delta Test and we'll click on Create Compute. So once you do this, let me go back to Compute again. You will see a compute being created. While this compute is getting up, let's go ahead and create our first notebook. To do that, I'll click on New and I'll click on Notebook. So I've already created a notebook for me. So I'll just go to my users and my name and I'll click on my notebook. So this is the notebook that we are going to use. Now we have to connect to our compute. So I'll click on this unknown and I'll click on the compute, which is right now starting. So you'll see it is starting. Now, once this is started, we will be able to see a green icon informing us that compute is ready to use. And once that is ready to use, we'll start running our code. So till then, we will wait. Now, if you can see, our compute is up and running. It is a green icon which says Delta Test and it is connected, right? Just to check if it is working fine, I'll just type Spark and I'll run this code. And to run, I'll click on Shift and Enter. Great. Now you see an output here. It means our compute is up and running and our Spark session is also ready. Now, by default, whenever a compute is created and it is attached to your Databricks notebook, it provides you with the Spark session pre-created. So your Spark session object is already created with the name of Spark, and you can go ahead and use this Spark session variable to run your Spark queries. Now, from this output, it is quite visible. The version of Spark is 3.3.2, and we are having a master of local of 8, and app name is Databricks Cell. So this is fine for us. Let's go ahead and see what is the catalog implementation that Databricks provide out of the box. To do that, I have written a spark.conf.get and spark.sql.catalog implementation. So this will provide us the catalog implementation that Databricks support out of the box. So I'll run this. You can see the catalog implementation is Hive. So Delta Lake has a persisted Metastore where the implementation is using Hive. So in order to check the catalog, you can just go ahead and run Spark SQL queries. Now, in order to run a query in SQL in a Python notebook, you just need to put %SQL and you can write show databases. And once you do this, it will show us all the databases that are provided using this SQL command. So in order to use a SQL command in Databricks, you just need to use %SQL if you are using a Python notebook. But if you want to use this whole notebook using SQL, you can just go ahead and change it from here. But today we are going to use it as Python. And in order to run a SQL query, we are going to use a magic command called %SQL. So to show the databases that are available in Hive, I'll just run show databases. It will show us the database which is by default present, which is default. Okay, now I have some Parquet data already there in the DBFS location of Databricks. So to show you that data, I'll create a data frame called df sales and I'll read this Parquet data using spark.read.parquet. So I'll run this. Awesome, this data frame is created, right? Now to view the data, I can write df_sales.show. So as soon as I run this, I'll be able to see the data that is present in this sales data.parquet. Great, you can see the data that is present, right? But Databricks provides us with a very good utility in order to have the data properly formatted. So to do that, I'll just write display and again the data frame name. Okay, this will also do the same work that we are doing using show, but in a neat way. So you can just see it will provide us the results in a beautiful tabular format. Now you see this data. It has provided us the data in a beautiful tabular format. So you can use this display command in Databricks to see any data in a data frame. Okay, so you can see in this data we have 4 columns: transacted at, transaction ID, retail, and description, right? Now we have read this data frame as df sales, right? Let's go ahead and create a Hive table using this data frame. So to do that, I'll write this data in form of Parquet tabular format. Okay, so I'll write df sales dot write dot format, and the underlying format would be Parquet, and I'll put an option which would be the path where I'm going to save this data. So I'm going to save this data is underscore data, and we have it in input, so I'll put it in output, and I'll put it as sales hive, or say sales parquet, and we will name it as underscore one just for our satisfaction. Okay, and we will save this table as table. Okay, so I'll name this as sales parquet. Okay, and I'll just put a mode as override, so if there is any data it will just overwrite, so I'll put the mode as override. Okay, let's go ahead and run this. Awesome, it completed, right? So our table is ready. Now before we see the table, let's go ahead and view the files in this location. So I'll just copy this path from here. Now in order to see the file structure in Databricks file system, you just need to use dbutils command. So that is dbutils dot fs is for file system, and ls is to list the data into that folder structure, right? So I'll just use double quotes and paste this structure here. So I'll run this. Now you can see all the files listed under this. Now if you want to see this again beautifully, just use display. So I'll just use display, and in the end I'll put like this. Okay, I have to change it to display, so I'll rerun. Great. Now you see we have written a Parquet file here. It is under this output folder, right? So this is a Parquet folder structure right now. Okay. Now we can go ahead and check the Hive catalog to see if this table sales Parquet is registered in this database or not. So to do that, I'll just write percentage SQL, and I'll write show tables in default, because our database is default, right? So I'll just write show tables in default, and I'll run this. Okay, I have to remove this comment from here, and I'll rerun. Okay, now you can see this is a sales Parquet table which is registered under this Hive database, and this is not a temporary but a permanent table, because we have already registered this table as save as table with sales Parquet name, right? So this is already available. Now if you want to see the metadata of this table, you can just go ahead and use this same SQL command. So I'll use percentage SQL, and I'll write describe, and I'll use this table name. Okay, so I'll use sales Parquet, and I'll run this. So I can see the column names and data type. Now, if you want to see more information about this table, like where it is stored and what is the format of the table, you just need to use extended. So I'll write extended, and I'll again run this command. Okay, now I can see the column names, and if I scroll down, so it just gives me information like it is an external table, it is a Parquet table, again the location where it has been stored. So it is an Hive Parquet table external, right? Because we have supplied the location where we need to save this table. This is not a managed table because we have provided the location. Okay, so this is an external table, but this is a Parquet external table in Hive. It means we will not be able to update or delete any data in this table. So just to show you, let me just run some SQL queries. So I'll write select star from sales default dot sales Parquet. So I'll run this. Okay, you can see this data, right? Let's put out any transaction ID, for example this one. So I'll copy this, and I'll just put where TRX ID is equals to this ID. Okay, I'll run this. So I'm able to see this data, right? You can see the amount is 8.58. Okay, let's go ahead and update this amount. So to do that, I'll write update this set amount is equals to 0, for example. Okay, let's run this. Okay, as soon as I do that, you can see an error here, right? By default, Hive does not support DML operations such as update or delete. Okay, so it is not working for a simple Parquet table which is there in our Hive catalog right now. Okay, now that we know DML operations are not supported for a Parquet table, let's go ahead and write that same sales data in form of delta table. So we have the DF sales data, right? To write it as delta table, I'll again write df sales dot write dot format, and this time in place of Parquet I'll put delta. Okay, and I'll use again the option, and I'll put path where I need to write the data. So we'll write at data slash output, and I'll write it as sales delta underscore 1. So I'll just put 1. Okay, and I'll write save as table because we want to save this as table as well. So I'll write sales delta. Okay, now I'll just put mode as override so that if there is any data it will get overwritten. Okay, so this is okay. Let's run this. Okay, the data is written, right? Now we can go ahead and see the catalog in order to see if the table is registered or not. Okay, to do that I'll put again Spark SQL, and I'll write show tables in default, right? So if I run this, now you can see another table called sales delta. Okay, now in order to see the metadata, we can again use describe extended. So to do that, I'll write percentage SQL and I'll write describe extended, which is our sales delta. Okay, I'll run this. Okay, same column names and data type, but this time if I scroll down, you can see this is external because we have provided path here, right? But if I scroll down, the provider is delta now because this is a delta table now. Okay, you can see at this path we have saved our delta table. Okay, now they have different properties here. You can see minimum reader version, minimum writer version. So these are different properties that delta live out of the box provides. Okay, so this is our delta table now. Now what is happening in the path where this table is written? So this table is written at this path, right? So I'll just copy this and let's go ahead and check the folder structure there. So to do that, I'll write display, and within display we will use our dbutils command. So I'll write dbutils.fs.ls and I'll put this path. Okay, let me run this. Awesome. Now if you see, it has written the data in Parquet format, but we have one more folder here called delta log. Let's go ahead and check out what is inside this folder. So I'll just put this delta log folder here and I'll rerun this dbutils command. So if you see, we have some files which are the metadata for delta written here, but the most important is this JSON file. Okay, so delta lake saves its metadata in form of JSON files. Okay, so that it can provide the DML operations or the ACID transactions, the properties it has, right? Audit logs that is being maintained in the form of this JSON files. Okay, so under this folder delta log, it saves all the metadata that is required for its audit log or the time trouble or the DML operations. Okay, so this metadata is something which provides data lake its ability for all the features that you have seen, right? So let's go ahead and check what is inside this particular JSON. Okay, to do that, I'll just copy this location. Okay, and again I'll run one more command dbutils.fs.head in order to see what is inside this JSON. Okay, I'll put this. So let me go ahead and copy this JSON file from here and I'll put it here and I'll run this. Okay, if I run this, you can see a whole lot of things inside this file. Okay, the most important thing is the Parquet files. You can see the path where it is mentioning which Parquet file to read for this particular version. Okay, so this is how it is maintaining all its metadata here. Okay, now that we know what is there inside this JSON file, let's go ahead and see this in form of versions. So to do that, I'll just click on code and I'll write percentage SQL and I'll write describe history. Okay, for this table, which is sales underscore delta. So I'll run this. We'll wait for this to complete. Okay, now this has completed. Okay, let me just expand this here. Okay, now you can see only one version data, which is 0. This is the same information that you get from this JSON file as well. Okay, this is 0th version JSON file and you have this information here. Okay, now if you see, we have only done one operation, which is create table. So we have just created this table. This is the only operation and you can get all other metadata informations here. Okay, the most important are the operation metrics. So if I expand this, you can see the number of files that has been written. Only one file, because that is what I've just shown you in this JSON file, right? Only one file has been written, and the number of output rows which is there for the sales data. Okay, now you can see how the version is maintained for delta table. Now that we know about versions, let's go ahead and do some manipulations, which is DML operations, in order to see how the versions are maintained after our DML operation. Okay, so we've already seen the delta JSON, so I'll remove this cell, and we have seen the history for the delta table, so I'll also remove this cell. Okay, let's go ahead and update the data. So I'll just copy the same update command that we have run previously. So I'll copy this, I'll go bottom here again and I'll paste it here. Okay, and I'll run it now. Okay, so my bad, I've just put it on sales package. Let me just change it to sales delta. So I'll just change it to sales delta and I'll run this. Awesome. Now you can see the number of affected rows because we have only one row for this transaction ID. So only one affected row, right? Let's go ahead and see the data for that particular transaction ID. So I'll just write percentage SQL and I'll copy this from here and I'll write select star from. I'll put it here and I'll remove the set amount. Okay, and I'll run this. Awesome. You can see the amount is set to 0 now. So delta tables support DML operations. Okay. Now let's go ahead and see what is there inside this table now. Okay, in this delta log. Okay, and also in this path where we have our delta tables, right? First, let's go ahead and check the path. So I'll remove this delta log from here and I'll run this. Okay, now you can see one more Parquet here, right? Let's go ahead and put the delta log and let's run this. If you can see, we have one more JSON here, right? 0001. Okay, this is because we have just made one DML operation, because of which delta table has upgraded this JSON. Okay, so I can just copy this and paste it here. And if I run this, you will see an operation called update is done. Okay, so this is how it maintains. Let's go ahead and see the history. So I'll rerun this history command here. Now if you see, there's one more version 1 created. Okay, and if I scroll to right, you can see the operation is update. And if I scroll more to right, you can see the metrics operation here. So I'll just scroll more. Okay, here you can see the number of removed files, and you can see the number of affected rows, which is 1. Okay, this metrics information provides us a lot of information about each version. Okay, so this is maintained in the metadata here. Great. Now that we know how to do DML operations, what are the version informations in Delta Lake, let's go ahead and use the Delta APIs that has been provided for Python for the same operations. Okay, now we will read the delta table using PySpark APIs. Okay, till now we are doing this using SQL. Let's go ahead and read this using DataFrames. To do that, I'll just write df sales and I'll write delta. And to read the delta table, you can just write spark dot read dot, since we are registering this as table, so you can just write table, and we can read sales delta. So I'll just put sales, and under this we can write delta. Okay, so if I just use display and I'll write df sales delta, and if I run this, great, you can see the data here, right? Now what if this table is not registered as delta table but has been written at a path? Okay, to do that you can just use format and you can use delta, and you can just load it from that location. Okay, so you can just provide the location where we have written this data. So I'll just go ahead and copy this from here. I'll come back and I'll put it here. Okay, so if I run this again, that same output, right? So you are able to load the delta table from the path, plus you can read it directly as table. Now again, you can read a particular version of a table directly as well. So to do that, you can just go ahead and use table, and you can put the table name, which is sales underscore delta. So in order to read a particular version, you need to provide the version. Now if you don't provide the version, whatever is the latest version, that will be read, right? So our latest version is 1, right? But if you want to read the version 0, you can just provide it like this, at the rate v0. So if I run this, this is the data for version v0. You can also verify, you can just use this transaction id, for which we just changed the amount to 0, right? So you can just go ahead and use this to see if we are reading version 0. So I'll just put where, and I'll put it here. I'll remove this here and I'll run this. Awesome. Now if you see, you can see the amount, right? Now I'll just change the version to 1 and I'll run the same command. Okay, the same command, you can see the version as 0, right? So you can read a specific version based on how you read it from the table. Okay, so this is one. Now what if you want to do it in using SQL queries? You can again do it. So you just need to use percentage SQL here. So to do that, you can just write select star from, and you can use the table name with the version name. So I'll just copy this and I'll paste it here and I'll run this. So it is reading from version 1, right? So just to verify, I'll again use that where command. So I'll just copy this transaction ID and I'll put it here where this, and I'll run this. You can see the amount is 0, right? What if we change it to 0? I run this and you can see it to 8.58, right? So you can read a particular version like this, okay, for SQL queries as well. And this is the benefit that Delta Table provides. You can go back in time and watch the version of data. Let's understand what is schema evaluation. So delta tables by default provides you the proper schema as per the metadata. Okay. Now, what if I go ahead and add one more column for a particular transaction ID? So it will help us to remodify our whole data set by default, right? So to do that, for example, let's take this transaction ID and I'll add one more column here. Okay. So to do that, I'll just make it like this. I'll add one more column called current timestamp as time now. I just need to make it percentage SQL in order to run, and I'll run this. Okay, I just added a new column called time now. right? So in order to make it work, what I'll do is I'll convert this SQL to a data frame, and I'll try to add this transaction ID inside this already created delta table. Okay, so what I'll do is I'll just create a data frame. So I'll write df new, and I'll use spark dot SQL, and inside this I'll put this whole command. Okay, and I'll remove this SQL from top, and I'll just display you so that you know what is there inside this data frame. So I'll make df new, and I'll run this. Okay, you have this data. Let's go ahead and write this inside the same data frame. To do that, what I'll do is I'll write df new dot write dot format, which is again delta, and the mode would be append because I'll be adding this, right? So I'll just write append, and I'll put the option where I'll say merge schema as to. It means please add this in the same schema but merge it, add the new column to the existing schema. Okay, and I'll say option, and again I'll put the same path and load, right? So I'll just copy it from the top. I'll just go here and I'll copy this whole thing, and I'll come to bottom and I'll paste it here. Okay, and I'll run this. So I have just made a mistake here. I'll make it a pin and I'll rerun this. Okay, sorry, my bad. The option is merge schema, so I just missed the A here. Okay, I'll run this. Okay, now it has completed successfully. Let's go ahead and check the version. So I'll just come back here in the top. Okay, and I'll run this describe history. Now you can see there is one write operation because we added, right? So let's go ahead and see the data. So to do that, I'll just come here and I'll run this from the same data table. You can see the time now. For the old record, it was 0, and we just added one record here, right? That was with the timestamp. Now, if I remove this, you can see the time now column added for all the records. Okay, so if I scroll to right, you can see the time now is null for all the records. So delta table has by default managed that schema. Okay, whatever the new column that we added, it has been added for all the records, right? So it has managed that schema evolution by default. Okay, so that is what is one more benefit that delta table provides. Now in case of Parquet, you have to rewrite the whole data adding that column. That's the problem that we have with Parquet and Hive table. Okay, but in delta table, you just use this merge schema option and you append the new record with the new columns. Delta table will by default take care of all the rest of the records. Now, delta table also provides us libraries in Python that we can use to manipulate delta tables. Okay. Now, so from delta, you can import this delta table command. Okay. Now, to read a delta table by name, you can use the Spark session. I'll just use DT, which would be my delta table, and I'll write delta table dot. I'll use for name because we have created table with name, right? We'll use the Spark session, which is Spark, and we will use the delta table name, which is sales underscore delta. Okay, and if I run dt dot, and I just want to show you the history, so I'll just type history, and if I run this, you can see it has created a data frame. Okay, so to see a data frame in a proper way, you can either use show or display. Okay, let's use show here. Now you can see the all information about the history, okay, using delta table APIs. Okay, now if you want to see this beautifully, you can just use display command, right? So I just write display and I'll just rerun this. Okay, now you can see the same version information here, right? That has been provided. So now let's go ahead and convert an existing Parquet table into delta table. Okay, delta table libraries provide us with that information. Now first let's go ahead and check if that particular location is a delta table or not. To do that, you can just write delta table dot is delta table. Okay, and now you have to provide two options. The first one is Spark session, so you can just write Spark, and the second is the location. Okay, so let's just go ahead and paste that location where we have our data. So I'll just write data slash output slash sales Parquet underscore 1. Okay, let me just run this, and you can see it says false, means it's not a delta table. Okay, let's verify our delta table. So I'll just remove this Parquet and I'll write delta, and I'll run this. It says true, it means it's a delta table. Okay, what if I want to convert my Parquet table, which is at this location, to delta table? Okay, so this is at this location, right? But this is not a delta table. I want to convert this. To do that, I can just use delta table dot convert to delta. We have to provide the Spark sessions, all right. Spark, and we have to provide the option as Parquet. So I have to write Parquet dot, and then we have to provide our location, okay, in tick mark. So you can see this is tick. I have put it as tick. So I'll just put it here and I'll change it to Parquet, okay, and I'll run this. Awesome, it has completed, right? Let's go ahead and validate this location. So I'll just use display and dbutils.fs.ls, and I'll put this location and I'll run this. Okay, now if you see, we have delta log here. It means it's a delta table now, okay, as per the path. But if we try to check our metadata now, so I'll use percentage SQL and I'll write describe extended and sales Parquet. And if I run this, if I scroll here, you can see still Parquet, okay, because the metadata is not updated. We have written a delta log here in order to convert it to delta table, but we have not updated our metadata. To do that, I'll change it to percentage SQL and I'll write convert to delta and the table name, which is sales dot Parquet, and I'll run this. Okay, sorry, my bad, it's sales underscore Parquet. Okay, let me run this. Awesome, it says okay. Let's go ahead and again see the metadata for this table. So I'll run this. Now if I scroll down, you can see this has changed to delta. Okay, now we have successfully converted our Parquet table to delta. Awesome. Now one more thing. So we are reading particular versions of data, right? So we were reading particular versions of data here using SQL commands, right? V0, V1. What if we want to revert back to a particular version? For example, if you see the version for this table, delta table right now, it is 2, right? What if I want to revert back to 1? Can we do that? The answer is yes. So to revert back, you can use SQL queries. You can write SQL restore table and the name of the table, which is sales delta to version as of and the version number. For example, we want to go to 1. Okay, so let me run this. If you see, we have updated the version. Let's go ahead and verify. To do that, I'll use the percentage SQL and I'll write describe history of sales delta. I'll run this. Okay, now you see one more version here. It says restore. So we are restoring one more version here, right? So if you want to see the data, you can just go ahead and write select star from the sales data, and I'll use the same transaction ID. Okay, last time we had 2 records for that because we just added 1, right? So I'll just use this. And I'll place it here and I'll run this. Okay, you can see the amount as 0. What if you want to see the older version? You can use it, right? V2. So if I run this, this was the version V2 which we have, for which we had 2 records, right? So we have restored to version 1. Okay, so the version 1 is right now this value, right, which we have for our default version 3. Okay, which we have restored, okay, which is 0 again. So this is how you can revert back to a particular version. Okay, now if you go back to the same location again to the of the delta table, so I'll just go back to the location here and I'll remove the delta log and I'll run this. Okay, you can see so many Parquet files being written because every time when you manipulate a version, delta table tries to rewrite a different version of data in different Parquet files in order to maintain that time travel, right? Now consider you are writing 200, 250, 300 versions, so will have a lot of data here, right? And that's not wise. You have to clean it up, and in order to do that, delta tables provide us with an option called vacuum. Now to do that, you first have to read it in form of delta table. So I'll read as delta table dot for name and I'll write Spark, and the name of the table is sales delta, right? And to do vacuum, we'll remove all the unnecessary versions now. So I'll run this. So you can see it says there's a retention period that has been provided. Now for your delta table, if you set it to 0, that will create some problem, and that default retention log can be removed using this Spark configuration. You have to set spark.databricks.delta retention duration check enabled as false. So this time it will not check the default retention duration, rather whatever is the data, it will manage it. Let's go and do this. So this vacuum operation has now removed your all older versions and you will have your latest version as the latest one. Okay, just to verify if you have the data removed. So I'll just use the dbutil command for that Spark delta location. Okay, so I'll just go ahead and run this. Now if you see, you have only one Parquet file and all other unnecessary Parquet files are removed. So what happens to the metadata? Let's go ahead and verify. To do that, I'll write describe history and I'll put the sales delta table here and I'll run this. Now you can see the versions are still available, right? 3210. Let's go ahead and see the data to understand what has happened. Okay, so I'll just write select star from, and by default this is the version 3, right? And I'll put the where condition in order to see the changes in the transaction ID. Okay, so I'll run this. You can see the amount as 0. Okay, now for v2, if you remember, we had 2 records, right? So if I run this, you are not able to see the v2. Okay, because there was data which is now removed because we have vacuumed, right? Now if I try to make it v0 and if I try to run it, you can see the same error, right? Because Spark has removed all the older files. Okay, the versions are still there, but you will not be able to access. The time travel is now not possible because you have vacuumed the data, and that is why vacuum is a very important operation that you have to do carefully, because if you want to retain up to some versions, you have to be very carefully doing the vacuum for that particular time. Okay, you cannot just go ahead and make it as vacuum 0. In vacuum 0, it would remove all the time travel information and only the latest would be preserved. Okay, so this is very important. Now, the last operation is converting to Parquet. What if I want to convert a delta table to Parquet table? Is it possible? The answer is yes. And we have already covered a lot of things in order to answer this question. Now, I want you people to try it out. Now, I'll be posting the answer of this question in the comments, but please go ahead and try this out. How to convert a delta table to Parquet. Okay. This was all for today. Now, we have learned a lot of things about delta, and this is very important to get you started with delta tables. Now, if you want to play around with delta tables, I would recommend you just go ahead and subscribe to Community Edition of Databricks and try it out. Today, we are going to discuss one of the most important topic, which is data scanning. Now, in big data, since our data lies in form of file formats, it is very important that we avoid unnecessary data scanning. Now, we have multiple ways in which we can avoid unnecessary data scanning. One of the most important is partitioning. Today, we are going to see the impact of partitioning. Now, partitioning is a very important topic when you are dealing with big data or data engineering. So, you need to be very careful when you are partitioning your data. Today, we are going to see all of this with a live example. So, without any delay, let's begin. Okay, now let's understand why data scanning is important. So, we know that whenever we are reading data, most of our data in data lakes are stored in some file formats. Now, this file format can be Parquet, CSV, Avro, anything, but the data is stored in almost all the cases in file format. Now, consider we are a retail company where we receive orders from multiple geographic regions, and it can be any country. For example, it can be India, USA, Australia, etc. Okay, it can be from any geographic region. Now, you're capturing orders in form of Parquet in your data lake. So you can see these files which are all kept under the file location for your orders data, right? Now, since these files are not segregated, each of the file can contain the order information for any geographic region. Okay, it can have, so the part 001 can have the data from India, USA, Australia, and any other countries as well. Okay, now consider you have to search information for a particular order. For example, let's take ORD 1001. For this order, if you have to search the data and you know that this order is from country India, right? But if you have to search this data, and since this data is not segregated, we have to scan all the 4 files in order to find out this data. Now, it can be that this data is in part 002, but you are not aware of it, right? In that case, this whole data scan has to happen. So, Spark has to go and read all the files in order to find out which particular file contains this order information. But we know that this order is for India and this particular order ID. But the problem is, since our data is not segregated, we have to go ahead and read all the data. And this is unnecessary data scanning. And because of this unnecessary data scanning, the time of our query execution would increase. So what is the solution? The best solution is partitioning. Consider we have segregated our data or partitioned our data in form of country. So if you can see, now we have partitioned the data where country is equals to India for India, where you have the data lying for India, right? Similarly for USA, similarly for Australia. Now you can have for any other countries as well, right? But now your data is more partitioned. Now, if you are going to search for that particular same order ID, ORD1001, we know this order is from India, right? So we put where country is equals to India and order ID equals to ORD1001. In that case, the query is going to only scan this particular partition. It is not going to scan the partitions for US and Australia. And it reduces the time for your query execution because this unnecessary data, whatever is for USA, Australia, or any other country, will not be scanned. It will only scan the data for India. And this is why it is very important that you partition your data properly. And the partitioning column should be part of your query, right? Now consider you don't know what is the country for this particular order. In that case, again, the query execution will scan all the countries because you have not put the country in the filter condition because you are not aware of it, right? And this is why the partitioning is very important. And if you are partitioning the data, it is very important to put the partition condition in your filter query. So your filter query should contain the partition condition. For example, it can have where country is equals to India and order ID equals to ORD1001. Now, what happens if we partition the column on based of order ID, right? Because we are searching majorly the data in form of order ID and which is the part of our predicate. So why not partition the data in form of order ID? In that case, we will have multiple partitions. So partition ID with form of order ID, which is a high cardinality column. When we talk about high cardinality column, it means it will have order ID unique. For example, you can have order IDs like this. So each partition will contain a single file in that case, right? So you will have files like this for each of the partition, correct? And this will lead to small file issue because when you start searching for a particular ID, in order to find that partition itself, the Spark has to struggle because there will be so many partitions now, which will lead to small file issue. So it is very important that you should always know what is the particular partition that you have to select for your dataset. And it is also important to put your partition as a part of predicate. When I say predicate, it means in the filter condition or in the joining condition so that you can avoid unnecessary data scanning. Okay, now that we understand this with an example, let's go ahead and check this for New York taxi data. For today's session, we are going to use the Databricks Community Edition. Now, in our past session, I've shown you how you can sign up for the free Community Edition and you can try it out. I have already created a notebook called Data Scanning and Partitioning and I have my cluster up and running, which is of one node cluster. Okay, for today's dataset, we are going to use the New York taxi dataset, which is already present in this particular location in your Community Edition. You can go ahead and check this out. So I've copied some of this data at a particular location in my particular personal folder, which is data input New York taxi and in form of Parquet. Okay, this particular dataset consists of the New York taxi trip details. Let's go ahead and check that out. So to do that, I'll write df Parquet and I'll write spark.read.parquet since the data is Parquet, and I'll copy this location from here and I'll paste it. And let's go ahead and check this data. So I'll write display and I will write df Parquet and let me run this. Awesome. We can see the data where we have multiple columns like vendor ID, pickup date time, end date time, passenger count, trip distance, longitude, latitude, and a lot of columns that is required for the trip data, right? So this data set is not segregated in form of particular vendors. Okay. So let me show you this, how this data set is. So I'll just go ahead and I'll show it to you. I'll write display and we will use the DB utils. So I'll write dbutils.fs.ls and let me just paste it there and let me run this. So you can see we have two Parquet files at this particular location. Okay, so this data is not segregated in any format. Now consider a case where you want to read some data where for a particular vendor ID you want to find out the count for the trips where the trip distance is greater than 1.8. So our query is something like this. So we will have a query where we need to find out, select the count of all the trips from the New York taxi data set. Okay, where the vendor ID is a particular vendor ID which is VTS and the trip distance is greater than 1.8. Okay, we need to find out the number of trips. So since we already have this Parquet data available, let's go ahead and write our where condition. Okay, so we'll do df.parquet.where and we can copy this from here, the same. Okay, and we'll put it here. So I'll just copy and paste it here and we can just do a count because we need to see the count, right? Let's go ahead and run this. Awesome. We can see total 5 million trips happened for this particular condition, right? But what has happened in the background? Let's go ahead and check the background. So for that, I'll go to the compute and to the cluster, which is demo, and to the Spark UI. Now, in the Spark UI, let's go to the SQL and DataFrame tab. Okay, let's go ahead and open our query. So I've opened the first query, and this is our bag for this particular run, right? So let me just scroll down to the scan Parquet where the data scanning happened. So if I expand this and I scroll down, you can see it has read all the 20 million records which was present in that particular location. So for that particular condition, it has to read the whole data set. Okay, now we can see this information from the explain plan as well. So if I go and expand this details and scroll down to the explain plan, you can see the location. And here the particular scan has happened from the root location where the data set is lying, right? So it is reading both the Parquet files and all the data for that particular condition, right? What if we can segregate this data or partition this data based on vendor ID, because the vendor ID is on our filter condition, right? In that case, we can avoid the data scanning. So let's go ahead and partition our data. To do that, I'll use the df Parquet and I'll write in form of Parquet, and we will partition this data based on vendor ID, and we will use the path where we are writing this data. I'll use an option for this, and I'll go and copy the path from top, which is here, and we'll write to a different location. So I'll just go ahead and change this to partitioned. Okay, and we will also register this as table. So we'll do is save as table, and we'll save it as nyc taxi partitioned. Okay, let's go ahead and run this. Okay, let me do one more thing. Let me put the mode as override because the data is already present at that location. So I'll do overwrite. Let me run this. Okay, the data write completed. Let's go ahead and check this location. So I'll copy this location from here and we'll write the display dbutils. Okay, so I'll use display dbutils.fs.ls and I'll paste this location. So now if you see, we have the data segregated in form of vendor IDs. You have CMT, DDS and VTS, right? And if you go into VTS, for example, let me just copy this location. So I'll copy this vendor VTS and I'll place it here. And let's go ahead and run this. And inside this, you can see all the Parquet files present. Okay, so you have segregated the data in order to avoid data scanning. Let's go ahead and check if this happens. Okay, to do that, what I'll do is we will read the partition data from here. So what we'll do is we'll write df partitioned and we'll read the data from this location. So I'll write park.read.parquet and this time we'll read the partition location. Okay, and this time we will do the df partitioned dot and we will use the same filter condition. Okay, so I'll just use this where and we'll place it here. Okay, and we'll run this. Okay, same result, but we need to see it in the background, right? Let me just go back to the cluster details, refresh the Spark UI, go to the SQL and DataFrame tab and to the latest one. Okay, so I'm just opening the latest log. So you can see the DAG again. Let's scroll down to scan Parquet where it is scanning the data. And if I scroll down now, you can see it has scanned less number of rows, which is 9 million and which is only for the VTS. Okay, what is the benefit of this? So if we go back to the SQL DataFrame tab where we were running our jobs, now if you see this particular query ended within 3 seconds, right? Now, if you see this query 8, which we have done previously, where all our data was scanned, let's just go ahead and verify. So if I scroll down and if I open this, yes, all 20 million, right? So for this particular job, if I go back and see the time taken, it was 5 seconds. So we have already reduced the time to almost half, right? Because of unnecessary data scanning that didn't happen. Correct. So this is where the partitioning plays a vital role. You have to be very sure that your data is partitioned on the proper columns and you are using that partitioning column in your predicate or the filter or the join condition, right? Without this, it has to go and scan all the data sets. So what if my condition is only trip distance? There is no VTS, right? In this case, both the data sets has to scan the complete data set because there is no filter on based on the partition, which is our important information here. Okay, so this is the information on data scanning. Now, used PySpark queries till now to do this. Whether it is true for the SQL queries, the answer is yes. Since we have already written the data in form of new taxi partition, so let's go ahead and see this in SQL. Okay, so I'll just use the SQL magic command and I'll write select count one from the table and we will use the same condition. Okay, so I'll just copy this from here and I'll put where and I'll put it here. Okay, and let me run this. So if you see same result, let's go ahead and check the Spark UI. I'll go back and refresh the SQL DataFrame tab You can see it has taken 2 seconds. Okay, let me just go ahead and show you the DAG. So I'll come back to the DAG, and if I scroll down and I open this, you can see only 9 million records scanned, right? Let's go ahead and see the explain plan. So I'll expand the details, and here you can see it has only scanned the vendor ID equals to VDS, which is only for VDS. Okay, so unnecessary data scan has been avoided. So we don't need to read the data which is not necessary. Okay, and this is how you can avoid unnecessary data scan with the help of partitioning. But you have to be very careful of the column that you are using for partitioning. If you use a high cardinality column, you are going to run into small file issues. Okay, and you need to make sure that your partition data has a sufficient volume in order to make sure that you don't run into those small file issues. In our last video, we have seen the importance of data scanning, and we tried to avoid unnecessary data scan using partition technique. Today, we will understand the importance of data skipping. Now, data skipping and avoiding unnecessary data scanning is almost same. Today, we will understand the optimization in Delta Lake, and we will also understand what is the importance of Z ordering. Now, if you have not seen our previous video, I would recommend you to watch this video first. So, without any delay, let's begin. Now, before we can begin with the code example, let's understand what is data skipping and how Delta Lake optimizes data skipping using Z ordering. Now, if you remember our previous video and the example that we used orders data, wherein we were getting orders from multiple companies and the order numbers were like this, ORD 001 and like this, and the order is distributed into multiple Parquet files. Now, in our previous example, since we had to search order based on country, so we partitioned the data based on country in order to find out order numbers along with country, right? What if we have only order number but not country? And we know that the order number is a high cardinality column. Now, we cannot partition the order number, right? Because it's a high cardinality column. If we start partitioning the order number, it will create multiple partitions. And again, the query will lag because of multiple partitions. So to prevent this issue, Delta Lake implements something called Z ordering. Now, if you understand Z ordering properly, consider we have data spread in 3 Parquet files wherein the data is from multiple countries. Now, it can be from India, USA, Australia. Now, the order IDs for each of the data is distributed in multiple Parquet files, right? Now, consider you have to search for an order called ORD 1001. Now, we know this is in Parquet file 1. Since we cannot implement any partition technique on the order ID column, we have to scan all the files in order to find out this order ID. Now, how we can optimize this using Z order? Consider you have stored this data in a Delta Lake table. Now, to optimize this with Z order, you will run a query where you will specify that you have to Z order this table by order ID. And once you do that, what will happen in the background is all the data for that particular order ID column will be first sorted and then distributed in different files. So if you see for the first table, once you Z order by order ID, it will distribute the data in sequential orders. So the first file will contain the data from 1001 to 1004. Similarly, for second file, it will be from 1005 to 1008, and the third file will get the next two. And once this is done, Delta Lake will store this data in its metadata. So whenever you will try to find a particular order, so it will know which particular file has this data. So it can skip the rest other 2 files. So consider you are searching for order 1006. In that case, it will straight go to the second partition because it knows that the second partition contains the data from 1005 to 1008. So it will skip the first file and the third file, and it will only scan the second Parquet file. And in this way, Delta Lake implements Z ordering by data skipping. Now, consider you want to search data by country. In place of partition, you can also Z order the data by country. In that case, the data will again be sorted and distributed in different files. So you can see, as per the data distribution, the Australia is in the first file, India is in the second file, and USA is in the third file, right? So as soon as you search for country equals to IN, it will straight go to the second Parquet file. It will not go to the first Parquet file. Okay. Now, Z ordering is on multi-dimensional as well. It means you can implement Z ordering on more than one columns as well. Okay, now consider you implement the Z order by country and order ID, because in your search query you have conditions like where country equals to Australia and order ID equals to some order ID, right? In that case, how Z ordering will be implemented? So if you see, the data is distributed into multiple Parquet files. Now, since this is based on 2 columns, the data will be distributed into multiple Parquet files. So here, first the country data will be sorted and then the order ID will be sorted. So if you see, the Australia data is sorted with the order ID, where the first 2 records are in the first 2 file, the third record is in the third file. Similarly, for India, you can see the order 1001 is in the second file, order 1005 is in the third file, Order 1006 in the fourth file, similarly 1010 in the fifth file, right? But the order ID is still sorted and the country is still sorted, right? Now, as soon as you put these columns in the predicate or the filter condition, it will straight go to that particular file in order to read that data. And this is how Z ordering is being implemented. Now, don't worry. If you are getting confused with this one, don't worry about it. We will see this with a live example. Now, I am in my Databricks Community Edition. Now, if you don't know how to log in into Community Edition, you can go back and watch our previous video. I have shown the steps that you can follow in order to enroll for Community Edition. Now, the data set that we are going to use today is retail data that you can find in this location in the Community Edition. I have copied the same sales data to a particular location in my Databricks. So if I show you the data, this is a CSV file which contains sales data, which contains some columns like invoice number, stock description, country, customer ID, etc. Okay, and I'm going to read this data and write it in form of delta, because we are going to perform optimization on delta table in order to see the Z order and the optimize commands, right? So I have rewritten this data with a partition of 16 so that we can split the files into 16 files, and I've written this to a particular location which is sales delta. Okay, let me show you the delta table first. So I'll run the select star command. Great, you can see the data, right? It contains invoice number, stock, description, quantity, and some columns like customer ID and country. And this is all a delta table. Okay, now before we can go ahead, let me show you the location where the data is written. So this is the location where the sales data is present, right? So let me run this as well. Now you can see that we have total 16 files in this location. And this is because I've repartitioned the data in order to make sure that we have more number of files, and each of the file size is quite small. Okay. Now, before we can go ahead and optimize this, let's go ahead and search for a particular invoice number in this table. So I'll copy one of the invoice number from the top. So let me just go ahead and copy this one. So I'll copy this, and we will write our SQL query in order to find out that invoice number. Okay, to do that, I'll write select star from sales delta where invoice number is equals to, and I'll put the invoice number. So let me run this. Awesome. We get the data for that invoice number. So we have more than one stock code and the quantity for that invoice number. Okay. Now let's go ahead and see what has happened in the background. To do that, I'll open the compute tab. I'll get inside the cluster and to the Spark UI, and then in the SQL DataFrame tab. Okay. Here's the query that we just ran. So I'll open this and I'll expand this. So if I expand this, if I scroll to bottom, you can see the number of files read. This is 16. And this is because delta table does not know where this invoice number lies. It can lie in any of the 16 files. Okay. Let's go ahead and see what are the minimum and the maximum invoice number for each of the file, so that we understand that how the data is right now present. Okay. To do that, what I'll do is I'll write one more SQL query. So for that, I'll write select minimum of invoice number and maximum of invoice number, and we will use one column which is hidden, which is called metadata, in order to find the file name. Okay, and we'll use the .NET notation because this metadata column is a JSON column. So we'll use dot file name in order to get the file name. Okay, from sales delta, and we will group by, and I'll copy the same column because we'll group by file name in order to see the minimum and maximum invoice number, and we'll order by minimum invoice number. So I'll copy this and let me run this. Okay, we got the data. Now if you see, this data is overlapping. It means you don't know which invoice number will lie in which of the files. Okay, all the files start from the same minimum invoice number and ends on a different max invoice number. So it does not segregate the data in between the files, and the data is not distributed properly. The data is uneven distributed in all of the files. Okay, so let's go ahead and optimize this data using Z ordering technique. Okay, and before we do that, we need to see one of the configuration which is very important related to Z ordering. So let me just show it to you. This is Spark Databricks Delta Optimize Max File Size. Now, the default value for this is 1 GB. And what exactly this is? This explains that if you try to optimize the delta table, it will try to pack as much as data with the maximum size of 1 GB. Okay, so consider you have data of 1.2 GB. If you try to optimize the table, delta table will optimize this in two files. The first file will be of 1 GB and the second file will be of 200 MB. Okay, now since we have very less data, we will try to play around with this configuration in order to make sure that we have many more files in order to see how Z ordering is working. Else it will try to pack all the data in one file, so we'll not be able to see what is happening in Z ordering. Okay, so we'll play around with this configuration now. So let me just copy this configuration from here, and I'll go back and we'll set this to 64 MB. Okay, so our file size would be maximum of 64 MB. So to do that, I'll write spa dot conf dot set, and we'll set to 64 MB. To do that, I'll write 64 into 1024 and into 8, because this is in bytes. Okay, so this will make sure that the maximum file size for our optimization will be of maximum 64 MB. Okay, so let me just run this. Okay, this completed. Now let's go ahead and optimize our table. To do that, I'll write SQL and I'll write optimize and the table name, which is sales delta, and then we will write Z order by the column which is invoice number. Okay, let me run this. Okay, so it has some metrics that you can go ahead and see, and let me just go ahead and copy the previous query for our minimum and maximum invoice number. So I'll copy this and I'll paste it here in the bottom, and let me rerun this query now. Awesome. Now if you see, the invoice numbers are not overlapping. It means if you see the first one, the end max number is 539259 and the starting of the second one is 539259. Similarly, the end is 541784 and the starting of the third one is 541784. And you can see all the part files in sequence. Okay, and similarly the data is arranged in sequence as well. So what has happened in the background is Delta has got all the invoice number, arranged it in sequence order, and then distributed in different part files. Okay, so our data is now Z ordered. Let's go ahead and run that same SQL query in order to see what time it takes in order to find that particular invoice number now. So to do that, I'll rerun this query. And if you see, it just finished. Okay, so it was so fast. Let me just go back to the cluster details. So our previous query took around 3 seconds. Okay, now let me refresh the SQL and DataFrame tab and open the latest query. Scroll down to the bottom for the scan Parquet, and if I go here, now if you see, the number of files read is 1. So it has only read that particular Parquet file which is having that invoice number, because it knows by sequence which Parquet file contains that invoice number. Okay, and it has completed in 0.5 seconds. So you can understand the optimization that has happened for a high cardinality column in Delta table. Okay, now let's go and check the metrics as well. So I'll just go back, and this is our optimize command that we ran. So let me just expand this metrics. So if you see this metrics, so if we see, the number of files added is 16 and removed is 16. And if you scroll down, the importance is this Z order stats. Okay, it captures all the stats for your Z ordering in this particular information. Okay, now since we have done this based on invoice number, let's go ahead and optimize this now on multidimensional. So what we'll do is we'll add one more column called country, and we'll see what happens to it. Okay, so I'll add country column here in the Z ordering, and I'll rerun this. Okay, now in this time, if you expand the metrics, you can see the number of files added were 16. So there are some different logic that happened this time. Let's go ahead and see what happened in the background. So I'll copy the same query again, and this time we'll add country in the query. Okay, because we added country. So I'll just add country column here, and we will group by country as well along with the file name in order to see what has happened. Okay, and we will order by country and minimum invoice number. So let me rerun this query. Awesome. Now if you see, we have Australia, Austria, and all of the country details, and for each of the country, the minimum and the maximum invoice number is separated in different part files. Okay, so if you see, for Australia, the minimum and maximum invoice number is this, and this is in part 005. Okay, and similarly, after 53949,419, it is 540267 for Australia, which is in part 01. Okay, now all of the data is in different files, and for Australia, it has distributed the data in different part files. Okay, now the important thing to notice here is, once you start adding more and more number of columns in Z order, this data will get distributed in more and more number of files. So it is very important that you decide what would be the Z ordering. So what if now you rerun this query, select query, without country filter. Okay, so we'll not use country filter, but we have done the Z order by country. So we'll rerun this again. Okay, so let me rerun this. So it has completed. Let me just go back to the cluster detail, refresh the Spark data frame, and let me just go to this. And if I scroll down to bottom and I expand this, number of file read is 2. So if you see, it has to read more number of files because we have added Australia as well in Z order. Okay, let's go ahead and put Australia in the filter condition and see what happens. Okay, so I'll go back, and in this invoice number, I'll change the invoice number, which is for Australia, and I'll add a country, and country equals to Australia. Okay, I'll just make it in single quotes. and I'll rerun this query. Awesome, this query completed. Okay, let me just go back to the cluster and refresh the SQL and DataFrame tab. So this is the one. I'll just open this. So this completed in 0.5 seconds now. Okay, and if I expand this and go down, so if you see, the number of file read again became 1. Okay, so it is very important that you select your Z orders properly. Okay, you cannot just blindly put any column as Z order and start searching for other columns, so it will create problem. So you have to select the correct orders for Z order. Okay, now that we are already using country in the filter condition, is there a better way to do it? The answer is yes. We can use the combination of partition and Z ordering. So we can partition the table based on country, and then we can Z order the data based on invoice number. So in that case, our performance will be much more better because we don't have to Z order the whole data based on country now. Okay, so I have already created one table called sales data partition. So this is again a data table partitioned on country, but we have not optimized it yet. So let me just quickly show you the data. So I'll use dbutils.fs.ls and I'll put the location. So let me just paste it here. So I'll put it here and I'll quickly do a display so that we can see it better. Awesome. Now if you see, this is a partition data where we have country equals to Australia. Okay, so let me just copy the first one, Australia one, so that we can see the number of files inside each partition. Okay, so I'll just place it here and I'll run this. Awesome. In Australia, you can see there are almost 16 files. Okay, this is a delta table and this is a partition delta table. Okay, so let's go ahead and optimize this table now. Okay, so before I optimize this, let me just run this query and see the performance first. So I'll run this. And this query completed in almost 3 seconds. So let me just go back to the SQL data frame and open the latest query, which says 3 seconds as total. And if I open this, scroll down, you can see the number of partition read is 1 because it is reading the Australia partition, and the number of files is 16. Okay, so let's go ahead and optimize this table. To do that, I'll just scroll down to bottom and we will use a filter condition if we want to selectively partition Australia. Okay, so consider we only want to Z order the data for Australia. So in that case, we can use a filter condition called where country equals to Australia. And if we want to Z order the whole table and optimize it for all the partitions, then we cannot use the selective one. Okay, let's do it only for Australia. So I'll put a filter condition, optimize the table name with country equals to Australia. Now you need to be very sure. If you put a where condition, your table needs to be partitioned based on that column. Okay, since our table is partitioned on country, I'll put country equals to Australia and I'll run this. Okay, now the selective optimization Z ordering is complete. So if we expand the matrix, you can see the number of file added as 1 and removed from 16. Okay, so if I go back, I run the same query again. So if I run this now, this completed in 1.52 seconds. Okay, previously it took 3 seconds. Now let me just go back and refresh the SQL data frame tab. And if I open this, go to the bottom and expand. Now if you see, the number of file read is also 1. The number of partition read is also 1. Okay, so we have optimized in order to make sure that only one file would be read and only one partition would be read. So this is data skipping at its best. So now you can understand how you can combine multiple techniques like partitioning, Z ordering in order to make sure that your data table is completely optimized and your data scanning is also optimized. So these are some of the Z ordering techniques that you can use in order to optimize your data table. Now, if you want to learn more about it, there is a documentation by the Delta IO. You can find it here, all about delta optimization, and all of this is there in this documentation. You can go ahead and check this out. I'll put this link in the description of the video. Now, before we wrap up, there's one more thing we need to discuss is auto compaction. Okay, by default, delta table provides this auto compaction in which the optimize means small files will be automatically compacted. Okay, but the data will not be Z ordered. Z order is something that you have to specifically provide as instructions. But optimization, or optimization when we say, is the compaction, means smaller files would be combined into one, can be done by auto compaction as well. Okay, this feature is available from Delta Lake 3.1.0. Okay, you can go ahead and check this out from this documentation. Today we are going to discuss about two of the important topics. The first one is deletion vectors and the second one is liquid clustering on delta tables. Okay, let's start with deletion vectors. What exactly are deletion vectors? So in a normal delta scenario, whenever we modify a data in a particular Parquet file, the whole Parquet file will get rewritten, right? That's a general scenario in a delta table. But consider a case you have millions of data in a particular Parquet file and you just try to delete one of the record. In that case, the whole Parquet file will be rewritten, and that's an optimization issue. So what is the solution here? The solution here is to add deletion vectors. So what Delta does is, consider you have millions of records written into a Parquet file and you just want to delete a single row. So if the table is enabled with deletion vector, a particular vector or say a flag would be added to that row, which is deleted by you. In that case, the data will not be rewritten. Rather, the row in that Parquet file will be flagged as deleted, right? So next time when you read the data from that particular Parquet file, only the rows which are not marked or flagged will be read. Okay, so this is how the data will get deleted. And next time when you run your maintenance, which is optimize, or your predictive maintenance, which is the predictive optimize command, automatically the Parquet file would be rewritten and all the rows which are marked for deletion would be removed from that Parquet file. And this is how deletion vector works. I am in my Databricks workspace. I've already created a new notebook called Delta Tables, Deletion Vectors, and Liquid Clustering. And I've already turned up my compute, which is with data cluster. Okay. The first thing that we are going to do is we are going to read a CSV file which has been provided by Databricks at this location. You can also read it from the same location. This data set is common for everyone. So in order to read a CSV file using SQL commands, we are going to use a utility called read files first. Okay, so before we do that, let me just write a select command in order to see if we can read the data. Okay, so to do that, I'll write select star from, and we are going to use a utility called read files. Now, the first thing that we need to do is we need to provide the path from where we need to read the file. So I'll just copy this from the top and I'll put it in single quotes. And next we need to provide it some options. So we already have header in this data. So I'll write header, and with implies I'll write true. And we also need to give the format. So the format for the data is CSV. Okay, now that we are done, let's go ahead and run this cell. Awesome. We can see the data is being read properly. It also has a rescued data column, which is generally used in case the schema does not match. But that is not a concern for us right now. So we are able to read the data using this read files utility. Okay. So let's go ahead and create a table on top of this. To do that, I'll just use a CTS command. So I'll write create table and we'll do it under dev bronze. Okay. So I'll write dev dot bronze dot sales and I'll put as. Okay. So I'll rerun this. Our table just got created. So let's verify that. To do that, I'll write select star from dev dot bronze dot sales and I'll run this. Awesome. Now that we can see data in the table, let's go ahead and write a describe command to see the metadata of this table. To do that, I'll just write describe extended and the table name. So let me run this. Awesome. We can see the metadata of the table. So if I scroll down to bottom, you can see the table properties here. It says enable deletion vector as true. It means the deletion vector is enabled for this particular table. Okay. So let's go ahead and first turn off the deletion vector, and then we are going to delete the data, and then we are going to turn it back on, and we are going to again delete the data. So to do that, I'll just type alter table, and the table name I'll type set tbl properties, and I'll make it false. Okay, so this is the property that you need to use for deletion vector, which is delta.enable deletion vectors. So first let me just turn this off. So I'll just run as false. Awesome, this is done, right? So let me just go ahead and run the describe command again. This is done, and if I go down, you can see it says enable deletion vector is false. Now that we have already disabled the deletion vector, let's go ahead and delete an invoice number which is 5406444 from the data. To do that, I'll just write delete from the table name, which is dev.bronze.sales, and I'll put the condition where, and I'll copy it from here and I'll paste it, and let me put semicolon and run this. Awesome. It says number of rows affected is 35. It means 35 records are deleted. Okay, so let's go ahead and write describe history to see what has happened for this delta table. So I'll just write describe history and I'll copy the table name from here and I'll paste it here and I'll run this. Nice. Now you can see the history of the table. Okay, the first one was CTAS, then we disabled the deletion vector, right? It is false. So this is what happens when we do not have deletion vectors enabled. Okay, and then we deleted the record based on this condition, which is invoice number and this 540644. Okay, let me scroll to right and you can see the operation metrics here. So if I expand this, now you can see the delta has rewritten some of the files. So it has removed the 2 files and it has added 1 file. Okay, and if I scroll up, you can see num deletion vectors added is 0. So it is not adding any deletion vector flag, rather it is rewriting the files when the deletion vector is not enabled. Okay, so this is the default property of a delta table in case a deletion vector is not enabled. So the data will get rewritten again. Okay, Now we will enable deletion vector, but before that you need to know deletion vector works with Delta Lake 2.3.0 and above. And if you're running it on Databricks runtime, then you have to have 12.2 LTS plus. Okay. Now let's go ahead and enable deletion vector on this table again. Okay. So to do that, I'll just make it true and I'll rerun this. So it says okay. Let me just go ahead and run the describe command here. As soon as I do that, scroll down, you can see the property here, deletion vector enabled is true. Okay, so it has enabled the deletion vector. Let's go ahead and remove another invoice number from this table. So I'll just go up and copy one of the different invoice number from here. So I'll scroll down and now I'll delete this invoice number from this table. Okay, so let me just run this. It has deleted 4 records now. Okay, so if I scroll down and run the describe history now, if I scroll to the left, so you can see the delete has happened. Before that, we have changed the table properties, set deletion vector as true. Okay, so you can see the delete has happened for that predicate, and you can see the invoice number here. Let me scroll to right and expand the operation matrix now. Now, if you see, we do not have any files removed. Rather, we have deletion vector added. Okay, so it has added for 4 rows, deletion vectors were added. Okay, and if you see number of file added is 0, it means the data is not rewritten. Rather, it has added deletion vector flags for the records that we have deleted, and later when we run the maintenance or it goes into predictive maintenance, which is the optimize command, it will automatically remove those flagged records while rewriting the Parquet file. Okay, so you can even do that. You can just write optimize command right now with the table name. So you can just write optimize and the table name in order to run that maintenance. So it will automatically remove while rewriting all the rows that were marked for deletion vector. Okay, so now you know what exactly is deletion vector. Let's go ahead and check what is liquid clustering now. In our previous videos, we have seen optimization techniques like partitioning or Z ordering. But in all of those cases, there was one demerit. We have to rewrite the data whenever we try to optimize the table. But there is one neat way. Delta table has introduced something which is called liquid clustering. So whenever you enable liquid clustering on a particular column in a delta table, you don't need to rewrite the data. The incremental data will automatically get adjusted as per the cluster column that you have mentioned. Okay, so what are the scenarios where you can go ahead and use liquid clustering? So you can see here the below examples. So in case you have a high cardinality column on which you need to filter data, you have significant skew in your data, or your data is growing too quickly. Okay, and in cases you have different access pattern of the data, or in case you have some data where you have too many or too less partitions. Okay, in case of liquid clustering, delta table will take care of properly repartitioning the file sizes for the clusters that you have selected for the data. Okay, you don't need to worry about it. Only thing you need to do is you have to provide the cluster columns on which you want to query, or you want to filter, or you want to join your data. Okay, now I'm back in my Databricks workspace. So in order to use liquid clustering, you need to have Delta Lake with version 3.1.0 and above, or you can use Databricks runtime with 13.3 LTS or above. Okay, now in order to do a liquid clustering on an existing table or on a new table, you just need to provide one thing, that is cluster by. Okay, so we already have our sales data here right now, okay, with this table. Let me go ahead and copy this from here, and if I scroll down, I just need to type on an existing table, altered table. I need to provide the table name, and then I just need to write cluster by and the column name on which I need to cluster. So consider I want to filter the data based on invoice number. So I'll use cluster by invoice number. Okay, and I'll just need to run this. Awesome, the command completed, right? Let me just go ahead and write describe history and the table name, and let me just run this. Now if I scroll down, you can see it has added a thing called cluster by, and it says which column it has to look for clustering. Okay, the new clustering column is invoice number. Okay, and it will upgrade some of the protocols for your table, so you don't need to worry about it. It will take care of that automatically. Now in case you don't want to cluster your table, and if you want to go back, you just need to put none here. Okay, if you don't want to cluster your table, and if you want to go back to a simple table without clustering, you just need to mention cluster by none. Okay, so this is how clustering can be done. What if you want to do on a new table? In that case, while creating the table, so I'll just copy the create table from top, and I'll paste it here. So while creating the table, you just have to mention cluster by and the column name. So invoice number was our column, right? So you have to mention like this. So I'll just make it as CT, and I'll rerun this. So you can see the table is created. Let me just go ahead and do a describe extended on this table now. Now if I scroll down, you can see here it says clustering columns, and you can see invoice number. Okay, you can have more than one column as clustering columns, plus only limitation is you need to have the column within the first 32 columns in the delta table. Okay, that is the important point that you have to note. That is the limitation. Other than that, you don't need to worry about anything. You can just go ahead and do a select star from this table. Only thing that you need to do is you have to make sure that you are using the clustering column in the filter or the predicate. So if I do a select star from the table, where I'll just put invoice number and I'll paste it here. Okay, if I run this now, you can see this has run so fast, and this will become evident as you grow your data millions and millions. And now the best part is, once you have incremental data loading in this table, you don't need to worry about maintenance. The new data will automatically get clustered properly and you don't have to worry about it anymore. So that's the benefit of liquid clustering, and that is how you can improve the performance enabling liquid clustering on your delta tables. I hope you have learned a lot about delta tables till now. Keep learning, keep growing, and keep sharing.